இப்ப யூடியூப்ல வந்துரும் சார். நம்ம கோலைவ் கொடுத்துட்டு இப்ப வந்துரும் பாருங்க.
இப்ப நான் திருப்பி அந்த ஜூமுக்கு போட்டுமா? ஜூமுக்கு போட்டுங்களா?
போய்க்கலாம் சார். நீங்க ஜஸ்ட் ஒரு செகண்ட் அந்த யூடியூப்ல மட்டும் உங்க ஃபேஸ் தெரியுதான்னு செக் பண்ணிக்கோங்க சார்.
சரிங்க தம்பி.
எந்த கொடுத்து திருப்பி ஆன் பண்ணலாமா? எந்த கொடுத்து திருப்பி ஆன் பண்ணலாமா? இப்போ அப்படியே இருக்கலாமா? அப்படியே இருக்கலாம். ஆனா இது வந்து நீங்க 2 பேர் இருக்கிற மீட்டிங் தானே? ஆமா. இது பண்ணி என்ன பண்ண போறீங்க?
ஐயோ
உள்ள வரும். இதான் ஆனா அந்த ஷெட்யூல் மீட்டிங் தான் ஷெட்யூல். சார் இப்ப வருதா சார்? நீங்க பாத்தீங்களா யூடியூப்ல?
யூடியூப்ல என்னோட ஃபேஸ் தெரியுதுங்க தம்பி.
அதான் சார். நீங்க வேணா இப்ப அந்த உங்களுக்கு திருப்பி அந்த 3 பட்டன் இருக்குல்ல சார், நம்ம எங்க போய் கஸ்டம் ஸ்டார்ட் பண்ணுவோம். இந்த கண்டென்ட் இப்ப எல்லாமே ரெக்கார்ட் ஆயிட்டு இருக்கும். ஃபுல் லெங்த்தும் யூடியூப்ல அவைலபிளா இருக்கும்.
சரிங்க தம்பி.
இப்ப உங்களுக்கு இது வேண்டாம் அப்படின்னா நீங்க வந்து இப்ப திருப்பி போயிட்டு கேன்சல் பண்ணிக்கலாம்.
இல்ல வேண்டாம் தம்பி.
வேணுமோ
இல்லங்க தம்பி, அது ஓடிட்டே இருக்கட்டும், ஒன்னும் ப்ராப்ளம் இல்ல. ஓடிட்டே இருக்கட்டும், கடைசியா நம்ம எடிட் பண்ணிக்கலாங்க தம்பி.
ஓகே சார், தென் ஃபைன், நோ ப்ராப்ளம். ஓடிட்டே இருக்கட்டும். ஓகே சார், இப்ப லைவ்ல வந்து சொல்லலாம், ஒன்னும் ப்ராப்ளம் இல்ல.
சரிங்க தம்பி.
சார் இதுல இப்ப நம்ம ரிஹர்சல் இப்ப இன்னொரு 10 நிமிஷம் பண்ணீங்கன்னா அது எல்லாமே ரெக்கார்ட் ஆகும்.
ஆகட்டும் கார்த்தி, ஒண்ணும் இல்ல, கடைசியா நம்ம எடிட் பண்ணிக்கலாம் கார்த்தி.
யூடியூப்ல எல்லாருமே பார்க்கலாம்ன்றான். இந்த லிங்க் போனவங்க எல்லாமே பார்க்கலாம். ஏன்னா இதுக்கப்புறம் வந்து டைம் பிஸி ஆயிருவீங்க, 9 ஆயிடுச்சு.
சரி கார்த்தி,
அதனால அப்படியே இருக்கலாமா?
அப்படியே இருக்கட்டும் கார்த்தி, ஓட்டு பார்த்தா
ரைட் சார், நல்லா கிளியரா இருக்கீங்க, பக்காவா இருக்கு. லைவ் வந்து 1.22 செகண்ட்ஸ் ஓடிட்டு 1 minute 22 seconds.
இது சப்போஸ் இந்த லைவ் போயிடுச்சுன்னா நம்ம மறுபடியும் எப்படி கார்த்தி அந்த 3 டாட்ஸ்ல போய் லைவ் ஸ்ட்ரீம்
அதேதான் சார், லைவ் போகாது சார் இனிமே.
போகாது. ஓகேங்க தம்பி.
அந்த அதே ஸ்டெப் தான், அந்த மோர் அழுத்தி
சரிங்க கார்த்தி,
வர லிங்க்ல அந்த பிராக்கெட் எடுத்துட்டு
காப்பி பண்ணி
பேஸ்ட் பண்ணி பிரஸ் பண்ணீங்கனாக்கா வந்துரும். அப்புறம் வந்து கோ லைவ்னு அழுத்திட வேண்டியது.
சரிங்க கார்த்தி, சரி.
ரைட் சார், எது டவுட்னா கூப்பிடுங்க. நான் இங்க
சரிங்க கார்த்தி,
அப்படியே இருக்கட்டும், இந்த செட்டிங் மாத்த வேண்டாம்.
சரிங்க கார்த்தி, அப்ப நான் ஜூமுக்கு போயிடுறேன் மறுபடியும்.
ஆமா சார், இது இந்த ஸ்கிரீன் இருக்கட்டும். 2 ஸ்கிரீன் கம்ப்யூட்டர் தானே இருக்கீங்க?
ஆமா கார்த்தி,
இது ஒரு ஸ்கிரீன், அது ஒரு ஸ்கிரீன் தானே?
அப்ப சரி,
விண்டோ வேற வேற விண்டோ தானே, இது பாட்டுக்கு இருக்கலாம்.
இது பாட்டுக்கு இருக்கலாம்.
அப்பப்ப அது போகுதான்னு பாக்கணும்ல.
ஆமா ஆமா கார்த்தி,
அதனால அது இருக்கட்டும். இந்த விண்டோ பக்கத்துலயே ஜூம் விண்டோ இருக்கும்.
சரிங்க கார்த்தி,
அதை கிளிக் பண்ணுங்க. இது க்ளோஸ் பண்ண வேண்டாம், மினிமைஸ்.
சரிங்க கார்த்தி, சரி.
ரைட், ஆல் தி பெஸ்ட் சார். ஓகே சார்,
தேங்க் யூ கார்த்தி, தேங்க் யூ. Thank you, Karthi.
Thank you, sir.
Thank you, Karthi.
All the best, sir.
Thank you, Karthi. Thank you, Karthi. இது என்ன தம்பி, இதெல்லாம் காணோம். நான் இப்ப அட்மிட் ஆக கொடுக்க கூடாது. கார்த்தி, இப்ப நான் பேசுறதே திரும்ப எக்கோ கேக்குது. அது கேட்காம இருக்கிறதுக்கு என்ன பண்ணணும் கார்த்தி? இல்ல, யூடியூப்ல கேக்குது.
முத்துக்குமார் சார், குட் மார்னிங். முத்துக்குமார் சார், குட் மார்னிங். கிருஷ்ணமூர்த்தி.
குட் மார்னிங், குட் மார்னிங், குட் மார்னிங். இந்த ஒரு நிமிஷம் தலைவரே.
கேரியா
கார்த்தி சொல்லுங்க கார்த்தி. கார்த்தி சொல்லுங்க கார்த்தி. ஓகே சரிங்க கார்த்தி சரிங்க.
ரெண்டு ஆப்ஷன் சார்.
சரிங்க கார்த்தி.
யூடியூப் க்ளோஸ் பண்ணிட்டு மொபைல் வேற ஒரு மொபைல் யூடியூப் ஆன் பண்ணி செக் பண்றதுக்கு ஆடியோ.
சார் குட் மார்னிங் சார், குட் மார்னிங்
சார். ஆடியோ மியூட் பண்ணிங்க சார், யூடியூப் ஆடியோ.
சரிங்க கார்த்தி சரிங்க கார்த்தி.
அப்படி இல்லைன்னா அதை யூடியூபை க்ளோஸ் பண்ணிட்டு
சரிங்க கார்த்தி.
வேற மொபைல் யூடியூப் ஆன் பண்ணிட்டு
சரிங்க கார்த்தி.
மியூட் பண்ணிட்டேன்.
கார்த்திகேயன் சார், அது ஆடியோ மியூட் பண்ணாலே போதும், இது எக்கோ வராது.
மியூட் பண்ணிட்டேன்.
இப்ப எக்கோ வராது, செக் பண்ணி பாருங்க.
ஓகே மியூட் பண்ணிட்டேன் கார்த்தி, மியூட் பண்ணிட்டேன். தேங்க்யூ கார்த்தி. தலைவரா மியூட் பண்ணிட்டேன் தலைவரா. ஹலோ கிச்சு.
அண்ணி
குட் மார்னிங் சார்.
மீட்டிங் ஆமா வந்திருக்கேன்
சார் குட் மார்னிங் சார், முத்துராமன் சார் வாங்க. குட் மார்னிங்.
ஆமா குட் மார்னிங். உங்களோட மெசேஜ்ல பாருங்க மாமா, மெசேஜ் அனுப்பியிருக்கேன் பிரைவேட்.
ஓகே குட் மார்னிங்.
முத்துக்குமார் சார். தலைவரே வணக்கம். நீங்க பப்ளிக் அலோவ் பண்றதுக்கு முன்னாடி முக்கியமான ஆளு எல்லாத்தையும் உள்ள அலோவ் பண்ணிருங்க. அலோவ் பண்ணிட்டு பப்ளிக் அலோவ் பண்ணுங்க, பின்னாடி கிரௌட் ஆயிடக்கூடாது.
இல்ல இப்போதைக்கு இன்னும் அந்த சீஃப் கெஸ்ட் 9:35க்கு லிங்க்கு வரேன்னு சொல்லியிருக்காரு.
அவங்க எல்லாம் உள்ள அலோவ் பண்ணிட்டு அதுக்கப்புறம் நீங்க பப்ளிக் காமௌண்ட் ஆள் கொடுங்க.
அதாங்க தலைவர், அவருக்காக தான் வெயிட்டிங். அப்புறம் இப்போதைக்கு ஹெச்ஓடி நம்ம மெம்பர்ஸ் அவங்க வர,
சரி
அவங்கள மட்டும் அலோவ் பண்ணிட்டு.
ஆமா, ஏன்னா நாங்க ஃபர்ஸ்ட் பண்ணும்போது இந்த பிரச்சனை வந்துச்சு. ஒரு ஸ்பீக்கர் அலோவ் பண்ண முடியல, பயங்கர கிரௌட் ஆயிருச்சு. அதனால கவனமா பண்ணிருங்க. ஓகே தேங்க்யூ.
சார் வெயிட் பண்றாரு சார் இதுல கியூல.
அதான் பாக்குறேன். சார் ஜெய்சங்கர் சார், குட் மார்னிங் சார்.
குட் மார்னிங்.
ஆமா வாங்க வாங்க சார், சுந்தர் சார் வாங்க வாங்க சார். ஓ வாங்க சார் வாங்க சார். அதே இப்ப எல்லாரும் வராங்கன்ட்டு வெயிட்டிங் ரூம் போட்டிருக்கேங்க சுந்தர் சார். நீங்க வந்த பிறகு நான் உடனே அட்மிட் கொடுத்துறேன். நீங்க வாங்க, நான் லைன்ல தான் இருக்கேன். வாங்க வாங்க சார். சார் விஜய் சார் உங்களது மியூட்ல இருக்குங்க சார், வீடியோவும் ஆடியோவும்.
இல்ல வீடியோ மட்டும் நான் வச்சிருக்கேன். ஏன்னா உள்ள வரும்போது.
ஓ சரிங்க சார்.
உங்களுக்கு அந்த டெக்னிக்கல் ப்ராப்ளம் இருக்கும்போது சொல்லிட்டு நான் வச்சிருக்கேன்.
ஓ சரிங்க சார். தெரியுது சார். குட் மார்னிங் சார்.
அட்மிட் பண்ணும்போது பேண்ட்வித் அதிகமா இருந்த ப்ராப்ளம் இருக்கும்.
ஓ சரிங்க சார். சரிங்க சார்.
அவர் இப்ப வச்சிருக்கேன். அப்புறம் மேடம் பேசும்போது நான் பண்ணுறேன்.
சரிங்க சார். இவர் 9:35க்கு இப்ப வரேன்னாருங்க சார் லிங்க்ல கோஷ். அவருக்காக தான் வெயிட் பண்ணிட்டு இருக்கோம் சார். தேங்க்யூ சார்.
சார் ஒரு 10:30 to 10:45க்கு.
சரிங்க சார். சரிங்க சார்.
கொஞ்சம் அந்த வைஷ்ணவ காலேஜ் ஆன்லைன் எம்எஸ்சி ப்ராஜெக்ட் இருக்கு.
ஓ போயிட்டாங்க சார். போயிட்டாங்க சார்.
போயிட்டு நான் வந்து 1:30 to 2 ஜாயின்.
சரிங்க சார். சரிங்க சார். போயிட்டாங்க சார். போயிட்டாங்க சார்.
ஆன்லைன் தான்.
ஓ சரிங்க சார். சரிங்க.
தெரியாது, முன்னாடி இருந்தா அதை ஷிஃப்ட் பண்ணிக்கலாம்.
ஓ இல்ல பரவாயில்லைங்க சார். இது நம்ம ரொம்ப
மண்டே தான் மதியம் தான் சொன்னாங்க மேடம்.
ஓ சரிங்க சார். இதுக்கு ரொம்ப நாளா பிளான் பண்றோம் சார். ஆனா சரியாவே வரல. திடீர்னு உடம்பு சொல்லாம போச்சு. இப்படி மாறி மாறி ஜூலை
ப்ராப்ளம் தான். எனக்கு வீட்லயே அந்த லிங்க் ஒழுங்கா வர
மாட்டேங்குதா? சரிங்க சார். சரி.
பேண்ட்வித் சரியா இருக்க மாட்டேது. பசங்க 2 பேர் வச்சுட்டு அது ரெகுலர் கிளாஸ் போகுது.
3 தடவை ஷெட்யூல் பண்ணி மாறி போச்சுங்க சார் டைமிங். அப்புறம் தான் சரின்ட்டு சரி கொஞ்ச நாள் போகட்டும் அப்படின்னு விட்டுட்டோம்.
ஏர்டெல் பிராட்பேண்ட் இப்ப ஜியோ வாங்கி வச்சிருக்கேன்.
ஓ சரிங்க சார். சரிங்க சார்.
ஏதாவது அப்படியே திடீர்னு காட்டானே ஏதாவது அட்ஜஸ்ட் பண்றது.
ஓ சரிங்க சார். சரிங்க சார்.
இல்லன்னா
நான் இங்க ஏசிடி வச்சிருக்கேன் சார். அதான் 1க்கு 2 கனெக்ஷன் வாங்கி வச்சிருக்கேன். ஒண்ணு போனாலும் இன்னொன்னுல கொடுத்துடுற மாதிரி சார்.
இது கூட செல்போன்ல யூஸ் பண்ணிக்கிறேன். அது
ஓ ஆமா, செல்போன் கூட ஒண்ணு இருக்கு. சரிங்க சார்.
அதனால இந்த மாதிரி வெபினார் கண்டது ரொம்ப ரிஸ்க் ஃபேக்டரா தான் இருக்கு.
ஆமாங்க சார்.
ஸ்கூல்ல ஆரம்பிச்சு ஸ்கூலு காலேஜ் எல்லாம் நடக்குதுங்களா
ஒரே நேரத்துல? ஆமாங்க சார். திடீர்னு சர்வர் டவுனுங்கிறோம். அப்புறம் மறுபடியும் அவனுக்கு போன் பண்ணி வர சொல்லி நேற்று அப்படிதான் ஆச்சுங்க சார்.
பசங்க விளையாடி வயர் வர ஆரம்பிச்சு அது ஒரு 2 தடவை ஆச்சு.
ஓ சரி.
ஏர்டெல்ல உடனே ரெஸ்பாண்ட் ஆகும்.
ஓ சரிங்க சார். சரிங்க சார். நான் ஒரு கோஸ்ட் சாருக்கு போன் பண்ணிக்கிறேன். மேடம் வணக்கம் மேடம். மேடம் இவரு நம்ம பிரின்சிபல் சார்ட்ட பேசுறீங்களாங்க மேடம்? ஆமாங்க மேடம். அவர்கிட்ட அதான் காலையில ஒரு வாட்டி இப்ப ஒரு வாட்டி பேசி நம்ம 10 o'clock 9:55 எல்லாம் ஜாயின் பண்ணா போதுங்க மேடம். 9:50 வந்தாருன்னா நமக்கு எல்லாம் அரேஞ்ச்மெண்ட் பண்ணி கரெக்டா இருக்குங்க மேடம் ஸ்டார்ட் பண்றதுக்கு. ஆமாங்க மேடம். 9:50 ஒரு 10 minutes எல்லாரும் வந்துட்டாருன்னா நல்லா இருக்குங்க மேடம். சரிங்க மேடம். சரிங்க மேடம். தேங்க்யூ மேடம். Sir, Sundar sir, good morning, sir. Sir, R sir.
Sir, good morning, sir.
Good morning, sir. வாங்க.
Morning, sir.
அந்த இத மட்டும் கண்ட்ரோல் மட்டும் நீங்க பாத்துக்கிட்டீங்களா சார்? நான் உங்களுக்கு
கண்டிப்பா சார். கண்டிப்பா.
சார்
குட் மார்னிங் சார்.
சார் விஜய் சார்.
Good morning, sir. Good morning, sir.
நான் இவர் கெஸ்டுக்கு ஒரு ஃபோன் பண்ணிடுறேன் சார். Sir, good morning, sir. Sir, shall I make a link, sir? Yes. Yes, sir. Yes, sir. We can make a trial. Yes, sir. I'm in the link only, sir. I'm in the Zoom link only. Just you can join directly, sir. Thank you, sir.
Sir, allow பண்ண ஆரம்பிச்சிட்டுமா?
சார் சுந்தர் சார் இருங்க. இவர் நம்ம கெஸ்ட் வந்திருக்கிறார். நம்ம
சரிங்க சார்.
அவருக்கு ஃபோக்கஸ் கொடுத்துருவோம். சார் thank you, sir. Sir, I will make it you as a co-host, sir. You can present on your place itself, sir.
Yeah, now what I will do?
Sir, 10:15 to just a minute.
Around 10:15 I will join, right?
Yes, sir. 10:15 to 11 o'clock is the schedule, sir. You can enter around 10:05 or 10:10 like that, sir.
Fine.
Yes, sir. Are you hear me without any disturbance, sir?
No, I think now so far it's fine.
Okay, sir. You are audible, sir. You are audible. We are hearing you about without any disturbance, sir.
Okay, fine. Actually, in Mumbai, we have very bad weather from yesterday.
Sir told, sir. Prabha sir told me. Yes, sir. Now it is working, sir. Sir.
Hello.
Sir, now it is okay, sir. Weather, how is the weather right now, sir?
Now it's a bit better.
Better. Okay, sir. Right.
Little bit, just I am not able to hear you properly. Little bit, just sound hesitate.
Sir. But sir, Sundar sir, நான் பேசுறது கேக்குதுங்களா சார்? சுந்தர் சார்
நல்லா கேக்குதுங்க சார்.
சார் விஜய் சார் கேக்குதுங்களா சார்? சார் அதர் சார் I don't have any problem on hearing my voice, sir.
I am audible, right?
You are audible, sir. You are audible,
okay.
But your video is not presenting, sir. Just to make your video presentation. Yes, sir.
Just a minute. It was, I think, some. बाबाई के दाखवते
তুমি কি তোর ভিডিও তো
ভিডিও শেয়ার করি আমাকে দেখতে পাচ্ছি না
Sir, in the left bottom on audio image will be there, no sir? Just
Yes,
unmute
sir.
that video. No sir, as far as sir, go sir.
சில பிபிடி உங்களுக்கு அனுப்பிச்சிட சொல்லுங்க சார். நீங்க லிங்க் கொடுத்து பெட்டர்.
Sir, go sir.
Yes.
Yes, sir. If you have any trouble in presenting your PPT, means you please mail your PPT to us, sir. We are presenting your PPT from our end. So you can.
I think let me try from here.
Okay, sir. Fine, sir. Fine, sir.
அவரை ஜாயின் பண்ணிட்டு அவரே கூட ஆபரேட் பண்ணிக்கிறாங்க. நீங்க ஓபன் பண்ணிட்டீங்களா?
Okay, sir. Okay.
அது பாசிபிள் சொல்லுங்க.
Okay, sir. Sir, you can operate from your end itself, but we are presenting here from our end, sir.
Join பண்ணி விட்டீங்கன்னா
after joining your video is not we are able to hear you, but your video is not presenting, sir.
Hello. Good morning.
Sir, good morning, sir. Good morning, sir.
Good morning. Good morning. Good morning. எப்படி இருக்கீங்க டாக்டர் ஜெய்சங்கர்?
ஃபைன் சார். நல்லா இருக்கீங்களா?
நல்லா இருக்கேன், நல்லா இருக்கேன். So thanks to Muthukumaran sir.
Thank you, sir. Thank you, sir.
Because of Dr. Muthukumaran sir only, I am going to meet Dr. Jaishankar once again after a long time. So
sir, first speaker that our Dr. AK Ghosh sir is on the line, sir, but video is not.
No problem. I'm just checking.
Yes, sir. He is trying to make it.
Okay, sir. Okay. Bye.
Madam, join பண்றீங்களா மேடம்? Okay, madam. மேடம் WS மேடம் கேக்குதுங்களா மேடம்? ஓகே.
கேக்குதா?
கேக்குதுங்க மேடம், கேக்குது. அவர் சீஃப் கெஸ்ட்காக வெயிட்டிங். மத்தவங்க எல்லாரும் வெயிட் பண்ணிட்டு இருக்கோம் மேடம். சார் இருக்கார், விஜய் சார் எல்லாரும் ஸ்கிரீன்ல பாத்தீங்கன்னா தெரியும் மேடம். அவர் சார் பர்சனல் ஜெய்சங்கர் சார் கூட வந்துட்டாங்க மேடம். கோஷ்காக தான் வெயிட்டிங். மறுபடியும் வந்து sir, it is disconnected, sir, from your side.
So I am just again trying just to accept my this thing.
Okay, sir.
So that
yes, sir. If you have any trouble, you please send the yes, sir. Send your PPT, sir.
there you not share some animation is there. That's why just.
Oh, then okay, sir. Then fine.
Yeah, who is speaking actually? I have to just enter from here.
Oh, fine, sir.
Other than later I can share this thing.
Yes, sir. Yes, sir. Thank you, sir.
Hello.
Yes, sir.
Can you just see my?
Yes, sir. Yes, sir. Yes, sir. You are displaying membranes for chemists.
Yes.
That slide we can.
Right.
Yes, sir. Sir, Dr. Parsaman Jaishankar sir also in the link, sir. You can talk
Okay.
to him few words, sir.
Sure.
Sir, Parsaman sir.
Hello.
Hello, sir. Sir.
Yes.
Parsaman Jaishankar sir.
Okay.
Oh, sir, just a minute, sir.
Audio.
Sir.
Hello. Sir, Professor A.K. Ghosh is on the line, sir.
Hello.
Okay.
Yes. Hello, Professor Ghosh.
Yes. Hello, sir.
Yeah. Good morning.
Morning.
I heard about you, but I didn't meet you actually.
Hello.
Hello.
Yes.
Nice to meet you, sir. I heard about you, but I have not met you in person.
Thank you so much. Same to you. I am looking forward to meet you also.
Thank you very much, sir. Thank you. Actually, if you can stop sharing the screen only, we can see others' video, I suppose. No, Muthukumaran, sir?
Yes, sir. Yes, sir. Sir, Hindi la tani na Hindi la kuda pesing, sir.
কোনো অসুবিধা নেই। আপনার ওই স্ক্রিন শেয়ারিংটা একটু বন্ধ করলে সবাইকে দেখতে পারবো আর কি। সো কত বছর হয়েছিল আপনার চেন্নাই গিয়ে? Professor Ghosh?
Just I am doing.
Sure.
No, yes, sir. Yes, sir. Thank you, sir.
Stop here.
Sir, Muthukumaran sir.
Sir, sir.
அதே நைப்பர் ஸ்டூடெண்ட் அபவுட் ஒரு I think 30 students will register actually, so they are now on the
Yes, sir. Nearly 41 students are waiting in the room, sir.
Yes.
So after entering our yes, sir. We are hearing, sir. Okay. Sir, we are hearing, sir. We are hearing.
Okay. Can you see me?
No, sir. Our video is not present.
Not yet, sir. Not yet. Yeah.
Yes, sir.
Just click on the video, sharing just video on the video.
Yeah, I am just clicking in the video. Somehow I do not know.
जो तुम्हार ये काज হচ্ছে না ক্যামেরা তো ঠিক আছে
Somehow my camera is disturbing. It's not
না নিচে গেলে আপনার একটা চিহ্ন থাকবে যেটা ভিডিও ক্যামেরার মধ্যে।
হ্যাঁ,
তার উপরে আপনি ক্লিক করলে পেয়ে যাবেন।
ওটা অন আছে স্যার।
ওটা অন আছে?
হ্যাঁ, কিন্তু ওই ক্যামেরার পিকচারটা ওইটা কাট আসছে কেন বুঝতে
বাবা। এ বাবা, তাহলে তো ঝামেলা হয়ে গেল, আপনাকে দেখতে পারবো না তাহলে আমরা। তো ক বছর হলো স্যার আপনার ওইখানে গিয়ে?
বিআরসি তে আমার 25 বছর হয়ে গেছে, 25 ইয়ার।
ও মাই গড, তাহলে আমার থেকে বেশি, মানে প্রায় আর কি। আমার তো 30 বছর হয়ে গেল কলকাতাতে আইএসসিবি তে।
আচ্ছা আচ্ছা আচ্ছা।
সো আমাকে তো, আমি পড়তে পারি লিখতে পারি বাংলা।
ওকে। আমার ঠিক ছিল, জাস্ট
আচ্ছা,
বুঝতে পারছি না সাডেনলি কি হলো। এখন আমাদেরও ম্যাক্সিমাম মিটিং এখন ওই এতেই হয় তো।
ওই তো, হ্যাঁ হ্যাঁ হ্যাঁ, সব মিটিং এ তো এখন তো ওইভাবে হয়ে গেছে, কিছু করা যাচ্ছে না। রোজ কয়েকটা মিটিং করতে হচ্ছে এইভাবে।
হ্যাঁ,
আমাদের গুলো এমএস টিমে হয় অ্যাকচুয়ালি, যেহেতু কি একটা সিকিউরিটি ইস্যু নাকি
অ্যাকচুয়ালি
এটা।
এক্স্যাক্টলি আমরা গুগল মিট বা
হ্যাঁ হ্যাঁ
সব টিমেই করি।
হ্যাঁ হ্যাঁ।
ম্যাডাম আজড়ি ম্যাডাম। சார் சுந்தர் சார், அந்த நம்ம இவர் பிரின்சிபால் ராவண சார் இவங்க எல்லாம் வெயிட்டிங் ரூம்ல வந்தாங்கன்னா டக்குன்னு அட்மிட் கொடுத்துருங்க சார்.
சரிங்க சார், நான் பண்ணிடுறேன் சார்.
ராவண சார் இப்பதான் இவர் சார் பார்த்தேன், தேவநாதன் சார் கூட பார்த்தேன். யார் பார்த்தாலும் டக்குன்னு அட்மிட் கொடுத்துருங்க சார்.
நான் கொடுத்துறேன் சார். தேவநாதன் சார் கொடுத்துட்டாங்க சார்.
கொடுத்துட்டீங்களா? சரிங்க சார்.
ஆமாங்க சார்.
ராவணன் சார் கூட பார்த்தேன்.
ஹலோ,
யார் வந்தாலும் அட்மிட் கொடுத்துருங்க சார் டக்கு.
ஹலோ
sir,
just 1 minute,
please sir.
Let me just restart my PC and check. I think it may work. Just I will take 2 minutes time.
Fine sir. 9:55 only, so okay, no problem sir, please sir.
சார் தேவநாதன் சாருக்கு கொடுத்துட்டேன்.
sir good morning sir. Principal sir good morning sir. Sir mute let me, sorry sir.
Yeah, very good morning.
Good morning sir.
Yeah.
Good morning sir.
Yeah, very good morning madam. Good morning sir. Yeah.
Madam actually madam நம்ம மேடம் பரசுராமன் ஜெயசங்கர் சார்ல சார் இருக்காங்க மேடம். சார் பரசுராமன் சார் மேடம் பேசுறாங்க சார்.
குட் மார்னிங் மேடம்.
Good morning.
Thank you very much. Good morning sir.
Sir, principal sir, good morning.
Yeah, very good morning please.
Morning sir. How are you ma'am? How are you sir?
Fine sir, very much.
Thank you sir, thank you.
Yeah.
ரிசோர்ஸ் பர்சனுக்காக வெயிட் பண்ணிட்டு இருக்காங்க சார். சார் வந்துட்டு ட்ரையல் பார்த்துட்டு போயிருக்காங்க சார். திருப்பி ஒரு 5 நிமிஷம் வந்துருவாங்க சார். பிரின்சிபல் சார் அதுக்காக தான் வெயிட் பண்ணிட்டு இருக்காங்க சார்.
ஓகே
சார் பிரின்சிபல் சார்.
எஸ் சார் யா
சார் ரிசோர்ஸ் பர்சன் சார்க்காக தான் வெயிட் பண்ணிட்டு இருக்கோம் சார். சார் ராவன் சார் குட் மார்னிங் சார். சார் அவர் ரீஜனல் ஜாயினிங் டைரக்டர் ஹஸ் கம் சார்.
ஓகே சார். ஹலோ
சார். எஸ் சார், டாக்டர் ராவன் சார்.
குட் மார்னிங் சார்.
RJD சார்.
சார் RJD சார் குட் மார்னிங் சார்.
குட் மார்னிங் சார்.
Good morning sir. Good morning. I'm Jayashankar from Calcutta sir. Yes.
Good morning RJD sir.
சார் இன்னும் பார்க்கலங்க மேடம். கனெக்டிங் ஆடியோன்னு வருது மேடம் அவருக்கு. சார் மியூட்ல இருக்கு, மியூட்.
முத்துக்குமரன் சார்.
சார் RJD சார். சார் குட் மார்னிங் சார். குட் மார்னிங் சார். மியூட்ல இருக்கீங்க சார். உங்க மியூட்ல இருக்கு, அன்மியூட் பண்ணுங்க.
சார் முத்துக்குமரன் சார் எல்லாம் பண்ணலாமா?
இருங்க சார். ஆமா இவர் வரட்டும் சார். ரிசோர்ஸ் பர்சன் சார் கோஷார் வந்த உடனே அட்மிட் பண்ணிடுங்க சார். சார் சார் ஆர்ஜேடி சார்.
குட் மார்னிங் சார்.
குட் மார்னிங் சார். குட் மார்னிங் சார். சார் ரிசோர்ஸ் பர்சன் சார் பரசுராமன் ஜெய்சங்கர் சார், நம்ம HOD மேடம், பிரின்சிபல் எல்லாரும் லைன்ல இருக்காங்க சார்.
ஓகே சார். பட்டல் சார்.
Good morning sir. I'm Jaishankar from Calcutta sir. Good morning.
Sir, good morning sir.
Yeah, 38 people have entered the waiting room for this meeting or the
ஆமா சார். சார் 54 people are waiting சார். ரிசோர்ஸ் பர்சன்ஸ்க்காக வெயிட் பண்ணிட்டு இருக்கோம் சார். உள்ள வந்த உடனே இவங்க விட்டுருங்க சார். அதை எடுத்து விட்டுறாங்க சார். அதுக்காக தான் வெயிட்டிங் சார். வந்துட்டாரு சார். ட்ரையல் பார்த்துட்டு அவர் சிஸ்டம் ஆஃப் பண்ணி ஆன் பண்றேன்னு போயிருக்காரு சார். அதுக்கு வந்துருவாருங்க சார். சார் சுதா சார் அவர் வெயிட்டிங் ரூம்ல இருக்க போறாரு. வந்து பாத்துருங்க சார். கோஷன்
சார்
கோஷன் வருங்க சார்.
இல்லைங்க சார், ஒன்னும் பேர் வரலைங்க சார்.
வரல. சரிங்க சார். சரி சார். கோஹோஸ்டா நிறைய பேர் கொடுத்துருக்காங்க சார். யார் பார்த்தாலும் கொஞ்சம் டக்குன்னு அவரை அட்மிட் பண்ணிட்டு.
எவ்வளவு பேருக்கு வாங்கி வச்சுக்கிறீங்க இது?
100 பேரு சார். 100 பேரு. எப்படியும் ஒரு 200 பேர் வரைக்கும் அகாமடேட் பண்ணலாங்க சார். ஆனா நமக்கு ரெஸ்பான்சஸ் வந்து 370க்கு மேல கிராஸ் ஆயிடுச்சுங்க சார்.
ஓகே ஓகே.
அதனால யூடியூப் லிங்க் இன்னைக்கு போட்டுட்டு இருக்கோங்க சார். இப்ப யூடியூப்ல லைவ்ல போயிட்டு இருக்குங்க சார்.
ஓகே ஓகே ஓகேங்க.
1200 rupees சார் 1 மந்த்துக்குங்க சார்.
நீங்க என்ன 500 பேருக்கு வாங்கிக்கணும். நீங்க எல்லாம் போயிட்டு 100 பேருக்கு போட்டா என்ன
சார்? நீங்க பணம் கொடுத்தீங்கன்னா நாங்க வாங்க போறோம். சொல்ல கை காசை போட்டு வாங்கிட்டு இருக்கோம் சார்.
ப்ரோக்ராம் ஆரம்பிச்சுட்டா பெரிய லெவல்ல பண்ணிடணும்.
அதே எதிர்பார்க்கலாங்க சார். அது நிறைய நாங்க ஒரு 200 தான் வரும்னு பார்த்தோம். நல்ல ரெஸ்பான்ஸ் சார். Sir, shall we start the meeting, sir? Oh, that's right. Okay, sir. Yes, sir, I am trying. Okay, sir. Fine, sir.
சார் அட்மிட் பண்ண ஆரம்பிக்கலாமா?
இருங்க சார். அவரு அலோவ் பண்ணிட்டு அதுக்கப்புறம் பண்ணிடுவோம். வரங்கிறாரு. சரி, 10 o'clock ஆயிடுச்சு. நீங்க இருங்க, நான் எடுத்து விட்டுறேன் எல்லாத்தையும் சார். அவருக்கு எல்லாரும் உள்ள வந்துருவாங்க. எனேபிள் வெயிட்டிங் ரூம் எடுத்துட்டேங்க சார். இப்ப எல்லாரும் வந்துருவாங்க சார்.
சரிங்க சார்.
மேடம் நம்ம ஸ்டார்ட் பண்ணிடலாங்க மேடம். அவர் வந்து மேடம் நம்ம சார் ஸ்டார்ட் பண்ணிட்டீங்க மேடம். இனாகிரேஷன் முடிஞ்ச பிறகு அவர் நம்ம சேர்த்துக்கலாங்க மேடம். அச்சோடி மேடம்.
ஓகே சார், ஸ்டார்ட் பண்ணலாம் சார்.
ஸ்டார்ட் பண்ணிடுங்க மேடம். சார் பிரின்சிபல் சார் ரெடிங்களா சார்?
எஸ் சார்.
மேடம் டபிள்யூஎஸ் மேடம் ப்ளீஸ் டேக் ஓவர் த லிங்க் மேடம்.
Good morning and welcome to the webinar Advances in Pure and Applied Chemistry, hosted by the Department of Chemistry of the 180-year-old prestigious Presidency College. Thank you all for taking time out and being here with us today. Now let's start the program with the blessings of Almighty. To begin with, may I now invite Dr. O.R. Devanathan, Principal in Charge, Presidency College, for the Presidential Address.
A very good morning to one and all. Am I audible?
Yes, sir. Yes, sir. You are audible, sir.
Yeah. A very good morning to one and all present here. It is a pleasant morning in as much as we have about 80 participants right now at the time of the inauguration for this webinar conducted by the prestigious Department of Presidency College, Chemistry, which has produced great stalwarts, great minds with a scientific temper. It is only right that we grow with time. It is but proper that we advance our knowledge to the present day trend. And in this context, this particular webinar with the title, with the topic, Advances in Pure Science and Pure and Organic Chemistry, it really would give impetus to the knowledge of those who seek it to the modern times. So I congratulate the Department of Chemistry first for organizing this webinar and specifically for choosing this topic, because we need to be on par with the time. So I hope that the resource persons and their experiences, especially with this particular topic, would throw more light on the participants. Our students and the faculty would definitely be benefited, I hope. I welcome all those resource persons, all those participants, and in this context, I am really delighted to have in our midst Dr. Ravanan, our RJD, our former principal, who is very much here in this webinar right now as a participant. I welcome all. My congratulations on the department, and I pray God that this bears all the fruit that the organizers want to have. Thank you all. Thank you.
Thank you so much, sir. May I now invite Dr. N. Indira Gandhi, Head Department of Chemistry, to deliver the inaugural address.
Ma'am. Madam, actually, madam. Unmute பண்ணனும். Unmute பண்ணிக்கங்க மேடம். HOD மேடம். Yes ma'am. மேடம் நீங்க ஸ்டார்ட் பண்ணலாங்க மேடம். HOD மேடம்.
A very good morning to all. It gives me an immense pleasure to extend a very warm welcome to Regional Joint Director of College and Education, Dr. Ravanan, Chennai region, our principal, resource persons, heads of the departments, professors, research scholars of various colleges in Tamil Nadu for this webinar series on advances in pure and applied chemistry. We welcome the brightest minds in chemistry. They are Professor Dr. A.K. Ghosh, Membrane Development Section, Baba Atomic Research Center, Trombay, Bombay. Professor Dr. Parasuraman Jayasankar, Chief Scientist and Head, CSIR, Indian Institute of Chemistry, ex-Head, NDDP and AUGF, BARCF, Kalpakkam, ex-Head, Separation Technology Section, Desalination Division, BARC, Mumbai. Professor Dr. M. Jagan Mogan, Department of Chemistry, Indian Institute of Technology, Madras, Chennai. Professor Dr. Anil Vital Kule, Professor of Analytical Chemistry, Shivaji University, Kolkapur, Maharashtra. Professor Dr. Murugan Pattaswamy, HRM and Analytics, University of Hyderabad. Professor Dr. R. Nadarajan, Principal Scientist, Organic and Medicinal Chemistry, CSIR, Indian Institute of Chemical Biology, Kolkata. Professor Dr. Swarnalakshmi Chandran, Emeritus Professor from Guru Nanak College, Chennai. The Department of Chemistry was established in 1875. It was one of the oldest natural science departments started in the British region. Since its inception, the department has grown to become a prominent research center in Asia, where many eminent scientists and scholars were shaped. The department was instrumental in manufacturing TNT during World War II. The infamous Amritanjan paint bomb was formulated from our chemistry department. 168 doctorates have been produced so far from our department. An ancient proverb says, if you are planning for a year, sow corns. If you are planning for a decade, plant trees. And if you are planning for a lifetime, educate. Dr. Abdul Kalam said, education is not merely a learning process, but it is necessarily a process of transforming humans into better and efficient individuals. Accordingly, Department of Chemistry is committed to provide knowledge, practical skills, and seeks to mold students into multifaceted personalities capable of facing the challenges in rapidly growing world. Indians possess potential knowledge superpower. In order to realize the potential to the maximum for the teaching and student community, this type of webinar plays a key role in sensitizing and creating an awareness about the recent advances in pure and applied chemistry in the wake of COVID-19 pandemic. Applied chemistry not only provides technologies for applications, but also covers a fundamental aspect of chemistry. Currently, as the human society is more complicated, the research fields of applied chemistry are expanding to the wider range and contribute to the development of new materials. It will make our society sustainable to create clean energy saving methods without destroying the environment, and incurable diseases will be prevented and treated by new medicines and medical technologies. I have to extend my sincere thanks to our principal who motivated us in organizing this webinar. We are also thankful to our resource persons for allocating some time of their busy schedule and share their valuable knowledge. I once again welcome you all for this webinar. Thank you.
Thank you, ma'am. May I now invite our Regional Joint Director, Dr. R. Ravanan, to say a few words.
Yeah, good morning to one and all.
Good morning,
Hello?
sir.
Good morning.
Yeah.
Good morning. Good morning,
sir.
Yeah, is it okay?
Yes, sir. Okay, sir. Good morning, sir.
Yeah, good morning to one and all. First of all, I congratulate the head of department of chemistry, the oldest, one of the oldest department and a very famous department in our Presidency College, conducted this webinar. Because of this corona, many improvement occur in the worldwide by conducting many program in through webinar. It's one of the very most advantage now improved in our curriculum. Because earlier we don't know what is webinar, but now it is very important. Any person from anywhere is not is possible to contact and deliver the lecture, and also is possible to attend the program. So I congratulate our principal, Dr. Devanathan, to arranging such a wonderful program and permit to do in chemistry department. And I also congratulate the head of the department, Dr. Indira Gandhi, and the convener of the program, Dr. Muthukumar, and other organizing secretary member for arranging such a wonderful program. I am really happy because in this session, I am also conducted more than some 10 program in this corona period. So really it is benefit to all the research scholar, and definitely this program will help to all research scholar and faculty. And also it is the one of the milestone in the Department of Chemistry and arranged by Dr. Muthukumar, really one of the great scientists in this department. So I thank to all the members of the Department of Chemistry and principal and faculties once again to thanks and give me this opportunity to talk with anyone, because after long time I saw many faces through this webinar program. I'm really thanks to all the organizer and thank you one and all.
Thank you, sir.
Thank you, sir, for your kind words of appreciation. Thank you. The presentation is about to start now. Before we start, just a little housekeeping. Dear participants, your active participation is important throughout the session. Right now, we have everyone muted just to avoid the background noises. But throughout the participation, we'll be managing the chat functionality. If you have any questions during the presentation, please type them in the chat box. We will be running a question answer session at the end of each session. You can raise your hand to ask questions so that we can unmute your line. Also, one more request. Please type your name and designation in the chat box during every session to help us to provide the e-certificate. Thank you.
Next. Oh, sorry, Gosha. Please invite Gosha. Now we will turn the time over to our speaker, Dr. A.K. Ghosh.
Okay, good morning, one and all.
A very few words about Dr. A.K. Ghosh. He is a scientific officer, Membrane Development Section, Chemical Engineering Group, BART, Mumbai. After his post-graduation from IIT Kharagpur, he completed his doctorate from Mumbai University and postdoctoral fellow from University of California, USA. He is a recipient of many awards and recognition. Few of them are Nina Saxena Excellence in Technology Award from IIT Kharagpur, Made in India Award by Indians Desalination Association, Chancellor's Award for Nomination for Exceptional Accomplishments in Postdoctoral Research. He has more than 100 publications in journals, books, scientific reports, conference proceedings, and has more than 3,300 citations in journal publication. He also has one US patent and one international patent. To his credit, he has developed the formulation for single-step TFC seawater reverse osmosis membrane for the first time in India. We are so honored to have him with us today, and I now invite him for the presentation on the topic, membranes for chemists. Please, sir.
Thank you so much, madam, for your kind words. I don't know how much I deserve what you have read out about me. In any case, good morning to one and all. First of all, I thanks to organizers for giving me this opportunity. And of course, to Dr. Prabhakar sir, he has introduced me and he asked me if I can give the webinar. So I think for now, sitting in the room and giving this talk is not a problem at all. And let me tell you very frankly that Chennai is very special city to me. This is in the sense that whether it is IIT, Madras, or it is NIOT, or maybe in many places, I feel some more comfortability, and I get some more inspiration to talk in any venue in Chennai, because interactive session with student and all these people I always enjoy. So I think in one here also, just that's why I have chosen one such topic, which will be mostly, I think, useful for the bachelor or master students, and mostly I think it will be something like some interactive session rather than a professional talk. So as I understood that whatever these participants are there, I think most of them are either research scholar or maybe some master student. Am I right? Yeah. So
PG students and research scholars.
Yes, yes. So accordingly, just I will just deliver my talk in such a way that it will be in a very interactive way, and it will be mostly benefited to them rather than I have not make it for the expert of the membranes. So now, shall I proceed for the presentation?
Yes, sir. Please, sir.
Yeah, sure. Just a minute.
Sir,
Yeah, is it visible?
Yes, it's visible, sir.
Okay, shall I proceed?
Yes, sir. Yes, sir. You can proceed.
Yeah,
Okay. Fine. Okay, then as you see, I have like this, that membranes for chemist. So I hope it is not like that only chemist can contribute for the membrane research. It can be others also, but where chemist's role is mainly important, that I will highlight. And you can see from the screen picture itself, there are some pictures of the membrane processes. So let me just proceed. Concept of membrane. If we can just little bit go back to our school days, all of us, we know that there are some natural phenomena is happening in the nature that everybody knows. For that, you need not be a layman person. You need not be a literate person, and layman person also knows. Suppose one such a small that natural phenomena, if we'll put this dry fruit or seed kept in water, or maybe some just example of one animal like sweet water. In first case, it is get soiled, and in second case, it will get die because the water from the body will get out to the environment, salt water, so it gets shrink. For students, I know everybody knows why this phenomena happens. Why this phenomena happens? Because water is getting inside the dry seed in first case, and in second case, water is coming out from the body. So little bit inside, if we want to see, we'll see in first case, it is happening through the plant cell, and in second case, it is happening through the animal cell. Can any student can guess that what is the cell wall of plant cell is made up of? Can I just get some feedback?
Please unmute yourself and answer the question, students. Participants, please unmute yourself and
Cellulose.
It is cellulose. Okay. And what about the animal cell membrane? Okay, I think you are right. I have also thought so. That's why I have written it is cellulose. What about the animal cell?
Phospholipids.
It is phospholipid, or it may be it is in the better version protein. It is PLP layer. Fine.
Okay.
So what is protein, by the way? What is protein, by the way? Protein is the polymer of amino acids. Means some sort of polyamide type of polymers, right? So from nature, you can see one is like some cellulosic thing, another is just like some protein or some polyamide type of things. So in later of this presentation, you will find it is so beautiful that nature has given us sense that what are the polymer materials we should target to make this osmosis type of membrane. So little bit very fundamental things like osmosis we all know. So suppose two compartment is there and we are putting a membrane. In one side, suppose some low concentration salt water is there and another side it's high concentration. What will happen with time? What will happen with time? I think this will. I think you all will agree that low concentration will get concentrated and its volume will decrease and water will go to the other side and it will get diluted till what time? Till what time? Till the concentration of both sides remains same. When it will be same, then this phenomena will stop. It is normal osmosis. Suppose in high concentration side itself, if I will put some pressure, what will happen? Normal osmosis will stop, definitely, and the water's flow direction will be reversed. So what is this P? Whatever this P I have just shown is pressure P. How much should be this P so that this water from the other side will just flow to the another side? What should be the how much pressure we have to apply? Can anyone tell? Can anyone tell that how much should be this pressure so that the direction of flow will be reversed?
Greater than osmotic pressure.
Yes, this osmotic pressure, it will be greater than. So first phenomena, we call it a normal osmosis, or in recently people have used the word forward osmosis. And the second one, it is a reverse osmosis. So what is the reverse osmosis? Is it the reverse of the osmosis? See, this terminology was used as reverse osmosis. Is it a reverse of osmosis? No, it is not the reverse of osmosis. It is osmosis, but taking place in the reverse direction. So in two cases, in a small, if we call FO and RO, in FO, this delta P, whatever applied pressure is 0, it is a natural phenomena. But when it is RO, your P should be greater than the osmotic pressure. Now, for the chemist, how we defined the membrane based on the first two slides. In a very, very simple language, we can tell that membrane is a semi-permeable barrier which allows preferential transport of one component from the mixture across the barrier. And if you can see this picture, the feed side means what? The side which we want to make separate. Component from the side we want to separate it. It is called feed side.
Sir, your voice is cracking. Sorry, sir.
It will contain many things. Box. Then in other side, both water and fluid can passage. Hello, yes. Hello.
Sir, your voice is cracking. In between, your voice cracked, sir.
Okay.
We were unable to hear.
Yeah. Sir, please proceed, sir. Please proceed, sir. It's okay, yes. Sir.
Okay.
Participant, please suggest.
Okay. Can you hear me?
Yes, sir. Yes, sir.
Yes, sir.
Okay. So from this slide, you can see that this phenomena already I have explained. Only one term I want to introduce here. I call it flux. How much water? Basically, my intention is I want only water should pass through the other side here, but minimum solute. So this flux, how much water is going per unit time is called flux. So how this flux, it is just a chemist can understand easily that when we want to calculate the flux, what are the terminology we will use? One definitely is diffusivity, because it should diffuse both. One is solubility, how much it gets soluble. That means if we assume membrane as a black box, so first we can assume that both water and solute it can dissolve, and one component is going force, and of course, as it is a barrier, they are inversely proportional to the resistance. Next, why separating by membrane? Why membrane is so special? Again, I think all chemists or chemical engineers or whoever separation chemist, I will rather tell that they can give the answer of this question. Why? By membrane. That means what membrane is doing in the separation, some other process also can do. Can you just tell me few other process other than membrane which can used for the separation application? Just you tell me one. Anyone can tell me. Other than membrane, can you give me another separation process name? Hello? 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 I am audible?
Yes, sir. Audible, sir.
Okay. Okay, fine. Definitely all of us, we know that one is chemical addition. We add some chemical to just purify the water. But as you know, in many cases, the concentration of that particular chemical and residence time, how much we kept, it is very, very important. If not properly maintained, your efficiency become very poor. Then it is again another very close method, relatively slow process, and it get exhausted with time. So with time you need to regenerate it. Same thing with ion exchange. Ion exchange, definitely it is excellent method for removing the ions, but need not be that our feed or contaminated water will contain only ions. It can be separate other organics, bioorganisms, and all these things that will not, so that will not cannot be separated by the ion exchange. And then of course distillation and evaporation, where you will get very, very ultra fine water. But as phase separation takes place, first your water will get to the vapor and then it get condensed. So it will be expensive and higher energy incentive. Then definitely now time has come, we have to see what are the merits for the membrane process over what four others we have told. All these things you need not be very worried about this thing. Only this much I can tell out of this. Membrane, there is a two very unique plus point. One is it is just a physical barrier, nothing else. Just a physical barrier. You have to manipulate the membrane in such a way that from your feet only the specific component can pass, nothing else. And second huge plus point is it is modular in nature. Suppose I want to put one membrane devices for my home where only 3 or 4 people are there. It's a small unit. Same thing for the community level or for a plant level. All chemistry, everything will remain same. I will just put number of unit more. That means membrane has a huge advantage. It's modular in nature. But there are some demerits also, where a chemist can play very, very important role. One is called membrane fouling. Membrane fouling means with time you will get that performance of your membrane is getting deteriorated because of some reasons, whatever it may be. But as a chemist, you will come to know in after 3-4 slides what are the material we are using for the membrane. So as a chemist, you can think of, I can make the fouling resistant membrane itself. So a fouling resistant membrane development is one of the very, very attractive topic. It is timely topic for any chemist. Then we called sometime low membrane life. In most of the cases, the user don't follow the pretreatment and other safe operation procedure, whatever given by the membrane manufacturer. But if you follow, definitely membrane life can be. Many times we called. Suppose, for example, I have several ions like sodium, chloride, sulfate, calcium, magnesium, and all these things. Sometimes what we need is, I want to only separate sodium and chloride, not the sulfate or calcium. That means selectivity, some selected species. Here, maybe common membrane. I will use again the same term. Common membrane cannot be used. You have to have a specialized membrane. Why I make these two items green? That fouling resistant membrane development and novel tune adsorptive membrane. Why these two I make green? Because a chemist can participate in these two in most than any other discipline people. So just be ready for these two. And then steps involved in membrane development. Now slowly we will just going to the what we have to do to make all such type of membranes, different type of membrane for the different applications. So selection of raw materials obviously first, it can be polymer, it can be something else also. Then preparation of this membrane, assembling of once, even if you have the membrane, unless you will assemble in the some module form, you cannot use it. And last, of course, its application. The first two, selection of raw materials and preparation of membrane from selected polymer. I will just mostly concentrate because these two are exclusively chemist's job, and the other two, some engineering is necessary. And of course, the application and this thing will be just discussed by Dr. Prabhakar sir in the afternoon session. So selection means some polymer. How we have just plenty of things in the nature. Out of that, only few polymers can be used. That we have to know what are those. Some thermodynamic parameters are considered. Then how to make the membrane from the selected polymers. If once I just select the polymer, how to make it, modular form and application. So very quickly I will go list of some commercially successful membrane processes. I will repeat it again. For here, just you know, if it is pressure driven, if I put the pressure, these are called some RONAPO. It's called membrane distillation. Then osmotic driven forward osmosis, very second slide, what I was explained, that can be make in a big scale in a actual process, we call forward osmosis. Then let's see a very simple one. How pressure driven membrane operation principle work. Some tangential flow is there. Many things are there in the feed. I want only one component. So what is the parameters? I will just define to explain how this membrane is good or bad. There are two. One is called selectivity, another is called permeability. Selectivity, obviously, I have explained just one slide before, that out of many components, how it can separate only one. And permeability, how much flux, whatever flux in second, third slide I have explained, that is called permeability also. Means how much is the water coming out of this membrane at unit time. So pressure driven membrane processes, this is one. Whatever I have just, you just don't bother about the second column for now and fourth column. Only pore size and pressure you can see now, because this thing we will discuss a little bit later. First is called RO reverse osmosis. You all are familiar, I feel, because mostly in Chennai, in household, whatever this water purification people are doing, it is very reverse osmosis. Then very close to that one is called nanofiltration, where it is basically separates univalence from multivalence. Ultrafiltration and microfiltration, these are size exclusive membrane processes, and mostly UF is for colloidal matters. So accordingly, you can see the pore sizes. It is RO and NF, it is very close. Accordingly, you can see here the pressure. Pressure also in bar, accordingly as pore size, it is just reverse. It is bigger pore size, smaller pressure. And here important is RO. You can see this range is huge, 10 to 60, because RO has two type of RO we told. One is called brackish water RO and one is seawater RO. Because extreme one, that's 60, seawater, because seawater has osmotic pressure, very, very high, like 27 bar pressure. So as in principle we saw, to get water in the reverse direction, we have to use excess of the osmotic pressure. That's why this pressure is so high. But normal municipality water is coming, whatever is coming, or from surface water, river water, they are under the brackish water where this pressure is 10 bar or sometime it less also. Ions, and this two UF is for colloid and microfiltration is for suspended one. So next is selectivity and permeability. These two property of the membrane, it's depend on what? It's governed by obviously membrane material. If you change the material, your this both selectivity, it is quite obvious. Then membrane morphology. Morphology means you can naked eye, you can see. If you see this membrane, it's just a piece of paper, or maybe if it is a hollow fiber or capillary form, it is like a thread. But in true sense, in molecular level, if we will see, you will see that its surface is not like that. Something else. I will just show a few pictures to you. Then the driving force. What is the driving force I am using? It need not be pressure always. If it is pressure, then all the pressure-driven membrane processes we use mostly like a dialysis. You know, this dialysis of the patient people do in the hospitals and all these things. Dialysis is there. Then forward osmosis, these are concentration gradient. Electrodialysis, it is electric and potential gradient. So depending on the driving force, this can be different also. So next, I think we'll mostly concentrate first on the pressure-driven membranes like microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. So this is a list of polymer. I think all chemists will understand that what are the different organic polymers used for this type of membrane preparation. This is just simply a list. You need not too much bother about it. You can get everywhere it is, but some common. Just go to the first two in the list. Why I have shown the first slide, some natural phenomena of seed soiling and fishes. Because of this, you can see this list is dominated by first two. One is cellulose acetate and another is Nomex type of polyamide. And very very happy to tell you that first this synthetic first laboratory membrane which is successful oil sorry, based on cellulose acetate type, and name of one of our Indian scientist, basically he is from again Chennai, his name is there. In 1960 he has first made the asymmetric cellulose acetate membrane. Anybody knows his name? He is Dr. Sarirajan, and he has done from the University of California with another scientist, Sidney Loeb. And these two still today in 2020 also, when we are thinking for any forward osmosis or reverse osmosis membrane, first we think about these two polymers, cellulose acetate and polyamide. Next, first it has gone, I told, it is organic. There are some inorganic material as well. This is the list. These are some ceramic materials like alumina, titanium, zirconia, or maybe metallic membranes are also coming nowadays to mostly for the gas separation. Then carbon membranes, glass membranes, and zeolites. Then with time, some people thought that particularly for fouling resistant membrane, maybe organic polymeric membrane is also not that good. Inorganic polymeric membrane also not that good, because both have their disadvantages. So what people are telling that, can we make the mixed matrix membrane? Mixed matrix means organic inorganic composite type. So this is the list where there are plenty. I have just given some representative ones where fillers means inorganic part, some silica or alumina, iron oxide, some metal or metal oxide, plus nowadays two more. This is geo. It is now people are very interested in this GeoH, graphene oxide. Another such thing is carbon nanotube CNT. So if you take this type of filler in a common polymers like polyether sulfone, again cellulose acetate or PVC, this type of polymer you blend it, it is called mixed matrix membrane. Next is structure. First, we know the materials from where this membrane can be made. Now, the structure can be it can be isotropic, means homogeneous membrane, non-porous, some electric charge. Can you tell me how a non-porous membrane can be? I think for the students, they will be very curious. Yes, sir, how non-porous membrane will work? There is no pores. I think phase inverse. Now I think it's time we'll go. I think now for this non-porous membrane, I think this one I am just giving to you. You should think, and then you can tell that how this non-porous membrane can also be used. Next is straight away I will go to some preparation of membrane. How to make the membrane by how we are making. We took some support. It is non-woven fabric. It is non-woven fabric means I have a polymer. Polymer, but that polymer, how will put it in the support? It means hello. Can you hear me?
Yes, sir. Yes, sir. You can proceed.
Okay, because here screen it is coming that it is not connected. Okay.
You can proceed, sir.
So just to make the membrane, I have to make over a support just to give the mechanical some strength, because basically membranes you just it is a very thin 40 to 50 micron. So better over 40 to 50, this 40 to 50 micron, I can just give the coating over a fabric. So just we have first take one non-woven fabric. It is generally made up of polyester of around say 90 to 100. Then we have a polymer solution. I have a solid polymer, but I can't make membrane out of that. First, I have to dissolve it in a suitable solvent. In our terminology, we call that it is casting solution. Casting solution means polymer plus some solvent. So this is typically one polysulfone polymer is there. I have added in a form. Once this solution is formed, we have to spread. Sorry, we have to spread over this fabric. Then immediately we should immerse into the water. Then what will happen? This polymer, it is insoluble in water, but whatever solvent is there, it is soluble. So from here in the water, this diffusion of solvent will take place from membrane to the water gelling bath, and with non-solvent exchange, some pore formation will take place. In true sense, if you will see, it will look like this. From surface, where this solvent and additives are leaching out, some water goes there and it makes foam. And as I was telling, apparently what we feel is a membrane surface will be a very smooth one, and it can be look like a paper. But if we will do some atomic force microscopic picture of this surface, you can see it is look like this. It is 3D picture of the same membrane, whichever membrane I make. I am just giving for your information. It has some roughness, some average roughness of say 5 to 10 nanometer or so. Then next is machine. How I am just implementing in the machine. I have to take the fabric, roll over here. Some rollers are there. Through some roller it will come for gel tank, means here water is there. It is get precipitated. Then to make it is completely solvent free, we have to range it some tank and it will go to the roll. And this is typical one casting machines picture. Then another is, suppose I don't want to get it into the sheet form. I want to make it in the hollow fiber or capillary form. I have to make such type of arrangement where we have to make a spinnerette. Spinnerette means from inside, one side it is dope is going and another side some bore liquid, so that inside some hole will come. Sorry. Yeah. So from doped solution and bore, this type of thread you can see here. Some thread is coming. So these are some hollow fiber. Next is today's RO membrane. Today's RO membrane, that is called thin film composite. What people thought that in normal membrane, if top layer I can give another coating of very thin, it will be called thin film composite, where it is a composite of two polymers, so that I can manipulate the property of both the layers. So first I have to take the first membrane, whatever I make 2 slides back, then I have to put it some amine solution, some monomer. I think chemists all will understand this. I want to make polyamide. So polyamide can be made from the amine and acid chloride. So first I will dip this membrane in amine solution. I have to squeeze it over the surface to access amine. Then I will put it in the acid chloride, do some heating, then another coating will come. And you can see here, this top surface will be typically looks like this. It cannot be look like some distinct pores, but rather it will be some noodles type of things, noodles type of thing. And if I will see again the AFM, you see here this roughness is much more. So in thin film composite prepared by interfacial polymerization, this typical this roughness will be in the around of say 40-50 nanometer in compared to the normal asymmetric membrane of 10 nanometers. So TFC membrane by interfacial polymerization, if I want to make in the machine, again the support role I will take, first aqueous amine, then organic acid chloride, then rinse, some oven drying, and I will get the membrane. And this is the schematic of a small machine. Then trackage membrane. This is very interesting. Here all pores, because in other two you will not get the pore uniformity properly because they are actually some pore size distribution you will get. So if I have some reactor or accelerator facility where I can generate the same energy, same size heavy particle, and I will bombard into a non-porous film, it will make some pores. That method is called trackage, because when I am just hitting it, it is making the track, means some bond will get weakened. Then with some strong acid or alkali leaching, if I leach that etched polymer, I will get the distinct pore. And you can see here this same picture. All the pore is having same size. So trackage method is used for the making of uniform pore size membrane, but it is costly because you need the source of generating either Venn diagram type of things or reactor. Next is by sintering, mostly inorganic membranes. Some inorganic powders are there. You do the sintering. What is sintering? You have to heat the powder to very close to its melting point, then put pressure. You hit it, then it get fused like this. So basically pores is coming from this interstices. Next CM images, you will tell what type of membrane these are. You can see here. These are 6 different membrane. One by one we'll see. First one, in surface pores are smaller, in bulk it is some voids. This type of membrane we make by casting. Next, here there are 3 layers. This is like void type. This is interface, another layer, and in top some fine layer is there. Just we have discussed that casting and coating means interfacial polymerization. What about this? It is glass, can we make by sintering. Next, this one. This one I have not just, sorry. Just a minute. Yeah. This one we have explained, this also, you know, this one. This is simple stretching, means where this polymer are some very flexible polymer like polyethylene or polypropylene. In the 2 hand you just stretch it. Such type of membrane you will get. Next one, obviously you have seen just one slide before. It is trackaged membrane. All pores are same size. And last, nowadays a new method, it is called lithography. Some example I have given this. Then once your membrane preparation is over, I think we have to make it in the modular form. You have to put it in some module form in spiral or for a sheet membrane, spiral and plate and frame, and tubular and hollow fiber. Then I think 2 more membrane method I will show, and I will close my presentation. Another is, so far we have discussed whatever is the pressure driven membrane processes like microfiltration, ultrafiltration, nanofiltration, reverse osmosis, their membrane preparations and all these things. Another very useful membrane nowadays people are using for fuel cell application. This is one typical fuel cell things. Hydrogen is coming. So here catalyst is there. Hydrogen is getting H++ electron. So now this H+, you have to somehow selectively, not with hydrogen and oxygen mix up, to the other electrode, so that here it will get oxygen and give this. So H+ is generating here. Electron is going through the outer circuit, and H+ through the proton exchange membrane. This is the membrane. This proton exchange membrane you have to design, you have to prepare, so that this determines the efficiency of the fuel cell, oxygen hydrogen fuel cell. And here actually we have kept bulb. If you put this thing in a car's wheel, that car will run. If it is fan, it will give you some fresh. And as a chemist, all of you know, if I have acid and base, if I mix them, it will give salt and water, right? What is the reverse way to make it? I have salt. How can I get acid and base? It's a Herculean task. It's a very, very tough thing. But in membranes, we have a solution. We called it as bipolar membrane. You can see here, this bipolar membrane is basically a sandwich of cation and anion exchange membrane with some binder materials. So what it do it split to cation and anion. So cation is go to one side and anion is go to another side. There, water is get again, water basically, bipolar membrane basically is doing it splitting of water. First, water it is getting splitted to H+ and OH-, because these two you want to get it acid. Normal cation exchange and anion exchange is good enough to give your cation or anion like sodium and chloride or sodium and sulfate to respective electrode. Bipolar membrane role is it split water into H+ and OH-. So this arrangement will be in such a way that H+ can be in one side and OH- should be on another side. And if we will put this cation exchange membrane and anion exchange membrane in such a way that this cation will go to the OH side and anion will go to the H+ side, it will give you acid and base. This is another very interesting membrane process people are using nowadays. I think, and just one example where such type of integrated membranes can be used, whatever membrane we have prepared, like milk concentration in several steps. I think Dr. Prabhakar sir will discuss in the afternoon more details. I think that's all from my side. This is the motivation. If we could produce fresh water from salt water at a low cost, that would indeed be a great service to humanity and would drop any other scientific accomplishment by John Kennedy at way back of 1962. Thank you very much for your kind attention.
Thank you so much, sir, for sparing your valuable time in spite of your hectic schedule and for your excellent presentation. Thank you so much. Now we'll go ahead and take some time for questions.
Sure. Yeah. Please.
Participants, you can raise your hands to ask questions.
Yes, please.
Participants, any questions are there? Sir, Sastri sir, you want to ask any questions, sir?
Please, I have email also. You can ask me through my email also, no problem. But now I will be happy to just give to a few answers.
Sir, Sastri sir, cake line, sir. Sastri sir. Yes, sir. Sastri sir, you can ask the question, sir, but it's not audible, sir. Sastri sir. Sir, Dr. Sastri sir. It's not audible, sir. Cake sir. Sastri sir, you cake line, sir.
Okay, sir. Maybe some problem.
இப்ப கேக்குது சார், இப்ப கேக்குது, கேளுங்க சார்.
Hello.
Yes, sir. Yes, sir.
Yes. I congratulate Dr. A.K. Ko, sir. It is very useful and informative lecture.
Thank you very much, sir.
Sir, kindly tell how the bipolar membrane works out.
Okay. Basically, it's a very newer development. It's a very newer development where actually, you know, now I think you might have heard one membrane. It's very famous. It's called Nephron.
Okay, sir.
Yes, some perforated polymer, and this is basically a sandwich of cation and anion exchange membrane with some other polymer, where when you are just creating the polarity by putting it into the inside two electrodes, the water is getting splitted there to H plus and OH minus. So it is some special membrane. It is not a very common membrane which can be used in that. So basically, the working principle is its surface is such that when it will face the delta E, that electrical gradient from two potential, that water is get splitted to H plus and OH minus. And at the present time, I think very few commercial manufacturer will get, of course, in the abroad only. In India, no company is making bipolar membrane so far.
Okay, sir. Okay, thank you, sir.
Thank you, sir. Thank you, sir.
Okay.
Thank you, sir.
Thank you.
Any more questions are there? Participants, if you have any questions, you can ask. Unmute yourself and ask the questions.
I am Prabhakar.
Yes, sir.
Okay, congratulations, Ghosh.
Thank you, sir. Thank you, sir. Thank you so much, sir.
Now, what is the status of these nanomembranes in India?
Nanomembranes are so far actually, first issue is the quality of proper nanoparticle we are not getting. Because so far worldwide only LG came, they are making the nanocomposite membrane commercially, thin film nanocomposite seawater reverse osmosis. We know the technology, we know the what nanoparticle can be used, but the quality of nanoparticle we are not getting in India so far. So, but all we are at least on the way, because that new one, that graphene oxide GEO, already in our laboratory also we are synthesizing, and we are very close to getting the perfect GEO particles. Once we will get, because we have full phase membrane manufacturing process. I think that once this nanoparticle will be fixed and this nanoparticle will be in the proper specification, to put it in the membrane manufacturing process will not take more time.
Okay.
Yes, sir.
See, one more thing, yesterday when I came across a meeting.
Yes, sir.
There is problem in scaling up from the laboratory size where you have made 80-40, even in the laboratory you have made,
yes,
but
sir.
mass manufacturing scale.
Yes, sir.
How about it?
Hello? Yes, sir.
There are certain problems.
Yes.
Scaling up in a manufacturing scale.
Yes, sir.
What are the problems? What do you think are the problems?
First of all, actually, whenever we are making in the laboratory, it is completely in the static condition. We are just taking a glass plate and making just by casting with casting knife and all these things. Then again for the TFC coating also, but there in the machine it is in the moving conditions. So especially the proper moving means speed of the machine, then the proper tension where this membrane is, because in many of the perfect manufacturers machine also I found this thing very frequently, sir, because other peripheral condition they can maintain, but when it is under the operation in the machines.
Thank you. I know you are. I am sure you are aware of these things.
Yes, sir.
Now, yesterday in the meeting, we decided how to get the good quality membrane on par with imported ones from Indian manufacturers.
I think we'll, sir. Yes, sir. We'll just
You have
very closely we'll discuss with the manufacturer, and it should be the combined effort of all of us. Yes.
because good work has been done, but it has to see the commercial state.
Yes, sir. Yes, sir.
Okay, good. All right, thank you.
Thank you, sir.
Thank you. Any other questions? Okay, thank you so much, sir.
Thank you. Thank you so much.
Thank you. Now let's move on to the next presentation. Our next presentation is on modern NMR spectroscopic technique driving natural products research by Professor Dr. Parasuraman Jaishankar. A few words about him. He has completed his PhD from Jadavpur University and had the rare privilege of working with Nobel laureate Professor Ryoji Noyori of Japan during his postdoctoral research. He is the recipient of many awards and recognition. Few of them are Fulbright for Professional Excellence for the year 2020 to 21 from USA, and the prestigious German Academic Excellence Service Fellowship, RCMS Japanese Fellowship, and CSIR Raman Research Fellowship. During his 30 years of service at CSIR, he has been active in research areas of asymmetric catalysis, synthetic organic chemistry, natural product chemistry, chemical biology, and medicinal chemistry. He has successfully guided 26 PhD scholars, 26 MTech, MPhil, MPharm, and BTech students, 5 research associates, and 2 SERB national PDF scholars. He has authored 3 books and has 106 publications in high-impact journals and more than 1,600 citations in the Science Citation Index. He has also had 13 international patents to his credit. We are so happy to have him with us today, and I now invite him for the presentation. Please, sir.
Good morning. Good morning, ma'am. Thank you very much for your kind introduction.
Good morning, sir.
At the outset, I would like to express my sincere thanks to the principal of my college, I would say. I am the product of Presidency College. I'm very proud to say that the chemistry department from the same very old department where I have completed my MSc. And Dr. Indira Gandhi Madam, head of the department, and Dr. Ravanan sir, our ex-principal and then RJD, my own friend, Dr. Muthukumaran sir, and Jaishankar sir, and other faculty members of chemistry department for giving me this opportunity to come and share a small experience of our research life among postgraduate and research scholars. And of course, I could see some of them are third year of BSc chemistry students also in the participants. So it's a really privilege for me to be in front of all of you. When Dr. Muthukumaran sir told, immediately I jumped actually. It's like, if you get a kind of opportunity from your, from your college, anyway, whatever form it may be, you'll be feeling very happy because it's my college, my department is organizing such an event. It's my responsibility to take it, to accept immediately. I said immediately accepted. I gave him a couple of topics, 2, 3, 4 topics also, and he has chosen this. Okay, sir, this will be useful for the students. So thank you very much, Dr. Muthukumaran sir and the head of the department, ma'am, for giving this opportunity. And with this, my gratitude to my department and the college I would like to start my presentation. This one is a Herculean job because, see, it is not easy to explain everything to the undergraduate and postgraduate students in a manner where we can understand actually. So in that sense, it's a Herculean job. So I believe that I assume that the participants are absolutely have got no idea about NMR. So I will start like that actually. Then I'm going to share how the modern NMR technique, that's a two-dimensional NMR technique we have used to solve elucidate the structure of a complex natural products in our own life. Actually, it's not, instead of taking from the textbook, I thought that I should share how we have arrived at the structure of these molecules, which we have isolated from the medicinal plant. So this is about going to be about my presentation. So just a minute. So can you all see my screen now? Can you see my screen?
Yes, sir. Yes, sir. Yes, sir.
Okay. 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 Thank you. Thank you very much. So the content of my presentation is going to be a small introduction about NMR, and then what is 1D and 2-dimensional NMR, application of 1D and 2-dimensional NMR techniques in elucidating the structure of the natural products in a stepwise manner. So we all know this cartoon is very famous, very familiar to all the participants, I would say, because see, whenever he gets something, like whenever he loses energy, he takes a cup of spinach and then he gets energy actually. So the nutraceuticals, let our food be our medicine. If it is so, then there's no need for the drug or even the anything else actually. So, but we are having some natural gift, like apart from the food as a medicine, we have plants which are actually making lot of chemicals for their own survival. Actually, it's not for you and me. It is making. It is for their own survival. So this is to survive from the insects, from the worm, even to protect from the sunlight, instead of, of course it requires sunlight, but to protect that. So many secondary metabolites are being made by the plant. This left hand side, you can just see, this is the very, yes.
Sorry,
can
sir.
you see?
Sorry,
you
sir,
see?
I'm not,
Please share the screen, sir.
Screen is not
Please
visible.
share the screen, sir.
Dr. Muthukumar, my screen is not visible.
Yes, sir. Here it is. Here it is. Okay, sir.
Yeah, for me also
Sir,
it is visible.
we are able to see your screen, sir.
Yeah,
sir, I think network is there in your place, pa. Participant, yeah, network
Screen is
problem
not
is there.
visible,
Here we have no problem.
Okay.
Screen is not visible, sir. PPT.
PPT
is
not
not
visible.
visible.
Yes, sir. Presentation is not visible.
Yes.
So I'll just
Only
exit and then,
only your image is visible, sir. PPT is not visible.
sir, then you go then switch over. You just click not at the presenter. Don't lock my image. Go to the presenter actually. Just unlock your videos actually. There is an option of locking. Probably you are seeing my video. You are not seeing the presentation because you must have locked it. Just click it actually. Just swipe and then you can just see my presentation also. So is it okay, sir? Can I start?
No, sir. Your PPT
Well,
is not presented, sir.
I see. Okay. Okay. So probably
share screen. Share
yeah. Put the share screen only. 1 minute. Share.
Yes, sir.
Is it visible now?
Yes, sir. Now it is visible, sir.
Yes, sir. Yes, sir.
Now it's
visible.
visible.
Now it's okay.
Okay, I'm sorry. Okay, thank you very much. Because unless otherwise you give me the feedback, it's very difficult to interact with the online mode because of the too much of noise actually, which will disturb the audience as well as the presenter. So now,
sir, if you don't mind, please put your slide from
Beginning?
First itself, beginning itself.
Oh,
Yes,
okay.
yes,
Okay.
yes,
Thank
sir,
you.
yes, sir. Thank you, sir.
So, presentation, actually, the content of my presentation is going to be introduction about NMR and 1D and 2D NMR, and then application of 1D 2D NMR techniques to solve the structure of a complex natural products from our own, our own natural products, which we isolated from the medicinal plants in a stepwise manner. How to approach, if you are having all the details, how to approach in a stepwise manner to solve the problems, solve the structure. So this is what actually I explained to all of you, that the nutraceutical, actually, if our food becomes a medicine, then everything will be nice. Actually, this cartoon is very famous, cartoon, where he gets energy every time he eats the spinach. But nature has clearly given some advantage for the human being to get it from the plant. Actually, see, the plant, they're making a lot of chemicals to safeguard themselves for their own survival, not for humans, not for you and me. It is making, actually, the fruit which we are eating is not meant for me. It's meant for us, because it is protecting the seed from the decay, actually. So this is an antioxidant. Vitamin C is composed of vitamin C. It is not meant for you and me. It is meant for its own survival. It's protecting their own, generation, actually. Fine. So, but we are having a huge number of medicinal, values, medicines which we are isolating from the plant. One of these things is that you can just see that Vinca rosea. Actually, this Vinca rosea on the left hand side is very famous. Our own plant, which has given, which from where we have isolated a huge number of Vinca alkaloids, which are actually being used as anti-cancer drug. With this, there are many number of phytochemicals. They are called the phytochemicals, which we are isolating from the plant, are called the phytochemicals. Number of class alkaloids, organosulfurs, phenolic, carbohydrates, proteins, lipids, flavonoids, etc. But so natural product based drugs is huge, actually. See, the total number of available drugs, only 36% of the new chemical entity, based on new chemical entities, are truly synthetic origin. But most of them, 64% of the existing drugs, molecules, are natural products, inspired molecules. So it is very important to know, to address the problem of the structure, to elucidate the structure in a very satisfactory manner and without any doubt, actually. This is very important, actually. So, see, if you see the first one, the aspirin, left-hand side, 1 minute, I'll just use the pointer. So, the left-hand side, this is the aspirin, which is very simple molecule, which it's not so difficult to elucidate the structure. But you see, the artemisinin on the right-hand side, and then Taxol, anti-cancer, so the complexity increases. And imagine, oh my God, what is this actually? Somebody is pointing out. Oh, okay. So huge. You just see that this is the polythionamides from the sponge, which is isolated from the Thionella sphenoide. This is the polypeptide, actually. Imagine such a big molecule. It's very, very difficult to arrive at the structure, actually. So, but how to resolve such a complex structure? It's a big task, is it not? So, what is to be done? We have a lot of modern analytical techniques which will give us a lot of information about the structure of unknown molecule. Starting from element analysis, melting points, optical rotation value, mass spectrometry will give the molecular weight or mass of the molecule, and infrared spectroscopy will give you the functional group present in the molecule, and then Raman spectroscopy, etc., etc. So the nuclear magnetic resonance spectroscopy, this is very important, actually. How today we are going to talk about how this nuclear magnetic resonance spectroscopy is helpful in resolving the structure of complex molecule. And you see the origin, the genesis of the NMR instrument, you can just see the left-hand side is 1960, which was the 40 megahertz, the instrument which was, which was assembled and being used. And now you can just see that Bruker has come out with the 1000 megahertz ultra-field NMR spectrometer. And at the center of resonance magnetic layer, this is actually France, Lyon in France, which is available. So nuclear magnetic spectroscopy is an incredible powerful tool for characterizing molecule structure. When we submit the molecule drug for the approval of the FDA, but we need to provide the structural characterization also by NMR. Completely, it is very crucial evidence for the structural identity. So, what is the basic principle in which the NMR spectroscopy operates? So, what is NMR? Actually, I don't know if the top one is visible or not actually, because for me it is not visible. Because a lot of other things are. So, what is NMR? So, the properties of, it's talking about the properties of the nucleus, a magnetic field, and resonance. So, nuclear spin, every nuclei has a spinning magnet. It has got a nuclear magnetic moments. Under the nucleus is a magnetic field, as which I told you. It is rotating in a precision under the Larmor frequency. Nuclear Zeeman and Boltzmann distributions. When the nucleus meet the right magnet or radio wave, nuclear magnet resonance occurs. So this tiny magnet will resonance with resonance with the applied magnetic field at the right radio frequency. So what are the properties of the nucleus? As I told you, nuclear spin is the total nuclear angular momentum. It's a quantum number. This is characterized by I, which may be integral of or minus integral or 0. Only nuclei with the spin number I that is equal to not 0 can absorb or emit electromagnetic radiation. These are all some of these a concept actually we need to understand. The magnetic quantum number has values I minus I2, minus I plus 1, and etc. up to plus I. It can be I is equal to 3 by 2, minus 3 by 2, off, minus off, plus off, 3 by 2, etc. Suppose the condition number 1, nucleus with an even mass and even charge, the nucleus spin I is equal to 0. Remember, even mass and even charge. That's it. Even atomic number and atomic weight. You can say that. Even. Then they will not be NMR, nuclear magnetic. I is equal to 0. They will not be active. They will not give you any NMR signal. Carbon 12, oxygen 60, sulfur 32, etc. The nucleus with an even mass and odd charge, integer value I will give you integer value I. So, example H2, that is actually the 2S, that's a deuterium, boron 10, nitrogen 14, they are NMR detectable. But a nucleus, this is very important, nucleus with odd mass, where N is an odd integer, that is, which will definitely be NMR detectable. That's what we are talking. It will have plus or minus off spin. That's what 1H NMR, 1H, 13C, 15N, 39F, 31 phosphorus. So these are all the nuclei or NMR active. So another important thing which we need to know, magnetic moment is, as I told you, is another important parameter for a nuclear. Mu is equal to psi I H divided by 2 pi. What is the I? Spin number, H is the Planck constant. It's a gyromagnetic ratio. Property of this is very important. This is specific to a specific nuclei. So 1H, that's a proton, will have I is equal to off, psi is equal to 267.512 in 10 to the power 6. Tesla inverse, second inverse. 13C, I is equal to 67.264 to the power 10 to the power 6. Tesla inverse, second inverse. N15, same way. So you can just see that. So proton and carbon 13, the two nuclei are the most useful to organic chemists. Both have spin plus or minus off. So we all know that proton is 99% at natural abundance. So carbon 13 is, whereas carbon 13 is 1.1% only at natural abundance. The natural isotope of the carbon is carbon 12. Fine. So this is the a schematic way of the NMR instrument. These two are the magnet and this is the radio frequency supplied. This is the transmitter. This is the tube in which the analyte is present in a specific solvent. That's what we call it as deuterated solvent. If you apply the radio frequency, there you will get this signal. So what are the signals you will get it? So the nuclear spin can be clockwise or anti-clockwise. What is happening? A spinning charge such as the nuclei of 1H or 13C NMR generates magnetic field. This is the basic concept of nuclear magnetic NMR, nuclear magnetic resonance. So this generates a magnetic field. So the magnetic field generated by nucleus of spin plus off is opposite in direction from that generated by nucleus of spin minus off. So it will be clockwise, another will be anti-clockwise, totally. So in nature, these nuclei are oriented in a random fashion, pointing in all different directions. This is the nature. But if you place it in the strong magnetic field, they orient themselves. Some will be along the orientation of the externally applied magnetic field. Some will be opposite actually. That's what actually. So in other words, the lower spin states will be excited to higher spin state. That's what actually. What is the lower spin? The one which is aligning with the applied magnetic field. That's the alpha spin we call it as. The one which is opposing, which is a higher energy state, is the plus all. That's what we call it as a beta spin state. So always, if you can just see that these are all positive. These are all positive. These are all aligning actually. So there is a slight excess of nuclear magnet moments aligned parallel to the applied field actually. So that will be a combination of the applied field and then its own proton, its own actually. So the one which is opposing will have lesser actually. So fine. So if I increase the difference between these two, naturally it is very small actually. Suppose something like that, the two spin state is something like that, 10 million in 10 or 10 million, 10 in 10 million, something like that actually. So that's very small difference. So if there is no difference in the absorptions of the energy level, then there will be, we won't get any peak actually. We'll be getting all the protons, all the carbons will be giving a single peak, which is of no use actually. The small energy difference is sufficient to get the spectrum of the nuclei under a different environment, basically. So it is proportional to the strength of the magnetic field, which we applied, like 300, 400, 500, 600, 800, 1000 megahertz actually. So if the more of the magnetic field, which we increase it actually, so the separation will be more, then the peak separation will be very good actually. That's why resolution will be very good. So as I told you, so forget about this thing, the alpha I already explained to you. The last one, the Larmor frequency refers to the radio frequency needed to flip that precision to the beta position from the alpha. This is what from the lower energy state to the higher energy state. That's what the flipping is happening. We are forcing, like temperature when you apply, so there will be elevated actually. The molecules or the particles will go to the higher energy state. The same way, here also we are applying the frequency, that's called Larmor frequency, to flip this nuclei, flip the lower energy, the beta state from the alpha spin state to beta spin state. So when we flip, this is what actually we need to know. It is given in the frequency, that's a delta E is equal to mu, and Bx I delta E is the radio frequency applied, and mu magnetic moment of a particular nuclei. That Bx is the external magnetic field. The mu depends upon the particular magnetic moment of the particular. As we have already seen the relationship between psi and mu. So I is the spin state of. So obviously with this, so as I told you, the one which will align magnetic field, which will be having the shielded, deshielded, and then one which is opposing actually the direction to the applied magnetic field will be the shielded actually. So it will be shielding. It is shielding what? It produces the electronic environment. See all the protons basically. It's in the nucleus. Nucleus contains proton and neutron. So it is surrounded by the electrons. So what happens? So this is protecting. If more number, if this nuclei, if a proton is surrounded by many number of protons in the molecule, very nearby. So there is a shielding and happening. So that shields the proton from the influence of the shield the protons from the influence of the external magnetic field. So that's what we call as shielding. So this gives rise to the called a term chemical shift. Spectrometers are typically named by frequency, which I explained to you. This is the generic name for the radio frequency to flip a proton under the applied magnetic field of that of the NMR magnet. The higher the frequency the spectrometer means, the higher magnetic field applied to the nuclei. This is induces a strong magnetic field applied to the tiny bar magnet of a nucleus. That means more energy, higher frequency needed to apply to the flip the nuclei. It is the vice versa. What are the informations we'll get from the chemical shift? The different kinds of proton typically come at a different chemical shifts. Shown below a chart where some common kinds of proportions are protons appear in this scale. Generally, most protons appear between 0 and 12. Okay, so if you see here, that's what we call it as a chemical shift in parts per million. Because we use a different spectrometer, so we use we can also draw here at the where the proton is resonating at the frequency also 0 to some 300 megahertz. Actually, you can just see that in the frequency hertz you can try, but that is very difficult one. In order to arrive at the common notation, this is what the chemical shift is expressed in always ppm at delta. So the ppm which I have mentioned is a peak position in hertz, peak position of a particular proton in hertz relative to TMS, tetramethyl selene, and then divided by spectrometer frequency in megahertz. That's a 300 means 300, 400 means 400. So you will get it actually the same. So now we use it in ppm. So the 1H NMR chemical shift in a position scale, this is the in a ppm scale. If you can start from the right to left, 0 to 12, you can see very specifically kinds of the proton, what kind of protons, how many protons are present in the molecule. You'll be able to get a clear-cut information about this. So for methyl hydrogen or CH2, CH, you will get 0 to, it will appear at 0 to 2 ppm. Suppose if it is olefinic or something like that, CH attached to the carbonyl and maybe NH or OH will also appear at this position. Suppose if it's a toluene, CH2, CH2 or CH3 attached to the benzene ring will also between 2 and 3, around 3, and 3 to 4, 5 specific, etc. Olefinic protons will be appearing at below 7. Beyond 7, above, or something like the 6.5, I would say 6.5 to about 8.5 aromatic hydrogens. Beyond that, aldehyde and carboxylic acid, amide, etc. Even the indole NH is also appearing somewhere at around 10 or 11. Okay, so this is very important. One has to understand. The concept is a de-shielding, which I already explained to you. De-shielding means the amount of due to the reduced electron density. That means due electronegativity atoms, and this is what actually. So it is appearing at the lower. That's a downfield. What we call it is a de-shielding downfield, and the higher ppm. What is the anisotropic? Due to the magnetic field generated by pi bonds, anisotropic. I think there is a separate slide for that in order to explain. So fine. The same way, you can also keep. There is a chart for different kinds of carbon will appear in a different position, delta ppm. So that's what we have put it here in the table. You can just see that different kinds of carbon will appear different position. So in order to get the structural information from the 1H NMR spectrum, the position is important, the number of signal, and the intensity. Intensity of the signal indicates the relative amount, how many protons are there in a particular kind of protons. How many protons are there? Is it so spin splitting? This is very important. Splitting gives further information of the neighboring environment for the various hydrogens in the molecules. So if my neighbor carbon has got 1, then I'll be 1 proton. then I'll be split by 1 plus 1. That is n plus 1, 2 signal I'll get, 2 peaks I'll get. That's what is happening here. If I take the this molecule, actually, tribromoether, you can say. So the first CH will appear, that's a CH2 will appear here, will appear as the doublet. This CH2 is because of the CH, hydrogen. This carbon has got only one hydrogen. So n plus 1, it will be split by 2. It will be split by n plus 1, 2. So whereas this one, that CH, will split into 3. That's a triplet. We call it as a doublet and triplet because this CH, the neighbor carbon has got 2 hydrogen, that n plus 1 is equal to triplet. So if these two are coupling, that's what we call it as a resonating or coupling or influencing with each other, then the splitting between the peaks, that's what we call it as a coupling constant, J value. That's what J is expressed in hertz. This has to be having the same J value. Then only you can say that they are neighbors, they are splitting with each other. Otherwise, if the J value is different, you cannot say that they are actually, even though you may have a n number of splitting in the compound in the compounds in the spectrum, but you cannot arrive, they are the neighbors actually. So I think I have explained these things and fantastic. Fine, this is what I already explained to you. You can also ask, if somebody asked me that why the split into triplet, the intensity is not same actually. That is because you see that the left hand side, if it is a if the CH, that's a CH is having a CH2, the CH2 into n plus 1 triplet. So it divides into here alpha alpha. These two protons can be alpha alpha or alpha beta, beta alpha, beta beta. So alpha alpha means it is deshielding. It is deshielded. Here shielded, both the cases off shielded, off deshielded. But here beta beta, that means here shielded. So that means this, that's why you are getting the difference in the peak height. Peak height. The triplet will not be like 3 the same height, or doublet like doublet actually. Triplet will be different. So and so on. You can just see that. So this is the NMR splitting of the pattern. How we can arrange simple mathematics. You don't have to worry. But after quartet, we normally refer as a multiplet actually. If multiplet is that, then we don't have to worry. But how this is actually the intensity is arrived at is, if it is singlet, fine, same. If it is doublet, two peak will be there of having equal height, equal intensity. So the triplet means 1 to 1:2:1 ratio. How we are getting quartet means 1:3:3, 1. Quintet means 1:4:6:4:1. How we are getting the simple one? It's a Pascal equation actually. So so whatever 1 plus 1, 2, and then the first and the last you can put 1, 1. If you add up these two, 1 plus 2, 3, and then 2 plus 1, 3, and then the first and last 1, 1, and then if you add up here 1 plus 3, 4, 3 plus 3, 6, 3 plus 1, 4, and last 1 and 1, and so on. You will get the intensity actually. How intensity, these peaks will be this height, the height will be different actually. So I explained to you, fine. And this is what we saw, that we were talking about the pi electron cloud or ring current actually, which reinforces with the applied magnetic field. That is why it is getting shielded. Aromatic protons typically appearing at 6.5 to between 6.5 and 8.5 ppm. So there is an induced current is less effective than the aromatic hydrogens. That's why in the olefins, of course, there is a deshielding, but it is less compared to the aromatic protons, that is between 4 and 6. But acyl protons, you can see here actually are shielded. That is because the reason is that it is induced current, which is actually shielding the protons from the externally applied fields. That's why it is appearing at delta 1.5 to 3 ppm. So why we use the tetramethylsilane? It's a standard internal standard we use it, because these 4 methyl groups are in the same environment. So they appear at single peak, and we make it as a single peak for integrating for 12 hydrogens basically. So we make it as a 0. So this is used as an internal standard. internal standard is 0. According to that, the position of the hydrogens and the carbons are expressed. So now, having said this thing, as I told you that I consider all of you is that you are novice to the NMR. So probably I explained to you with the basic. Now we'll go to 1D and 2D NMR actually. Applications of NMR in structural elucidation of the natural products. So how we isolate the molecule, how we isolate this is the plant product, plant material. So we use a different solvents to percolate it, we extract this, and then we put it over silica gel. And before that, we do HPLC, thin layer chromatography, to see that how many spots, how far in the particular solvent is getting resolved, all those things. And then silica gel chromatography, we do it and separate them. And one such case, what we found actually, we got almost 4 pure molecules. That's fine. Actually, we run the NMR initially, absolutely all right, all are pure. But when I asked the Rahul, the research scholar, to do the HPLC, each pure compound is giving 2 peaks. So I'm going to talk how these 2 compounds, how the single peak, having same NMR, mass, carbon-13, everything is same, but they are being separated by using HPLC. This is a normal HPLC column. It's not a chiral HPLC column, by the way. So that is what actually our intriguing point. And you can just see that beautifully a separated compound A and B here. And when we run the this LCMS, ESA mass, electrospray ionization technique. So this is the beauty of this one is between the EI. EI will give you molecular ion, parent ion, as I would say, along with the fragmented ions also. But ESI, electrospray ionization technique, is a soft ionization technique by which you can get only the molecular ion only. It's a soft ionization technique actually. So this is always coming in the form of adduct, the sodium, potassium, etc. So you can just see that M plus is 536, M plus Na 23. If I add 23 here, it's going to be 559. So this is true with both the compounds. By the way, we got exactly same mass. But how to solve it? Actually, there are some conventional 1D and 2D NMR experiment which we are going to do it, which we did it actually. We have to, like a tailor, we have to stitch. We have to cut into pieces the molecule and then stitch exactly. Otherwise, it will not look like a shirt actually. If it doesn't stitch in a way, it should be. The whole material after stitching will not be having any shape actually. Is it not? The same way, natural product chemists like tailors has to have a small bits of the synthone or small parts and then join together, make it a structure of the molecule actually. So we can have connection through bonds. That's what we call it as a spin-spin coupling. Homonuclear. Homo means same nuclear. 1D, 2D. In the 2D, 1H cozy. That's what we call it as a cozy. Forget about other things. Cozy. And then usage spin system assignments. So that means spin system means neighbor. How the hydrogens are bonded through bond actually. These assignments can be done. Then comes heteronuclear. That means heteronuclear means hydrogen, carbon. So it can be direct. That's what they detect. 13C NMR. DEPT, head core. We don't talk about head core. We just enough to have a DEPT. Then inverse detect. That's what inverse actually. Inverse detection. What we inverse is carbon, hydrogen, HMQC, all through bond. By the way, all through bond. HMQC, HSQC. We don't talk about HMQC. We talk about HSQC, HMBC, and that's it. And then this is used for assigning heteronuclei connecting spin system. How they are connected. And then connection through space. This is very important. How beautifully we have used, noisy. Actually, why we call it as a noisy, and rosy is also used, but here we have used noisy to connect this structure. Which we use through the space. How they are space. I mean, like if I bring my head has to be very closer, but they are not connected actually. Spatially connected actually. If I take it away, then there won't be any connection between me and my hand, my head actually. Okay. So these informations you can get it from the noise. So in a typical outline of the NMR experiment approach for a complete structural elucidation of unknown molecules, the first thing what we need to do, 1H NMR, then COSY, that's what 1H hydrogen bonded COSY. Then the third step to run the 13C NMR, then DEPT. What is the DEPT? I'll tell you. Then 1H 13C NMR, HSQC, HNBC, and of course we also used noisy. Fine. The step one, first thing was NHNMR. As I told you, you have to run the what we will get from the 1HNMR, 1D NMR. You will get the position of the chemical shift of the each hydrogens present in the molecule, as well as how many hydrogens are present in a particular environment and how they are connected actually. So if I put it here, this is the aliphatic methyl proton. This is our spectrum, aliphatic methyl protons. These are the aliphatic protons. It's CH2, CH protons. Here, this is very specific. Fortunately, actually, there are some standards are available, so very easy to. These are protons from the sugars. We know that actually one important thing is that the anomeric protons. This is the anomeric protons for sugar. Very typically, you will find here. You will find this range, and then aromatic protons. So we have classified the kinds of protons and where it appears, because from this one we got it from the sheet which I already the chart which I already displayed to you. Then comes COSY, HS COSY. The example, two types of HS COSY coupling occurs. On the left hand side, this is an nuclear side. You can just see that it's for explanation purpose. I put it here. The 3-bond short range coupling between protons 7. This is the 3-bond 1, 2, and 3. 1, 2, and 3. Hydrogen, carbon, hydrogen. 3-bond coupling. The short range coupling. This is visible, red. And then 4-bond long range coupling between the hydrogen, hydrogen 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So long range 4-bond coupling, 3 are 4-bond coupling, and long and short range 3-bond coupling. This is you will get this information you will get from the COSY, correlation spectroscopy actually. COSY is a correlation spectroscopy. So this is the actual COSY of our molecule compound A, and you can see that the connectivity between the protons on the basis of the geminal and the vicinal coupling. By the way, geminal means the same carbon. If carbon has got 2, they will couple. That's what geminal, same. Vicinal means with a neighbor. Okay. So this is what we call it as a diagonal peak. Diagonal peak. So they are called diagonal, and these are all called cross peaks. Cross peaks. Up and below the diagonal peaks are cross peaks. So if you want to see the connection, actually you will be able to see there a lot of boxes actually. If you make the boxes, you can just see that the above and the below, they are connected. Suppose if I see this hydrogen is having connection with this hydrogen, okay, as well as this hydrogen. So like that, you can beautifully have n number of tables. You can see that you can stitch this hydrogen is connected to this hydrogen, this hydrogen. Next, the question comes, okay, how many carbons are there? The third step is how many carbons, what kind of carbons actually. If the carbon, when we get the information about the carbon, and then we have to link whether this carbon is attached to which hydrogen atom. If they are attached, what is the neighbor actually? So we have to stitch like that. So this is the NMR spectrum of 13C NMR spectrum of our compound, and you can just see the total number of peaks. Mostly you will get it actually 26. So you can say that 26 carbon, but it's not always true. If the same environment carbon will appear at the same position, that you have to see the height. So, so here you can just see that the 5 almost 10 to 35 region you will find 10 to 13 to 35 region you will find CH3 hydrogens, methyl carbons are there. So between 64, 62 to 83 you will find CH2 carbon. And then there is one more carbon, is 104.04. This is for, because we know, so typically for anomeric carbon actually, and the sugar. So then comes beyond 115 to 144 is CH carbon, and then tetrasubstituted carbon 199.76. This is the tetrasubstituted, means it is carbonyl carbon, actually carbonyl carbon. So how do we know, sir? This is very difficult. How do we know that which type of carbon it is belonging? We are also having a beautiful experiment called actually, step 4. This is the DEPT, which I was talking about. This one, distortionless enhancement of polarization transfer. Experiment help assign carbon peaks by determining the number of protons attached to each carbon. So, in other words, it will tell me which how many hydrogens are attached to which in each carbon actually. So, if we do 135 DEP to 135, that's angle of shows CH and CH3 carbons as positive peaks. That means above the plane it will appear, and then CH2 carbons will be negative peaks. Okay, carbons with no protons are not visible at all. That means tetrasubstituted carbon will disappear. You can just see somebody is actually can somebody remove these lines? Somebody is trying to control. Anyway, so somebody is trying to control. Okay, so here depth to 135, you can just see that these are all CH2 carbons. 1, 2, 3, 4, 5. There are six CH2 carbons. There is one. This is a methyl carbon. Okay, this is what actually. So here CH3 is up and CH carbon. CH3, because this is the range at 13 will be CH3 carbon, and then rest and all CH carbons. CH2 carbons will be below the plane. And then if you do the DEPT 90, you will get only carbons. Rest on, you will simply all other carbons will disappear except CH carbon. Carbon having only one hydrogen will be visible. From this, you can just see that how many carbons, how many? 1 CH3, 6 CH2 carbons, 12 CH carbons, 1 tetrasubstitute, 6 tetrasubstituted carbons are there. Sorry, 6 tetrasubstituted carbons, which includes 1 carbonyl carbon also. So, aliphatic, same way, sugar, anomeric signal, which I told you 110, around 110, very typical, 104, I'm sorry, 104, very typical. And then for aromatic carbons, and then aliphatic carbonyl carbon will appear at 199, around close to 200. So, the next step will be which carbon is bonded to which hydrogen. This is the HSQC. That's what we call it as a hydrogen 13 proton 13C heteronuclear single quantum coherent spectroscopy. Shows which hydrogens are directly attached to which carbon atoms. Fine, that's it. Nothing. It's very simple and a very beautiful one. Rest you will not get it actually. So in the one dimension, you will find this. In both the dimensions are one dimension. You will find the proton NMR. The other dimension you will find carbon 13 NMR. You can just see that here, and beautifully it will be having a link. Which hydrogen is bonded to which carbon. If I enhance this one, so you can just see that here 4.54 is bonded to something like the 83.6, and 4.52 is also bonded to 106, 103. This is the anomeric, which I was talking about this anomeric carbon. But you just see that this one 83.6. So in the same way, similar way, 3.39, the proton is bonded to carbon, which is attached to, which is appearing at 62. You can also see that this hydrogen is also bonded to this carbon. So meaning that two different hydrogens are bonded to the same carbon. That means though they are attached to the same carbon, but they are not under the same environment. Okay. After that, once you make the carbon hydrogen correlations, then you have to make the bond. You have to make the chart. There are n number of tables we have to make it. Actually, so now it's beautifully we can arrange it. So after that, the next 2D NMR comes the HMBC, which I told you here also. It is also through bond, hydrogen carbon hetero. That's what it's called, heteronuclear hydrogen. There we saw hydrogen carbon. Here also it's heteronuclear hydrogen carbon heteronuclear multiple bond correlation spectroscopy. Shows the correlation between proton and carbon that are separated by multiple bonds. Here you can just see that actually here But here, this hydrogen, that's a carbon, hydrogen number 4 is bonded to C2, carbon 2, and then 3. 1, 2, 3. 1, 2, 3 bond. As well as 1, 2, 3. This carbonyl. In fact, this hydrogen. Finish, sir. I'll take only. Sir, can I take only 5 minutes? Muthukuman, sir. Okay, fine. So you can just see that actually. So this hydrogen 4 will be having correlation with the carbonyl also. So beautifully, you can just see that 3 bond, 4 bond. But 3 bond is very visible, and 4 bond is bit weak. So you will not be able to get it actually. So like that, you will find beautifully these hydrogens. Here, one dimension, you will find that carbon, the y-axis and the x-axis, you will find that hydrogens are put. And this, suppose if I take carbon hydrogen number 11, which is bonded to carbon number 8, carbon number 12, carbon number 9, carbon number 11. So this what? So it is, you can easily identify the neighboring carbon, neighboring hydrogen by using HMBC. This is very important, bit complicated, but it's very important tool to arrive at the structure. So come to our case, what happens? The same way when we put, as I already explained to you. So the important thing which I would like to, you'll find a lot of correlations, but only I would like to point out here, 69, this carbon is having 69 carbon, 1, 2, 1 with the H3 and 1, 2, 3, but with the 1.48 as well as 2 bond with the, this hydrogen, this carbon, hydrogen. 1, 2, 1, 2, 3, 1, 2, 3. Okay, so you will find these informations actually 4.54, 1.455, 1.42 are multiple are correlated to each other. So you have to make the list. As I told you, the probable structure is, there are many many structural informations you can get it. Alternative structures predicted now. So this is actually more or less the structure of the compound, but actually the problem, this one is the sugar D-glucopyranose form. The chiral centers of all this sugar is completely fixed, so we don't have to worry. But there are only 2 chiral centers. In fact, here also this is also fixed. This is actually beta. This is anomeric OH, beta D-glucose, beta. This is also fixed. But the problem is here actually. That means this is the chiral center, newly created chiral center. But whether this O-butyl is above the plane or below the plane, this is the difficult part. How to solve it? The stereochemistry of the compound A, how to solve it? So, as I told you, in order to do that, Noisy has helped us to solve this puzzle. So, how we have solved? So, we found 3.83, that's a Noisy through the space, as I told you, as I explained to you, through the space, hydrogen through the space, actually, how they are related, how they are in the close proximity. So, 3.83 hydrogens is close, having a proximity with the 4.54 as well as 4.52. That means this is the 4.42 hydrogen, which is in the alpha orientation, as well. This is having a spatially close proximity with this 3.83, as well as this hydrogen, which is appearing at 4.54 delta, having close proximity with these two 3.83. That means these 3 hydrogens are alpha. So we have solved the issue. This fine. These 3 here also alpha. Forgot to mention all these things are now we fix the stereochemistry. There is no problem. Compound A is done. Then compound B. What is that? As I told you, exactly the same mass. Everything is same. It's very peculiar. The compound A, and there are very slight difference in the proton NMR, identical 13C NMR. I'm not going to explain. Identical COSY, identical HSQC, identical HMBC. Everything is same. Then there was what is the problem? What is the difference? So the difference is what we found, the Noisy experiment, because the same compound, this is the same compound. What we found, the Noisy experiment, what we found, the proton which is appearing at 4.52 is having relationship with a 3.83. You can just 4.52, 3.83. Whereas 4.50, this hydrogen is not at all having relationship with this one. This is not in the close proximity with the 3.83, these hydrogens. So that means these two are opposite. This we already fixed. This is fixed. It's a beta. These two are opposite. We got it? Now we fixed it actually. So in net, you can just see that the two compounds which we isolated from the plant is diastereomers, two diastereomers. Like that, this is very, very, very interesting. Usually, the plant kingdom are very specific actually. They give usually only one type of molecule with enantiomeric rich. Normally, they don't give the diastereomeric mixture. Two possibility actually. This is very, we are very fortunate to have this plant, and we have identified like this four more pairs of diastereomeric. And what is the business of this plant is that actually they showed excellent inhibitory activity against Leishmania donemani topoisomerase, dose depending manner. What is a topoisomerase? It's a parasitic disease. Okay, that much is sufficient actually, which is caused by the sandfly bite. People who are living in the seashore near to the forest, and actually it is called Poorman disease. Leishmania donemani is a Poorman disease. Basically, these people are affected, and one of our area is also to develop the effective and cheap drug to treat the Leishmania donemani, and we have these molecules having a excellent topoisomerase 1B activity. And topoisomerase is something like that. Actually, it is very important enzyme, basically, which cleaves the double helix of the DNA. Nick and rewind, and then join. Nick, rewind, and join the supercoiled DNA. That is how this is very important one for the cell divisions and propagation of the parasite. This is stopped. So obviously, so this is the importance of this one. So with this, actually, I would like to thank my group, and as well as my student, research scholar who has submitted his PhD thesis, Rahul Gajpi, and he has done the hard work of this, the complete separation and getting all this done, and then 2D NMR, 1D NMR, then getting it done, everything. And with this, I've come to the conclusion of my talk. And thank you very much for your patient attention. I would be very happy to take a couple of questions. Thank you.
A great presentation, sir, from the alumnus of Chemistry Department of Presidency College.
Thank you, ma'am.
For the useful and informative presentation. Thank you so much. Now it's time for questions. Participants, you can ask your questions, unmuting your line. Participants, if you have any questions, please ask.
So I would also, since let them also think actually.
Sir, in the chat box, a few participants asked some questions, sir.
I'm not able to see the chat box. Maybe I.
Sir, yes, sir. I will read that one, sir.
Please, sir. Please.
Why these are in blue? Why not in red? These dots in Cauchy spectra. Why CH2 shifted to 34? Parthiban Devendra.
In the which one, sir?
Sir, why these and in that slide? Why these are in blue and why not in red? These dots in Cauchy spectra. Why CH2 why CH2 shifted to 34?
Okay, Cauchy, no? Cauchy, 1 minute. I'm just trying to get this Cauchy.
Yes, sir.
Time. Okay. You mean is it this one, sir?
I think so, sir. If the participant is there, please ask the question.
Yeah, you can unmute and then ask me.
Yes, sir.
Yes. This is the color. You can choose it actually when you are processing the 2D spectrum. You can choose the color actually. It's nothing to do with the blue or red actually. These circles are encircled by us for for easy to understand actually. But this is very important to make the box actually. Unless otherwise you make the box connecting 4 points, and then you will not be able to know actually they are connected to each other. I mean, the diagonal peaks, diagonal peaks should be ignored. Only the cross peak should be taken into consideration.
And next question is, sir.
Yeah.
The next question also the same one. So why red and blue dot in nosy? Same thing.
Okay.
Then what denotes this blue and red color? The same question, sir.
No, actually, this is nothing. Actually, this this blue and red color means this is only just this is the box which we when we process, we have to make this line. Actually, now it is very easy for us. Earlier, when we get the spectrum, we have to physically take the printed spectrum and then make by using the scale. We have to make the connection actually. So we have to make the boxes in the COSI. We have to make the boxes. Whereas in the, I think what he's talking about, is it a HSQC or what is it actually is talking?
No, sir, simply nosy like that he typed.
Oh, nosy. Okay, let me go to
yes,
nosy. Nosy, yeah,
yes.
yeah. 1 minute. Yeah.
One more question from nosy also. There's a negative effect of nosy. Question mark is there, sir. Negative effect of nosy. Then he put some question marks.
No, actually, nosy, it's true. Actually, nosy is good for small molecules. Actually, when you are talking in terms of the spatial interaction with the big macromolecule, we use a ROSY, ROESY. So ROSY experiment. Actually, this is used when we take the cyclodextrin. Say, for example, cyclodextrin and the small drug, how they are interacting. Actually, there is no bond between these two complexes. Actually, this complex is only purely based on the van der Waals. You can see this kind of interactions. You can find it by using the ROSY, big molecule. It's very good technique actually. But when we use for different purpose actually.
Then last question, sir, from Yuvanesh. Sir, what is double resonance and spin tickling, and how these helpful in simplifying the spectra? Like that he asked.
Okay, see, double resonance actually what we call it in the 2D NMR. These signals are recorded as a function of two time variables. That's a T1 and T2. And the resulting data, Fourier transform twice to yield a spectrum. First is the one which is actually first when we irradiate, and then it goes to the evolution, and then the second one actually before it comes to when it comes to the resting state. That's once it is excited before it comes to then the second pulse is given second time. So that is how. So it will be like in the case of COSI, it will be like 90, 180. So completely flipping will happen actually. So 90 degree and 180 degree. So these two times we are giving the pulse. This can be this can be explained. But the other spin actually, if it talks about spin, but suppose if the hydrogens, if the neighboring hydrogens are not in the similar environment, suppose if the CH is attached with the CH2 and CH3. In NUT, we are supposed to get 2 plus 3, 5 plus 1, 6. That's what n plus 1. But we don't get it actually. First, the CH hydrogen will be split into triplet. Each triplet, by the way, each triplet will be split into quadret actually. That's what a triplet quadret. Altogether, 3 n plus 1, 3. That means 3 multiplied by 4. 12 you will get it actually. So this is a bit, you will get, this is called multiplet, but you can easily resolve it. Yes.
Yes, sir. That's all from question, sir. But, more than 90 charts we have received. Excellent session and very informative like that, sir.
Thank you very much. It's a tough. Yeah, I think somebody wants to ask any question. Yes.
Hello, sir.
Yes.
I have a question, sir. Suppose if our compound contain carbon center contain with fluorine atom, so how can we will distinguish by 2D NMR or anything? Can you help me for this, sir?
Yeah. See, yes, fine. Actually, very easily. Fluorine, in order to get the fluorine NMR, you need to tune it actually. But normally, you don't. You need to have a probe. Actually, people may not be having. But I will tell you, not the NMR, but mass. You'll be able to get this information actually. From mass, you'll be able to get the isotopic peak. That's very easy to identify. But in the case of, you can easily see what carbon-13 NMR. What we are getting is a decoupled. Otherwise, if you allow it to couple with hydrogen, that's what we used to get in earlier olden days. we get the coupled spectrum. That means if carbon is having one hydrogen, you'll get N+1. We get for one carbon, we get a doublet, like proton, what we get. Okay, but what we are getting the carbon-13 is a decoupled. So we decouple the fluorine also here. Okay, in that case, you will so that will be appearing as a singlet. That's what we are getting. But in the 2D NMR, you'll be able to easily identify it actually. That will be appearing as a singlet having no connection at all, no connection with the hydrogen. So HSQC will be able to tell you separately. So it has got no hydrogen. Yes.
Thank you, sir. Sir, can you again explain that noisy space arrangement, because it is little bit confusing for confused.
Okay, very good. So this is this hydrogen. I think, can you see? I'm sorry. I will go to this slideshow mode. Then I'll be able to use my pointer. 1 second. Can I take this one? Can I take?
Yes, sir. Yes, sir. Of course.
Okay. This hydrogen. See, if it is dash bond means below the plane. Alpha, what we call it is it's a plane below and above. Alpha and beta. Okay. Beta is above the plane. Alpha is below the plane. This hydrogen is below. If this hydrogen is also below, that means suppose actually it will be the below. So these two are in the close proximity to each other. So they will be actually resonating. They will be having effect. That's a overizer. That's what we call it as a spatial effect on these two. You got the point? If this is above, that means if it is the 180 degree above, just opposite to each other, like this. Okay, this is just opposite to each other. Absolutely, there will not be any resonance with each other. So they will not appear as, there won't be any influence on this thing. So they will not give you noisy effect at all, noisy spectrum at all. You got the point?
Yes, sir. Yes. Thank you, sir. Thank you so much, sir. I wanted to tell you, sir. I have also worked with Rahul, sir. He is very excellent and very knowledgeable person. I'm impressed so much. Thank you so much.
Thank you very much. It's tough to explain in 45, 1 minute, 1 hour time, the whole thing, about everything. It's tough, but I think it's okay. Thank you.
Sir, good morning.
Thank you, sir.
Hello.
Yes.
Sir, I am Sastri from the same
Dr.
department.
Sastri. Yes, Dr.
Yes,
Sastri.
sir.
Yes.
Greetings to you.
Thank you, sir.
Sir, just I want to know, just dynamic means temperature NMR can be done in the same instrument itself, or means how to perform the experiment in 2 different temperatures in the same instrument?
Sir, the same instrument you can do that actually, but see, we say 300 Kelvin, or you can increase the temperature or you can decrease the temperature. So the same, but you have to have the that setup actually. It's not easy. We have to have the cold probe. Then only we can do that one. Otherwise, with the normal probe, you cannot do that, sir. Actually, it's not possible to do that.
Okay, sir. It is, I am asking for the interest of a second MSc student. I am taking last 5 years for NMR course for them.
Thank you very much. It's my pleasure, sir. It's my pleasure.
Sir, just for N-dimethyl formamide case, we are demonstrating this experiment, sir.
Oh, N-dimethyl formamide.
Thank you very much, sir.
Okay.
Yes, sir. Yes, sir. Okay, sir. Thank you, sir.
Thank you.
Okay.
Sir, you have delivered very informative lecture, sir.
Thank you, ma'am. Thank you very much, ma'am.
Sir, I am very delighted to hear that you are the alumnus of our department.
Yes, ma'am. Very much. I'm the first set.
Yes, sir. Many eminent scientists were shaped from our department. You are one among them, sir.
Thank you.
Our students get inspiration from you, sir. Thank you so much, sir.
Thank you very much, ma'am. Thank you. It's my pleasure, ma'am. Thank you, ma'am.
Okay. Thank you so much, sir, for your presentation.
Thank you. Sir. Thank you very much to everyone.
Hello.
Yes.
Sir, I'm from Naipa, Kolkata. Sir, I wanted to ask one question. That we have just a compound solution in DMSO, and if after go inside the NMR, it convert into the crystal form. That solution. If any solution for it, sir, if you suggest.
You run, it's simple. You run it in higher temperature actually, because the DMSO, I don't know, I think you are doing it at the lower temperature. It just got it will crystallize it actually. So you do it with the higher temperature, or you try to change the solvent actually. But I don't know whether it is soluble in CDCl3 or methanol D3 or even any other solvent. But the problem, if you have dissolved in DMSO already, it's difficult to get the molecule back actually. This is the, we try to do it with the CDCl3 so that you can recover the compound. If you are a natural product chemist, it's really tough. You cannot afford to lose the molecule. But this is the solution actually. Either you change the solvent or you increase the temperature of the probe. I think you are having a 400 megahertz, I think.
Yes, sir. Yes, sir.
Yeah.
Yes, sir. Yeah, 400.
Yes.
Okay. Okay. Sir, can you share this PPT with us, sir? It will be very helpful for us.
I think the organizer will decide that one. I don't know.
Okay. Thank you so much, sir. Have a good day, sir.
Thank you very much.
Thank you so much.
Thank you, ma'am.
So an announcement to the participants. Attendance link will be provided at the end of the 4th session at 3:45 p.m. Thank you, and kindly join us for the post-lunch session at 1:50. Thank you.
Sir, thank you, sir. Thank you very much, sir.
Thank you very much.
Very kind of you, sir. Thank you, sir.
Thank you, sir. Thank you very much. Thank you, ma'am. Thank you to everybody. Thank you. Bye.
Thank you.
Hello? Hello? Hello?
Yes, sir. We hear you, sir. Thank you.
I will share the screen with my PowerPoints because I slightly modified. In case it is not working, you can share the screen. Okay, sir? Hello? Hello? Membrane distillation போட்டுருங்க. ஆமா ஆமா.
மேடம் சொல்லுங்க மேடம். ஆமா லிங்க் அதே லிங்க்ல தான் போயிட்டு வரோம். ஆமாங்க.
Hello, sir? Hello? Hello?
Hello?
Hello?
மேடம் கேக்குதுங்களா மேடம் சாந்தி மேடம்?
கேக்குது.
ஓகே சார் சுந்தர சார் கேக்குதுங்களா சார்?
கேக்குதுங்க சார். கேக்குதுங்க சார்.
ஓகே சார் வணக்கம் சார் ப்ரொஃபசர் சார் வணக்கம் சார்.
வணக்கம். முதல்ல நான் ஷேர் ஸ்கிரீன் பண்றேன். பை சான்ஸ் ஐ அம் ஃபெயிலிங், யூ கேன் ஷேர் த ஸ்கிரீன்.
டெஃபினெட்லி சார். எஸ் சார். நான் எதுக்கும் ஸ்கிரீன்லயே போட்டு வச்சிருக்கேன் சார். அப்படி ஏதாவதுன்னா நான் உடனே டேக் ஓவர் பண்ணிடுறேன் சார்.
I will share my screen because I have modified a little bit of things.
Okay sir. Fine sir.
Hello.
Sir, Vijay sir, good afternoon, sir.
Good afternoon, sir.
Sir, Sundar sir.
Sir, good afternoon, sir.
Good afternoon.
Good afternoon.
Professor Bose sir, good afternoon, sir. Yes, sir. Good afternoon.
சொல்லுங்க சார்.
இல்ல சார், சார் ப்ரொஃபசர் வந்திருக்கிறாரு கோஷ் சார், அவருக்கு குட் ஆஃப்டர்நூன் சொன்னேன்.
ஓகே. Good afternoon, sir. Good afternoon.
Ma'am, HOD ma'am, good afternoon, ma'am. Ma'am.
Good afternoon, sir.
Good afternoon, ma'am. சார் வந்திருக்காங்க மேடம். ப்ரொஃபசர் பிரபாகர் சார் லைன்ல இருக்காங்க மேடம், லிங்க்ல ஸ்கிரீன்ல இருக்காங்க. சார் விஜய் சார் வந்திருக்காரு, எல்லாமே ஸ்கிரீன்ல இருக்காங்க மேடம். சார் RS இருக்காரு மேடம், WS இருக்காங்க.
I am all those persons, sir.
47 இருக்காங்க மேடம்.
Good afternoon, sir.
Good afternoon.
Good afternoon, sir.
Good afternoon.
Good afternoon.
ஸ்டார்ட் பண்ணிடலாமாங்க மேடம்? WS மேடம்.
ஓகே.
ஸ்டார்ட் பண்ணலாம் சார்.
சார் ப்ரொஃபசர் சார் ஸ்டார்ட் பண்ணிடலாமாங்க சார்?
Okay, sir.
சார் பிரபாகர் சார் ஸ்டார்ட் பண்ணிடலாமாங்க சார்?
We can.
Yes, sir. Thank you, sir.
Thank you.
Good afternoon and welcome back to the afternoon session. Now the presentation is on membrane process for environmental safety by Professor Dr. S. Prabhakar. Professor Dr. S. Prabhakar is currently an adjunct professor in SRM IST and former head Nuclear Desalination Plant Kalpakkam and former head Separation Technology Section BARC Mumbai. He has a unique distinction of developing the membrane technologies from membrane preparation step to final deployment. He was one of the pioneers for the demonstration of the application of reverse osmosis technology for the production of safe drinking water and volume reduction of low-level radioactive effluents both at uranium mills and uranium metal plant. He was one of the members responsible for the erection, commissioning, and operation of seawater reverse osmosis multi-stage flash desalination plant at Kalpakkam and operated the plant at full capacity when he was the head. At SRM IST, he is guiding doctoral, master's, and undergraduate students in the research projects involving membrane applications. He has published more than 100 papers in national and international journals and has 3 patents to his credit. He has also contributed 6 chapters in various books related to desalination and water treatment, and 1 chapter each for 5 books published by Springer and INSA. He was awarded Homi Bhabha Awards for different achievements, including for special contribution for excellence in science and technology. We are so fortunate to have him with us today, and I now leave the floor to Dr. Prabhakar for the presentation.
Good afternoon. Good afternoon, everyone. Thank you very much for your kind words of introduction.
Good afternoon, sir.
Good afternoon. So, I am speaking as an applied chemist and not as a pure chemist of conventional sense. In fact, with the background of engineering as well as chemistry, I thought that there are many societal problems which can be sorted out by chemists in much better manner. Now, environment is one of the important things which is concerning the modern society, and we have to contribute enough towards that. Now, if we look at it, initially, see, environment was not a concern about 50 or 60 years back. Slowly, the concept of protecting the environment cropped up. Initially, if you see, any waste is disposed nearby the house so that it doesn't harm the house concerned. Later, we became conscious of the society and it became okay, this thing. Now, as far as government is concerned, they recognized about 20 years back, environment has to be protected. They brought in environmental regulations so that no industry discharges their waste stream beyond a particular concentration. During that period, what happened really was, industries were hoodwinking the government by diluting their waste. By that time, they are wasting water as well as contaminating the streams. Then later, a situation came when government started putting up in mass that industry should not dispose beyond a particular kilograms or grams of a particular contaminant. Then, with increasing of environment, we have reached what is known as a zero liquid discharge. That means no liquid could be discharged. Unfortunately, this converts liquid waste into a solid form, but still the problem is not sorted out. During the rains or any of the hydrogeological activities, the contaminant gets leached and contaminates the whole system. Now, we are going towards the need for implementing zero discharge. No waste is to be taken. Now, the next step which we are envisioning is, there is nothing called waste. Waste is unutilized health. There is value in it, and that value has to be recovered. These are the fundamental principles of environmental safety. In this, membrane has a big role to play. Now, what are the conventional systems like precipitation or solvent extraction? They are all equilibrium governed process and requires large time and space footprint area also. Now, for the sake of economics, we cannot treat individual streams in the conventional manner. We combine all the effluent streams together and try to deal with them. Once you mix everything, separation of everything is different, is very difficult, and norms could not be achieved. Then process-based restrictions are existing because you have got to mix all the fluids. When your chemicals are added, they are also getting mixed. Or solvent extraction, also you have to mix the whole system and then allow them to separate. So you have got a lot of restrictions when you want to apply the conventional systems. In addition to that, since they are slow, we have to go for large inventories of chemicals and other resources in order to treat them. In this context, membrane has come to our help. Membrane is basically, we can understand as a barrier. In the barrier of the membrane, it separates two phases, And because of its specific property, it allows one component from the and doesn't allow the other component by so that bringing the separation. But membranes are not really perfect. They are not ideal membrane. As you would have listened from Ghosh, normally most of the membranes which are being used now commercially, they are made either by phase inversion technique or thin film composites. They have got a pore size distribution with the result that not all the pores are uniform. Some pores are bigger, some pores are bigger. So we do not get 100% separation. We get only a good amount of separation. So this is a basic minor problem with the membrane, but this can be circumvented over other processors. What are the role of membranes? Membranes enable us faster separations because they are mostly rate governed processes, and then it is modular in nature. You can adapt to an industry which is producing 10 liters of waste, and the same can be adopted which is producing millions of liters of waste. Then economic.
Sir, excuse me, sir. Sir, put your slideshow, sir. Slideshow. It's not.
Okay.
It's not in slideshow mode, sir. Yes, sir.
Okay.
Yeah, thank you, sir.
Thank you. So, and it is possible to have economic separations because most of the membrane processes are less energy intensive. And second thing, not much, no phase change is involved excepting in 1 or 2 cases. Peroperation is one process where phase change is involved. In the other cases, there is no phase change. Then they are all eco-friendly separations because there is a less chemical intervention. Okay, now let us look at what is the general philosophy by which membrane separations are achieved. Now, a membrane is a barrier which has got a surface which is responsible for the separation. The surface property define which is separated. It can be a size exclusion principle based on only size. Then it can be a physicochemical process which can depends on the physicochemical interactions. Then it could be a chemical like an ion exchange, or it can dissolve in the some species can dissolve in the membrane and get diffused across a gradient. Then there is a supporting layer for the membrane. It has to diffuse through the separated species has to diffuse through the membrane, and then it gets disengaged from the other surface, which can be motivated either from the feed side or permeate side. You apply a vacuum, you get the things out, or you apply some sort of a pulling some sort of a solvent where it can dissolve, it can pull out. In the feed side, you apply a pressure, it comes to the membrane. So this is the general philosophy. Now, each one is applicable to the particular range of membranes, particular properties of the membrane, which normally there are different types of membrane processes, but today I will deal only with porous membranes. Now, the different membranes have different characteristics. When we talk about porous membranes, they are used essentially in what are known as pressure-driven membrane processes. Now, we have a variety of membrane processes in this, right, starting from reverse osmosis, nanofiltration, ultrafiltration, and microfiltration. Now, as all of you know, reverse osmosis is the most famous process now for desalination of seawater or brackish water, or even in effluent treatment for recovery of water. Reverse osmosis is being used. The membrane used is a very finely porous membrane with the pore sizes in the order of a few Armstrong units, with the result that water alone passes through it. The separation here takes place purely due to physicochemical interactions. Now, just I will slightly digress. Osmotic pressure is a phenomena based on colligative properties. Now, we can visualize this osmotic pressure as the force which we have to overcome to pull the water out of the interaction with the solutes. That is why the more solutes are there, less water is interacting with each species. So you have to apply more force to take it out. So we have to, when the solution becomes concentrated and more concentrated, we have got to apply more and more pressure in order to pull the water out. And that is basically the philosophy of reverse osmosis. That is why we operate seawater reverse osmosis plant at 50 or 60 bar pressures. Whereas in the case of brackish water, we operate at 20 or 25 bar pressure, or even much domestic systems where hardly any dissolved solutes are there, we operate at 5 bar or 7 bar system. Now, then comes nanofiltration, whose pore sizes are slightly bigger than reverse osmosis. In addition to that, these membranes have a little bit of charge also incorporated into that, with the result that we will be able to separate multivalents from monovalents. Now, then comes ultrafiltration. It is the simplest filtration only, but the pore sizes are in less than a micron, with the result that it can give separations even in a totally homogeneous dissolved solutions. Whereas in the case of microfiltration, we are separating one phase to another. That is solid phase we are separating from the liquid phase. Whereas in ultrafiltration, it is a separation process mostly acting in the homogeneous phase, where macromolecules which are dissolved can be separated, or microbial organisms can be separated, or sometimes colloids also can be separated, which cannot be done in microfiltration. Now, with this distinction, next. Now, let us take the ultrafiltration, because this is the most useful, in my opinion, in waste management processes or quality recovery. See, ultrafiltration is purely a size-based separation process. It can separate on basis of size at pressures of 1 or 2 kg, and it is backwashable. Now, because of the sizes, only it separates. For instance, microbial organisms have got sizes greater than the ultrafiltration range, with the result that if a water contaminated with microbial organisms, you simply filter through the ultrafiltration, you get a sterile water. In fact, we call it as a vegetarian water because it doesn't contain any of the microbes in the final water. Now, what is the advantage? The RO also gives the same thing. But in this case, you can backwash and remove all which is accumulated on the feed side and again start afresh, which is not possible in the reverse osmosis system because the pore sizes are much smaller. It is being supported by a matrix which has got a larger pore size. So when you start backwashing, you will be disrupting the structure of the reverse osmosis membrane and it may not function any further. And then when size exclusion is not possible basically from the size of the ions, say, let us say, yeah, you have got an effluent where metal ions are present like copper 2+ or lead or something. It may not be as such separated by ultrafiltration, but we can make use of our chemistry to separate it. Add a complexing agent, it complexes, the size becomes bigger than the pore size, and you can get it separated. Now, whole thing is done in the ambient conditions, maybe 1 or 2 bars of pressure, and whatever is separated is concentrated on the feed side, and perhaps by changing the pH, you can decomplex the whole system and recover back all the ions. That means in an effluent treatment plant, because there are general processes available for water treatment and water recycle, but the basic problem comes with trace contaminants, which is not amenable for the conventional systems to separate. Now, there it comes into handy because you can use complexation ultrafiltration, or in general, what we call as a size enhanced ultrafiltration. In this, we enhance the size by some chemical means or physicochemical means. Either you complex it, you also use an adsorbent to which it can stuck, so size becomes bigger and get it separated. Once it is separated, you rework the process by changing the operating conditions and recover back the things. That means this can lead to value recovery, and not only for environmental regulation, but also it gives you value. Then these are the plus points, and it can remove metal ions, etc. Then nanofiltration, how it is useful in the environmental safety. Now it is again a physicochemical process, come size exclusion principle. The membrane, I said, is slightly charged. With the result, see, some of those effluents in dye industries, leather and tanning industries, they produce chemicals which are slightly bigger in size, and chromium, etc. also of that. So all these things in a complex state, you can separate through nanofiltration, allowing sodium chloride and other monovalent ions pass through it, with the result that it doesn't require too much of a pressure because some of the monovalent ions are passing through the membrane. but at the same time, it concentrates the macromolecules, which probably can be reused in the process if it is not undergone any physical chemical changes. So this is one thing. It is used in the food industry. It is used in this thing with the result that the water is free. In fact, the water that is coming out of nanofiltration in the food industry or in the reverse osmosis, it is basically sterile at the point when it leaves the membrane, and it can be directly used for any sterile water requirements. Then comes reverse osmosis. It is definitely a water purification system. It helps in recovering water, but there are many limitations. Now, reverse osmosis operates at a very high pressure, and as you are drawing water from the reverse osmosis system, the concentration of the feed keeps increasing, with the result that osmotic pressure keeps increasing. That means your application of pressure has a limitation in producing the water. When the osmotic pressure of the feed slowly rises and almost comes equal to the pressure which you are applying, we cannot get any more water. Or in other words, reverse osmosis can produce very good water for use, but it is not an effluent treatment system for meeting environmental regulations, because it is going to produce a concentrated stream which has to be further treated in order to make it environmental friendly. These are the basic limitations. So what happens then? We look for hybrid systems. In the hybrid systems means use a number of membrane systems so that you ultimately recover all the ions or species, so that environment is rendered friendly. For instance, I can recall one of our experiences in the uranium mill effluents. We have, after recovering uranium, the whole waste is acidic in nature. It contains a lot of calcium and sulfates, because sulfuric acid is used for leaching out uranium. With the result that a lot of calcium sulfate is there and it is acidic. So they neutralize also with lime, with the result that calcium sulfate is almost in the saturation point there. Now, when we use NF, because NF is slightly charged, and second, the nature of the calcium sulfate, it takes more time to crystallize. You making use of these two things and optimizing the operating conditions, we can remove virtually all the calcium sulfate in the NF stage, and the remaining, which is rich with sodium chloride, it is passed through RO. So we get the RO permeate, which is good for of water. The concentrate of RO is rich in sodium chloride, which can be used for regeneration of the column where we are trying to extract uranium, and then the calcium sulfate alone has to be disposed of as a solid waste. Now, this effluent treatment virtually makes the waste production almost zero. Now, if we come to the hyphenated systems, we are all talking about reverse osmosis for seawater. We are producing billions of liters of water throughout the world. The concentrate disposal is becoming a problem, which is very much rich in sodium chloride, calcium, magnesium, etc., etc. It goes back, and we say it is harmful to the environment there, because the sea animals may not be able to survive that high concentration. Now, the seawater contains virtually is a repository of all heavy metals as well as other species. Now, if you combine a process where UF followed by NF followed by RO, you can give an eco-friendly system which gives you pure water at the same time value recovery. For example, when you look at UF, you can add some complexing agent, because trace metals are available only in ppb level or ppm level maximum. So if you add only ppm levels of complexing agent or adsorbing agent, all these things will be trapped. Their sizes are made bigger, and UF will remove them first. Then after removal of this, you come to the NF stage where multivalents are removed. Only sodium chloride is allowed to pass through. So the concentrate between NF and RO is rich in sodium chloride. and the concentrate of NF is rich in bivalent and multivalent ions. Now, C is a source for magnesium. So you can use a concentrate to produce magnesium, which is one of the important materials for us. And similarly, the concentrate of RO, which is rich in sodium chloride, can be directly used for producing caustic. Because there is no multivalent ions there, the efficiency of caustic production will be very high. Then RO, after the RO, we have got pure water. That means the whole seawater now is made into a useful value product by the combination of a number of membranes. Now, these are the conventional ways where work is going on and people have been attempting, and some of them have been proven also for the commercial stage. Now, next one, which is a developing one, which is a membrane distillation process. Now, when we say membrane distillation, we think we have to supply heat energy, etc., etc. No, it is not required. Now, most of the power plants, most of the petrochemical complexes, they discharge large amount of hot water after doing the cooling for them. Normally, what happens is hot water goes to the cooling pond, allowed to evaporate. In that process, it gets cooled. Now, this membrane distillation works on the same philosophy, but we are recovering the water that is evaporating as good water. Now, what we have to do is that when the cooling water is coming back from the systems, we interpose this membrane. It is allowed to pass through it. On the other side of the membrane, we use a cooling medium, that is even water at a lesser temperature. So whatever vapor is passing through the membrane, it gets condensed on the other side. So pure water is produced. Now, as if it happens in our normal ceramic pots, which we are having in the house, where we cool water, as the vapors are removed from the water, the latent heat is taken from the water, with the result that the incoming water, the temperature comes down. So it has got a win-win situation. In one, we are getting pure water from the one which is discharged and it is called waste. That heat is utilized. And the other side also, the temperature has brought down to near ambient temperatures, which is allowed to be discharged as per environmental regulation without harm to the environment. We have to see, otherwise, if you look at it as a desalination process, it is very costly. It's very, flux is very low, productivity is very low, it cannot be used. But for other applications in the effluent treatment or even separation of some small organics from this thing, it becomes a very, very important tool. So this is one developing process where we can concentrate in terms of ML. Now in this, for doing different types of work, we have 4 types of membrane distillation process. One, see, one side hot water or a hot stream is flowing, that is always constant. The way in which the vapors are extracted and condensed depends upon the type of process which you are adopting. One is called direct contact membrane distillation, where the vapors are directly condensed in a cool water, which is passing through the other side. Then we have got air gap membrane distillation. It is nothing but cool water is circulated in outside the chamber, and the inside whatever vapors come get condensed on the surface of the chamber, which is having a cooling water circulation outside. That is called air gap. Then we have got sweep gas membrane distillation, in which a gas is allowed to flow through the other side of the membrane, and it takes away all the moisture, and then it is condensed outside. Or the fourth operation is vacuum membrane distillation, where you can apply the vacuum, draw the vapors, and allow it to get condensed at a cooling chamber. Now, why this 4? It is not all or not necessarily for desalination. This is for removing traces of alcohol which is available in some of the effluent systems. Same of the organics which are available in some of them. So in order that it should not mix with water, we have got the air gap. Similarly, each one has got an application area where it can be applied, and it is more suited for environmental applications, where pollution prevention rather than pure water production process. Then the other one is called forward osmosis. Now, in the membrane processes, we have got 2 types of processes. One set is called active process, another is passive process. In an active process, we have to supply energy from an external source. Now, if you look at RO, reverse osmosis, we definitely get pressurized water and pass it through the membrane, you get pure water coming out of it. But then you are pressurizing the water using the external energy means. But in the case of forward osmosis, which is nothing but the osmosis, it's a natural phenomena, we get the water separated out. But as you know, the water is not going to be pure because it has to go and mix with some other solution which is acting as an osmotic sink. Now, there are many such systems being exploited. People feel how to separate water which is mixed with the external solution. They use phase change materials, either that or they use inorganic compounds which can be on heating, which can be driven as gas like ammonium carbonate, etc. They are trying to use. But the real use, I believe, is in the effluent treatment. Now, the sewage water, which has got less inorganic ions, after the primary and secondary treatment, it contains mostly inorganic ions and it is disposed of. Now, allow it to pass through the forward osmosis membrane. So we use seawater as a osmotic sink. With the result, what happens? Where water is there in the wastewater, by the process of osmosis, it dilutes seawater. Now, once the seawater gets diluted, then your RO plant can operate at much lower pressures and produce good water. With the result that indirectly you are saving the energy cost for the RO plant. At the same time, the sewage water is getting concentrated. Now there is a water, food, and energy nexus. When we combine all these things, there will be no waste which is going into the environment at all. In fact, the present philosophy is to have value recovery from the waste. Now, I will give another example in membrane solvent extraction. Now, solvent extraction, as you know, has got a lot of limitations, right from selection of the solvent based on the solubility, number 2, based on the density, and we have to intimately mix, so it will be in the open system, and our vapors will be produced, etc., etc. It is environment. So this solvent extraction cannot be that easily adopted in small scale industries, at least for effluent treatment purposes, because a lot of organics, valuable organics, go into effluent like phenol and other things which cannot be recovered. But now you can use a membrane module which is very compact, like hollow fiber membranes, a lot of surface area, and then you pass the solvent through one side and pass the effluent through the another side. The pores which are available, they provide the interfacial contact to the solvent and the effluent, with the result that the species which you want to separate gets extracted by the solvent, and the solvent becomes rich in the species, and the aqueous phase becomes lean. That means you have removed the thing. Now what you do is, in the next module, you strip the phenol or strip the contaminant in the same way. So in a single system, when it is linked together, you can extract the phenol and again recover the phenol from the other side. The solvent is recycled. Now, what is the advantage? It is enough if we have a small inventory of the solvent, which can repeatedly be recycled, but at the same time, keep removing the contaminant and allow it to recover. In fact, this is one of the latest things which has to be developed, and this will go in a long way for MSMEs who are working on fine chemicals and all, to recover some of the contaminants which have gone to the effluent, otherwise which is valuable to them, as well as environmental safety. These are the other examples. And we have many such examples in gaseous separation through membranes. We can remove the offending gases by dissolving it in appropriate solvent on the other side of the membrane. Once it dissolves, where the affinity is more and more vapors will go. What we have to calculate is how much length it has to travel so that the complete removal can be achieved. So in general, membrane being a barrier, it does not require intermixing of these phases. See, in solvent extraction, you have to add the solvent to the aqueous phase and thoroughly mix, and then allow it to separate and remove it. Whereas here, no such thing occurs. You send one phase to the one side of the membrane, other phase to the other side of the membrane. Ultimately, you get the mass transfer. Now, how it is so effective compared to the conventional processes? See, conventional processes we are mixing in order to bring intimate contact of every molecule in two phases together so that the transfer of mass occurs. Whereas here we have got millions of small pores which makes virtually molecule to molecular contact through the interface, with the result that whatever transfer occurs, it can occur very fast and without much of an external interference. Now this gives you the advantage. See, in the conventional solvent extraction, your solvent density and the aqueous phase density have to be different. Otherwise, you cannot separate them. The purpose is lost. Whereas here, the densities need not be different. If you get a good solvent which has a high solubility for that particular species, you can use in the membrane solvent extraction, which you cannot do that in the other thing. And then simultaneous recovery is possible in this. So these are the things. I'm not saying that it is there in technology today. This is where chemists can contribute, because it can. One more advantage is what works in the lab will work in the field because it is modular in nature. On the other hand, in conventional system, when you go from 10 liter scale to 1,000 liters or 10,000 liter scale, the scale of factors are different. The problems which you encounter is different. So they have to be designed independently. So these are the advantages. And I think I will open myself for questioning further. Thank you very much.
Participants, if you have any questions, you can ask. Unmute yourself and ask the questions.
Sir, good afternoon, sir.
Yes.
Sir, I am Dr. Velmani from Coimbatore. Sir, I am Dr. Velmani from Government Arts College, Coimbatore.
Okay, sir.
Sir, I just wanted to know, usually whatever we have, we use the ROs that is used in domestic households. Does it have any lifetime in the sense that for how many years it can work, or it is just a throwaway material, or is there any chances of doing some sort of a cleaning there? Is that way? Is it possible, sir?
In general, nowadays membrane is a consumable item. Its life can vary from 2 years to 5 years or 7 years, depending upon your system, depending upon the mutual compatibility of the membrane. People are also developing ceramic membranes, etc., which may last longer. But definitely, membrane has a life. It has to be changed once in a way. But if you work out the overall cost, you may not feel the pinch of the cost. See, even the equipment which you have in any of the plants, that also has a life of 15 years. But this life may not be 15 years. This may be 3 years or 4 years, or depending upon the system. Membrane is a consumable.
So sequentially, you're adding a nanofilter and then an RO. In that case, the life alone is getting extended, right, sir?
See, how do you define life is a question. For instance, desalination.
Okay.
We say that life is lost when the product is more than the potable level. When the product is more than the potable level of salts, we say the life of the membrane is over. But now I put one more membrane unit from the potable level. From the high level, I will still reduce to a very low level, and it becomes useful to me. It's a question of cost, and it's a question of a design of a system. Now, most of the places you find there is a two-stage reverse osmosis system in order to extend the life. Because in 4 years, the performance deteriorates, your product ability goes up. So people thought that every 2 years you have to take, but that is not the case. It's a small RO plant nearby, for which the feed is the permeate of the first RO plant, and the life overall comes to 7 to 8 years. So 5 years is becoming 8 years, and the second RO plant which you are putting doesn't require any other treatment other than the modules and pump. So it all depends on the process design. And membranes are becoming sturdier and sturdier nowadays. What has become for 3 years earlier has come to 5 years and 7 years. It may last further.
Okay, sir. Okay, thank you, sir. Hello.
Yes, sir. Please, sir.
Yes, sir.
Thank you, sir. Thank you, sir. Thank you, sir.
Thank you, sir. For okay, and I do have some other questions, sir, but anyway.
Audio is little bit. Yes, sir. Disturbance is there.
I'm not able to hear sir's voice, Dr. Prabhakar's voice.
Wait.
Does have a break in between.
Oh, but I cannot. Maybe it's the problem of my line.
Okay. Anyway, thank you, sir. Thank you for answering it. Thanks a lot.
You can use the phone. What is the number I should dial?
Kindly tell your number. Sir will contact you, sir.
Okay. Otherwise, also I can contact you and answer the questions. No problem.
Oh, sure, sir.
You can tell the number where I can, which is connected to your list.
It is 9942909994, sir.
994290
0994. Dr. Vail Money. Usually, when they are designing these domestic RO that is being issued to us based on certain liters, sir, 32 liters per hour, 25 liters per hour, they do say something like that. And the membrane that you just where there is a sticker on it saying that it can be utilized for brackish water type. I don't know what they actually mean by that.
Water is otherwise called back.
It is like this. These membrane and the pressure they would have designed.
Yes, sir.
It only will take up to a particular salinity because salinity is directly related to the osmotic pressure.
That's
for
fine.
This performance, you have to apply a pressure which is greater than the osmotic pressure to get some. There are only 4 kgs or 5 kgs of pressure. If you take 1000 ppm of water, it is roughly equal to 0.7 kg of osmotic pressure. So, only for 8 kg or 9 kg, you cannot have more than 4000 ppm system working. That is why they mentioned that.
Okay, thank you, sir. Now, the certain technical details that they write it on the stickers, it becomes sometimes confusing. It's just confusing us. That's the thing. I just wanted to ask you. I'll try to get your number from sir, from Presidency College professors. Maybe I'll try to contact you, sir. Thank you. Sir.
Definitely, sir.
Thank you, sir. Thank you, sir.
Thank you, sir. Participants, any other questions are there? Please
There's
ask.
a question in chat box.
Oh, 1 minute, I'll look.
There is a question in the chat box. I'll just read the question. Hello?
I don't know, I'm not getting.
Is RO safe? Is there any leaching of synthetic membrane into pure water?
RO's place?
Is there any leaching of synthetic membrane into pure water?
At least we are not aware of it. I don't think. See, it is quite possible in the beginning if the membrane is not fully washed and prepared, because they preserve the membrane in some glycerol and other things. During that period, if it is not fully washed, something may come out. But after it stabilizes, I don't expect anything, because it is only polymer. Nothing else is there in the membrane. It's only a polymeric material. So there is no question of leaching of the polymer. In fact, it is one of the problems. Membrane disposal is one of the problems, because we are not able to either biodegrade or these things, make it small, shed it. So nothing is possible to leach from the membrane as such. Membrane gets hydrolyzed or chemically attacked, with the result that its property is lost.
Yes.
That is why we do not expose the RO membranes to chlorine, because chlorine being a very heavy oxidizing agent, it can kill the membrane's property. It can break some of the bonds, with the result that the property is lost. But leaching is very, very rare, and I have not come across at least.
Any other questions from participants?
Anyway, I have one comment. This topic is such that it requires face-to-face interaction rather than remote handling.
Sir, but still you have given excellent presentation, sir. It is very clear. And everybody, I hope those who have listened, means they will understood everything. It was excellent presentation, sir.
Thank you anyway. Thank you.
Thank you, sir. Thank you.
Thank you, sir, for your...
Ma'am, one more question is there in the chat box, please, ma'am.
Welcome.
Sir, one more question. Sir, one more question is that.
I'm
sir,
able to hear, please.
Yes, sir. What is the reason for using UF and RO in same water purifier unit? What is the reason for using UF and RO in same water purifier unit?
Right. See, you want to protect the RO membranes, which is costlier, and performance you want to protect. Now, any membrane process, what we are talking about, particularly RO, is a surface phenomena. Unless the surface is clean, it will not be able to identify water molecules from the rest and preferentially allow it to pass through it. Now, in order to make the surface always safe, we do not want any deposits of microbial organisms or any small foulants which may not be seen by the eyes, but which will be present in the water. If we use ultrafiltration first, virtually all these microbials and all suspended matter which we cannot see, which are likely to deposit in the membrane, are removed. By using an ambient pressure operating ultrafiltration unit, which is cheap, that helps in saving the membrane surface and prolongs its life for a good time. Otherwise, if you don't use that, immediately, if it is a borewell water, it may not happen that fast. If it is a municipal water, in 2 days, your plant will stop. Because the foulants will deposit on the membrane surface, and membrane surface is no more available for the separation of pure water from its solution. That is why it is important. Pre-treatment is a very, very important step in any RO process, whether it is in wastewater treatment or was in desalination. That is why operator also becomes very sensitive. If that fellow sleeps for a minute, if it doesn't dose the chemicals properly in the pre-treatment step, membrane will go back completely. This is one big problem. RO operators have to be skilled. Even though it is a question of operating a couple of valves, but he has to be skilled, use his brain to ensure that things are going in the right direction. That is why they provide 1 or 2 pre-treatment units. Sir, you are convinced, or any further questions on that?
Participants, any other questions are there?
There is one question in the chat box. How to minimize the wastewater from RO?
Okay. See, there is something is called a recovery. Now, if you recover more, the concentration on the feed side keeps increasing. You have to apply more and more pressure. So it is an optimization between the pressure that is costing you and the recovery where you are getting less benefit. Okay. And more you recover, the quality of water also will suffer. Now, the best way to use RO water in the domestic sentiment, you draw RO water, RO purified water for drinking, less quantity. The remaining water should be used for other purposes. We should not throw. Use it for gardening purposes, use it for other purposes, then we can save. But by increasing the recovery, you will not get even good drinking water. That is a problem. And the membrane may not sustain for long when you go for high recovery, because unnecessarily you are applying very high pressure. When the recovery increases more, we cannot. So in fact, the general advice or this thing suggestion we give for all the RO plants inland or household, you have less recovery, but use all the water for different purposes. See, water use has to be reduced means you have to use according to the quality use linkage. For instance, you are flushing water not be good water. It can be RO water. And you don't need to drink, nobody drinks more than 10 liters of water per day. So your family maximum needs 50 liters of good water in a very luxurious way. So the remaining water, that quality need not be maintained, because less quality will do for flushing. And even for washing machine now, detergents are being used. There is no need for a hard water or a soft water distinction there. So this is what in all India level we are trying to promote, because RO, if you go for high recovery, the membrane also will get spoiled faster and you will be spending more energy. At the same time, your one portion of the water becomes waste. And if it goes to the ground, it will unnecessarily increase the ground salinity. So we want all the 100% water to be used, but use water depending upon the quality for different uses. The quality use linkage has to be implemented. See, one concern I find everywhere, including my society, when they put RO, they are wasting 70% of the water or 60% of the water. Now, that I agree, as far as drinking water production concerned, it is a waste. But if you do not use it for other purposes where it can be used, then there is no waste. But that has to come. We cannot afford to throw water even a drop. See, virtually every water we are using, we are consuming hardly less than 0.5%. The remaining are, water is only a carrier. It is a medium by which it carries the species to different parts in the vegetations or in the industries. Everywhere, see, for instance, take thermal industry, thermal power plants. It is a big consumer of water, maximum consumed by government. But all of them are used only either for a steam production, which is again condensed, or it is used for cooling purposes. But that is a big guzzler of water. So if it is recycled, so we have plenty of water. Only thing is, if we make a management properly, then we will not find shortage of it. That's why we have to see the whole system in an integrated manner and not in a secluded manner. We are looking at RO as a secluded process, but we take overall management of water in the house, things will be different. And now we are talking about water, energy, and food nexus. Even from sewage, everything is valuable now. You recover water, you recover fuel, you recover fertilizer, which can be used in the field. Now we are thinking in those directions. Any further questions?
I think that's all, sir. Ma'am.
Okay.
Sir, stop share screen, sir. Sir, you are sharing your screen, sir. Sir, Prabhat, sir.
Yeah.
Yes. Sorry, ma'am.
Oh, sorry. Thank you.
Thank you, sir.
Thank you very much for your patient listening.
Thank you, sir.
Given some value for your listening time. I hope some benefits will occur to both of us. Thank you very much.
Thank you, sir, for your nice presentation. It was nothing short of incredibly informative and interesting. Thank you so much.
Thank you. Thank you very much for the chance.
Thank you, sir. Thank you, sir. Thank you, sir.
The last presentation of the day is the metal catalyzed CH alkylation reactions by Professor Dr. M. Jaganmohan.
Ma'am, we can wait for some more time, ma'am. It's not available right now. So exactly we can start 3 o'clock. We can start.
So the next session will start exactly at 3 o'clock.
Hello?
Sir, good evening, sir. Welcome, sir.
ஆமாங்க. ஃபோன் பண்ணியிருந்தீங்களா?
ஆமா சார், ஆமா சார்.
ஓகே, ஓகே.
உங்களுக்காக எல்லாரும் வெயிட்டிங் சார். ஜஸ்ட் a minute, சார்.
சரி.
இதோ வரேன் சார்.
ஓகே. லைட் எல்லாமே நிறுத்துங்க.
சார் என்ன நேம்ல வந்திருக்கீங்க சார்? இனிய மகிழன். ஓகே சார்.
ஓ அப்படிதான் இருக்குங்களா?
நான் உங்க நேம் தேடிட்டு இருக்கேன்.
அது பசங்க அவங்க ஆன்லைன் கிளாஸ் யூஸ் பண்றதால
நோ ப்ராப்ளம் சார். நான் இப்ப இந்த கோஹோஸ்ட் கொடுத்துறேன் சார். அதுக்காக தான் சார்.
சரி.
எஸ் மேம். மேம் ஹச்ஓடி மேம் இருக்காங்களா? மேம் ஹச்ஓடி மேடம். சார் விஜய் சார் ஸ்டார்ட் பண்ணிடலாமாங்க சார்? சார் விஜய் சார். சார் விஜய் சார். சார் ஸ்டார்ட் பண்ணிடலாமாங்க சார் நெக்ஸ்ட் செஷன்?
டைம் ஆயிடுச்சு இல்லையா? கரெக்டா இருக்கு. பண்ணிடுங்க சார்.
எஸ் சார். தேங்க்யூ சார்.
Well, the last presentation of the day is metal catalyzed CH alkylation reactions by Professor Dr. M. Jagan Mogan. A few words about Dr. M. Jagan Mogan. He has received his doctoral degree from National Tsinghus University, Taiwan, and has nearly 15 years of research and teaching experience. He has successfully guided 6 PhD scholars and has 3 ongoing projects apart from the 7 projects completed. He has got an impressive list of publications, around 93, in international and national journals. His total citation in Scopus is 4287 with H-index 42. He is a recipient of many awards and recognitions. Few of them are ICT Young Scientist Award by Institute of Chemical Technology, Mumbai, and DAE Young Scientist Research Award by BARC. We are so happy to have him with us today, and I now leave the floor to Dr. M. Jagan Mogan for the presentation.
Thank you very much for your kind introduction, madam. Okay, so can I start?
Yes, sir. Please, sir. Sastri sir also there, sir.
Oh, that's yeah. I met him when I was in ISAR Pune.
Right, sir.
So can you start, sir, now?
Yes, sir. Yes, sir. Your screen is presenting, sir. You are presenting your
okay
slide.
So first of all, I would like to thank Professor Vishwanath for giving this opportunity to present our research work. So today I'm going to talk about our recent observation on metal catalyzed CH alkylation reactions. So our research mainly deals with the metal catalyzed organic reactions. Our main aim is construction of chemical bonds in a highly atom economical and environmental friendly way. So what we do is that, before going to talk, I would like to give a brief introduction about our research activities. So what we do is that in our laboratory, first we design a new catalyst. So we by using various ligands, we design new catalyst. Mostly we deals with the transition metal catalyst. So after that, by using the catalyst, we develop new synthetic methodologies. And then later on, by using the synthetic methodology, we prepare natural products, biologically active molecules, and chiral molecules. We also pay more attention towards mechanistic investigation, what is happening in the reaction. So in my today's talk, I'm going to focus on CH functionalization reaction. My research, if you see here, it's mainly deals with the metal catalyzed organic reaction. So, before going to my research presentation, I would like to give a simple introduction about mechanisms in organometallic chemistry. So as you know very well, in typical organic synthesis, we have several mechanisms. For example, for substitution reaction, we have SN1, SN2. For elimination reaction, we have several mechanisms. So like that, in organometallic chemistry also, there are several important steps. So frequently in my today's talk, I use this kind of terms. It would be very useful for MSc students. Before going to my research presentation, I would like to give a simple introduction about mechanisms in organometallic chemistry. So if you see here, in any metal catalyzed reaction, the first step is ligand substitution process. So in ligand, this is the basic step in a metal catalyzed organic reaction. So after that, depends upon your reaction, the mechanism changes. Like in some reactions, you will have oxidative addition, and then if you have oxidative addition, reductive elimination is a reversible process. So that step also would be there. In some reaction, we may have transmetallation, insertion, beta hydride elimination. We will see one by one. In metal catalyzed reaction, the first process is ligand substitution process. So that is the first step in all kind of metal catalyzed reaction. So mostly we know it very well. If transition complex obey 18 electron rule or 16 electron rule, then we consider those type of metal complexes are very stable. So this all we know it very well. So now question comes, if your metal complex obey 18 electron rule, why it has to dissociate ligand? So generally for catalytic reaction, minimum you need 2 free vacant site on metal surface. Minimum we need. For example, if you take octahedral complex, 2 ligand has to dissociate, and then you should have ML4. So that in that 2 free vacant site, we can do various type of organometallic reaction, metal catalyzed reaction. So now basic question comes. So if your complex obey 18 electron rule or 16 electron rule, already these complexes are very stable. So why it has to dissociate? This is very, very basic question. So that's why, this before going to that, we have to see classification of ligands. As you know very well, you might have, particularly master students might have studied in organometallic chemistry. So ligands are classified into 3 types. One is negative ligand, the second one is neutral ligand, and third one is cationic ligand. So generally, this neutral ligand is very, very useful for metal catalyzed reaction. So this anionic ligand or cationic ligands are not much useful. So in neutral ligand also, then there is a possibility comes, like what type of ligands are very good. So neutral ligand, I give you example, ammonia, let us take triphenyl phosphine. So ammonia, this ammonia is a very good neutral ligand. It won't change oxidation state of metal, but those type of ligands are not good for metal catalyzed reaction. So here the new term comes like innocent ligand. So we always say innocent ligand. So like a triphenyl phosphine is a kind of innocent ligand. So this ligand, this type of ligand only is needed for catalytic reaction. So what is particularly in catalytic reaction, the ligand role is very straightforward. Whenever metal wants, ligand has to go and coordinate, and whenever metal doesn't want, ligand has to dissociate. So those type of ligands are very good. So generally triphenyl phosphine ligands are very good for this kind of reaction. Now, I said, ligand substitution process is very, very key. It's very, very important process in metal catalyzed reaction. How this ligand dissociation is happening. So, because, if your ligand makes very stable complex with metal, it won't break. So, you need a ligand whenever this bond has to dissociate, that bond should break. Whenever metal wants to make bond, then ligand should make bond with metal. So those type of ligands are really good. Those type of ligands are called innocent ligands. So now how that ligand dissociates, that mechanism is very, very important. There are 2 mechanisms in ligand substitution process. One is associative mechanism and another one is dissociative mechanism. So if your complex obey 18 electron rule, then your metal cannot go more than 18 electron, right? So in order to octet rule, so what should happen is that if any complex obey 18 electron rule, due to steric entrance around the metal, so on metal you have 6 ligands, right? So due to steric entrance, that ligand can dissociate, or you can give some external energy like heat energy or light energy. So when you give external energy, then ligand will dissociate. Like that, here there is a equation ML5X. Okay, this complex obey octahedral. I know basically this is octahedral complex, obey 18 electron rule. In dissociative mechanism, what happens if you apply heat energy or light energy, this X dissociates, and then when you do organic transformation, you add some organic molecule, right, that goes and bind with metal, so that this kind of intermediate forms. So this type of mechanism is called dissociative mechanism. For example, you have a square planar complex, let us imagine. So you know it very well. Most of square planar complex obey 16 electron rule. Okay, in d orbital, only 4 orbitals are involved in bonding. Only 1 orbital won't involve. That is dx square minus y square orbital. Okay, so that the energy of the corresponding orbital is very high, so that in square planar complex it won't involve in bonding. So in this kind of cases, associative mechanism happens. How this associative mechanism happens? Like already your complex obeys 16 electron rule, so it can maximum go to 18. Okay, but it cannot go more than 18. So in this case, what is happening? The incoming ligand is there, no? That incoming ligand, time being, goes and bind with dx square minus y square orbital. So that here, what will happen is that the square planar complex goes to a penta-coordinated complex, like a trigonal bipyramidal, like this kind of geometry you will have. After that, whatever ligand you are having, original ligand you are having with metal, that dissociates. So here Y goes and bind. 16 electron complex goes to 18 electron complex. After that, this X goes away, and then you get complex like this. So in this case, now imagine your Y is your organic molecule, whatever you are taking, that goes and bind, and then X, already you are having the ligand, innocent ligand, that goes away. So like that, this associative mechanism is happening. So here what I conclude is that if your complex obey 18 electron rule, so the dissociative mechanism is happening. If your complex obey 16 electron rule, then associative mechanism is happening. Now, already I have explained associative, dissociative mechanism. Now let us go for second. Now what happened? Now on metal complex via ligand substitution process, one ligand dissociates. Now organic molecule, let us imagine you are having AB. Okay, here let us imagine you are having organic molecule. So in AB you have one covalent bond. Okay, this covalent bond goes and bind. Already one ligand dissociates on metal. So this A and B goes and bind. After that, what happened? This A and B bond cleaves, you get oxidative attack. So I said for metal catalyzed reaction, generally you need 2 vacant sites. The reason why you need 2 vacant sites is that this molecule, this organic molecules reacts with this metal, giving like this kind of site. You see here A occupies one site and B occupies one site. So minimum you need 2 sites. Okay, so this type of mechanism is called oxidative addition. And I generally put it AB. Now I go very closely. Now the Nobel Prize winning reaction, Suzuki reaction, we know it very well. Here aromatic bromide is there. Here you have sigma bond. The sigma bond goes and bind with the palladium complex. Here palladium tetrahydrophenol phosphine is a catalyst. Here PD, PPH3O4 you have 2 ligand dissociates, and then this sigma bond goes and bind. After that, oxidative addition is happening, and then you get addict like this. In oxidative addition, what is happening? If you have palladium 0 oxidation state, then it goes to palladium 2. That's why oxidation is happening on metal. Palladium oxidized to 0 to +2, and then followed by addition. That's why the term oxidative addition occurs, in this way. So now oxidative addition, everything happens. Reductive elimination is a reversible process. For example, in organic molecule, you have 2 species like A and B. So in reductive elimination, what is happening? Metal oxidation state is higher only. For example, here metal oxidation state is 2. What happened here? A and B both are adjacent to each other. So that in this case, reductive elimination happens. A and B makes new bond, and then come out A and a new molecule. After that, metal reduces 2 to 0. So that's why, like a reduction is happening. So metal oxidation state is 2, and then it goes to metal 0, after followed by elimination of this A and B. So this is another mechanism. And then for reductive elimination, what is important? For example, if 2 organic molecules, should eliminate, that means both molecules should be cis to each other. So if you see here in platinum complex, you have methyl group. So two methyl group, are cis to each other, so that reductive elimination happens very easily. For example, if you have trans geometry, then reductive elimination won't happen. So this is classical example. So here two methyl groups are trans to each other, so that here reductive elimination doesn't happen. Now the next process is transmetallation. So transmetallation is nothing but exchange of ligand. For example, let us take here allyl bromide. So here metal is magnesium. So magnesium has two ligands, one is bromine and another one is organic moiety, allyl moiety. So now you have another species called a tin, the triphenyl tin chloride. So here tin has 3 phenyl ligand and 1 chlorine ligand. If you see here in this two, if you take this two reagent and mix together, what will happen is that you might have heard about hard acid, hard base, soft acid, soft base theory. So you know it very well. Hard acid likes to make bond with hard base. Soft acid likes to make bond with a soft base. In this species, if you see here magnesium, so magnesium is hard in nature, and then bromine is also hard in nature. So magnesium is hard acid, bromine is hard base. So magnesium bromine bond is very strong, whereas magnesium carbon, if you see here, magnesium is hard acid, carbon, this moiety is there. No, this is soft base. So this bond is not very much strong. So whereas in this case, if you see here, tin is there. So tin chloride bond, tin is very, very soft in nature. And then chlorine is there. No, this chlorine is hard in nature. If you see here, this tin chlorine bond is not very strong. So that if you mix together, what will happen is that this chlorine is soft in nature, so that it prefers to have bond with the tin. So chlorine is hard in nature, it goes with the magnesium and then form MgCl2. So like that, hard acid likes hard base, soft acid likes soft base, so that this type of exchange is happening. So this type of process is called transmetallation. And then insertion. This is also very important process. For example, if you have a carbon-carbon pi component or carbon-carbon, carbon, some other pi component, let us imagine you are having carbon monoxide. So let us imagine, so in carbon monoxide, you have a triple bond, right? So what will happen is that if you are having MX, so this MX inserts to carbon, this carbon, and then makes a compound like a carbonyl compound like that, in same carbon, M and X inserts. This type of insertion is called 1-1 insertion. For example, if you have double bond, so here what happens is that 1-2 insertion is happening. Metal X bond is there. So this metal X bond undergoes insertion to double bond to give like this kind of species. This is called 1-2 insertion. What is very, very important in 1-2 insertion is that the M and X inserted, right? Both are seen to each other. X and M, both are seen to each other. That is very, very important thing we have to keep in mind in insertion reaction. So next one is the beta hydride elimination.
Sir, please have some water and come back, sir.
Yeah, that's why I thought,
Yes, sir, we can wait.
Okay, thank you. So beta hydride elimination, this is the last part of mechanism. So keep in mind that, in metal, if you have organic ligand, like a organic species if you have, and then particularly in beta position, like let us take here on metal, we have alkyl group. So this is alpha carbon and then this is beta carbon. In beta carbon, if you have hydrogen, then beta hydride elimination happens very facilely. You keep in mind, particularly for students, particularly in metal catalyzed reaction, carbon monoxide insertion is very, very fast. After carbon monoxide insertion, beta hydride elimination reaction is very fast. Remaining all oxidative addition, reactive elimination, transmetallation will all come later only. So in this case, what happening here, the hydrogen is there on beta carbon, this hydride shift to metal, followed by elimination, followed by cleavage of this metal alpha bond. You get like this kind of olefin species. This type of process is called beta hydride elimination. So for beta hydride elimination, if you see here, particularly what happened is that, so this hydride goes to metal. So which kind of hydride goes, if you see very closely, the hydrogen, whatever you are having on beta carbon and metal, both are coplanar to each other. What I mean coplanar is that, I make it very simple. here you have metal and here you have carbon. You see here, this angle is very important. So for example, if you have sp2 bond on metal or sp3 bond on metal, still if you have beta hydrogen, it won't undergo beta hydride elimination. For example, if you have alkyne moiety or alkane moiety, it won't undergo beta hydride elimination. If you have alkyl bond, particularly if you have sp3 bond on metal, then beta hydride elimination is very facile. That is first rule. Second thing is that the hydrogen, whatever is going to undergo beta hydride elimination, that should be same plane, coplanar, same plane to metal. So these things are very, very important. Now let us go for classical reactions. Till now we have discussed mechanism. Now what kind of reaction can be done with where you can apply this mechanism? Let us see here. Now you know very well about Hake reaction, Zucchini reaction. This all we know it very well. In Hake reaction, what you can do is that you can make olefin derivative. So in Hake reaction, generally you need organic halide. For example, if you take RX, let us consider this is organic halide. So first what happened here, palladium tetrahydrophosphine we take, palladium around surrounded by 4 ligand we take, that complex will be tetrahedral complex, tetrahedral geometry, and then when you apply heat energy or light energy, one of the ligand dissociates, and then this RX, this sigma bond goes and bind. After that again one ligand dissociates, and then you get oxidative addition. So in this way, oxidative addition is happening. After that, this double bond is done. Now, this double bond here, you have more electron density. This goes and bind with palladium. After that, insertion is happening. When you have a double bond, you know very well, you will get only 1,2 insertion. So like this 1,2 insertion will happen. So keep in mind that, like in 1,2 insertion, you get only syn geometry. So whatever, you get only syn geometry, you keep in mind. After that, you see here, in alpha and beta carbon, you have hydrogen, so that this hydride prefers to undergo beta hydride elimination. You have olefin derivative like this, so that you get back organic molecule, and then you get a palladium catalyst. So like that, reaction is happening. So this is a few example. Now let me go to my research topic. I'm going to talk about CH functionalization reaction. So if you see here, generally CH activation reaction can be done by 2 ways. One is non-chelation assisted CH activation, and another one is chelation assisted CH activation. So for example, let me go with chelation assisted CH activation. Let us imagine here I have aromatic moiety, and then in that aromatic moiety, I have a functional group. So in the, generally what happened, in the functional group, you have heteroatom, right? So this heteroatom has lone pair. Okay, so this lone pair donates electron density to metal, so that this directing group coordinates with metal, and then metal activates CH bond. Those type of reaction is called chelation assisted CH activation. So non-chelation assisted CH activation is nothing but in organic molecule you won't have any functional group. Okay, so due to steric entrance, for example, it's let us imagine radical mechanism involves, tertiary radical is more reactive. For example, in organic molecule, you have tertiary radical, secondary radical, and primary radical. And then by using, you know it very well, by using metal, you can generate radical, so that, tertiary carbon reacts very facilely. Those type of reaction is called non-chelation assisted. Okay, so now, frankly speaking, non-chelation assisted method is not very, very selective. You know it very well. In organic molecule, you have several CH bond, right? Let us imagine, let us take this molecule. So here I have 2 CH bond. Now I want to activate only this red CH bond. I don't want to touch this black one. But metal, could not recognize. Metal could react with both CH bond and giving mixture of product. So you don't have regioselectivity in non-chelation assisted method. Whereas in chelation assisted method, you have regioselectivity, let us imagine. But chelation assisted method, what you need is that you need a functional group. So let us imagine here I have organic molecule. Here I want to activate this CH bond. So in nearby carbon, I can introduce one functional group. Functional group is nothing but a kind of a directing group. So here I have introduced this carbonyl group, let us imagine. Now, in this carbonyl group, I have oxygen atom, let us imagine. In oxygen, you know it very well, we have 2 lone pairs. So that oxygen has more electron density. Keep in mind, this is very, very important for MSc students. In organic chemistry point of view, metal is electron deficient and all organic molecules are electron rich. Why metal is electron deficient? Mainly we deals with the transition metal. If you see in transition metal, d orbital, if you see here, always you have partially filled d orbital. And then let us take iron. Okay, so iron is d6 system. You have 6 electrons on d orbital, and then you have, of course, 2 electron on 4s orbital, and 4p orbital is always free. So that means metal needs more electron density. So all transition metals have partially filled d orbital. So that you keep in mind. So what happened here, metal, if you have, metal is electron deficient. Here in heteroatom, you have electron density more. So that this heteroatom donates electron density to metal. So now you have intermediate like this. So now metal site is fixed. So metal cannot go. So in this case, what happened? Metal can go here or here. But in this case, metal site is fixed. So this X, it's like a kind of cement, this cement directly attached with metal. So that metal site is fixed. So now this metal doesn't have any choice. So wherever nearby CH bond is there, it can activate. Okay, so now, as I said before, metal is electron deficient in nature. So X has given electron density. So still that electron density is not good enough for metal. So metal look for other electron density. So now here you have CH bond, you have sigma bond, right? In sigma bond, you have more electron density. No, you have covalent bond, right? Here you have carbon and here you have hydrogen. So hydrogen gives 1 electron, carbon gives 1 electron, so that you have covalent bond. So in this covalent bond, you have more electron density. So this sigma bond is done. That sigma bond gives electron density to metal. So during that time, whatever electron density is there in metal, that electron density transferred to metal. Okay, and then in metal side, now you have metal has more electron density. Let us take here. So metal has more electron density. How metal has more electron density? This lone pair has given electron density. This CH bond has given electron density. And then here, for example, if you have double bond, that also can give electron density. So now in metal side, you have more electron density. So now metal has to give back electron density. So metal look for it. So in CH bond, you have sigma star antibonding orbital. So in that sigma star antibonding orbital, metal gives back electron density. So keep in mind, whenever you keep electron density on antibonding orbital, that means that is equivalent to bond breaking. So during that way, what will happen is that the CH bond elongates. Okay, so if you look on pKa value before CH activation, the pKa value of let us take this now. Let us imagine here you have double bond. Let us imagine the CH bond pKa value is above 40. After CH, elongation, the pK value decreased drastically. Now you have intermediate like this. What to do with this intermediate? Now you can do CH activation in 2 ways. One is oxidative addition pathway. For example, if you take with metal with 0 oxidation state, you prefer to undergo oxidative addition, and then metal, let us imagine if metal oxidation state is 0, it goes to metal 2 oxidation state. This is one way. And another way, I don't want this hydrogen. So what you can do is that you can take mild base. Now this pK value of this hydrogen is less than 9 only. By using mild base, generally acetate base is quite good. So for example, if you take sodium acetate and then if you add over there, so this sodium acetate deprotonates this hydrogen and then you get intermediate like this. This type of pathway is called deprotonation pathway. My research mainly deals with the deprotonation pathway. This oxidative addition pathway is well demonstrated. So I'm not going to talk about oxidative addition pathway. I'm going to talk about only deprotonation pathway. Now, I was telling non-chelation assisted CH activation. I give one example. For example, here I have benzene, and then here I don't have any functional group. So, but here I have more electron density. So, if I take benzene and treat with palladium acetate, you know it very well. Benzene is more electron rich in nature. Palladium, like metal is electron deficient. So here, Friedel-Crafts type reaction takes place. Okay, so what happens, this is the nucleophile and then palladium acetate is electrophile. You get the Friedel-Crafts type reaction. You will get like this kind of intermediate. After that, this double bond inserts to carbon palladium bond, followed by beta hydride elimination. You get olefin derivative. This is example for non-chelation assisted CH activation. But I was telling that this reaction is not regioselective. Why? If you see here, benzene case, reaction is very easy. For example, in aromatic system, if I have R group, then there's a possibility for ortho activation, para activation, and meta activation. In all cases, I can have CH activation so that I get mixture of product. So it is not good. Whereas in chelation assisted CH activation, for example, now I want to activate this CH bond. In nearby carbon, I can have carbonyl. This is functional group. I can have it. So that, this here I have electron density. Carbonyl in oxygen atom, we have more electron density. So that this oxygen goes and bind with the ruthenium. You get intermediate like this. After that, this ruthenium undergoes here, ruthenium oxidation state is 0. 0. So it undergoes oxidative addition. You get ruthenium hydride. After that, if I treat with olefin over there, this ruthenium hydride inserts to this olefin, you get this kind of intermediate. After that, this one undergoes reductive elimination to give this organic molecule. In this way, what I can do is that I can activate the CH bond very selectively, and then I can introduce alkyl group over there. Okay, this is example for oxidative addition. Now, what I was telling that I'm going to talk about only deprotonation pathway. So, particularly with the ruthenium metal. Okay, so for this kind of reaction, variety of metal can be used like palladium, rhodium, cobalt, and ruthenium. But I'm going to focus on only ruthenium. So, as I said before, in chelation-assisted CH activation, CH bond can be activated by two ways. One is oxidative addition pathway, and another one is deprotonation pathway. In oxidative addition pathway, if you take metal with a lower oxidation state, then it undergoes oxidative addition pathway. You have ruthenium hydride. For example, if you don't want this hydrogen, if you want to deprotonate, along with metal, you can have acetate group. This acetate deprotonate bond, and then you get this intermediate. So, question.
Sir, some disturbances there. Hello, sir. Sir, voice is breaking, sir.
Hello. Video start.
Sir, Jagan sir.
Connectivity problem.
I think both audio, video disconnected, no, sir?
Yes, sir. Yes, sir. I think, sir. He'll be back, sir.
So ask him to rejoin, sir.
Oh, yes, sir.
Disconnected.
சார் ஏதோ கட் ஆயிடுச்சுன்னு நினைக்கிறேங்க சார். ஒன்றும் ப்ராப்ளம் சார். வாங்க சார், வாங்க சார். தேங்க்யூ சார்.
காலேஜ்ல ரீஓபன் பண்ணல இல்லைங்களா சார்?
சார் இனிமேல் தான் சார் பண்ணுவாங்க. இப்பதான் கொஞ்சம் குறைஞ்சி வருதுங்க சார். ஆமாங்க சார். ஸோ இன்னும் கவர்மெண்ட் எதுவும் டிசைட் பண்ணலங்க சார்.
எங்களுக்கு இங்க நேத்து லாக்டவுனு, அதே மாதிரி நெக்ஸ்ட் 8th அன்னைக்கு இருக்கு, அப்புறம் 20th 21st இருக்கு, 27 28 29 இந்த மாதிரி ஒரு 4-5 நாள் இருக்கு. இப்படியே லாக்டவுன் போயிட்டு இருக்கு
சார். இங்க இப்ப ஆன்லைன் கிளாஸஸ் ஸ்டார்ட் ஆயிருக்கு சார். ஆகஸ்ட் 3rd இருக்கு சார். ஸோ அதுதான் போயிட்டு இருக்குங்க சார் எவ்ரிடே.
வெரி குட், வெரி குட், வெரி குட். ஜெய்சங்கர் சார்லாம் இப்போ வீட்ல இருந்துட்டு கிளாஸா இல்ல வந்துட்டு?
எல்லாருமே வீட்ல இருந்தா எடுக்கிறோம் சார்.
ஓகே ஓகே ஓகே. சரி சரி சரி.
சார் ஒரு நிமிஷம் போன்ல பேசிட்டு வரேங்க சார். Yes, sir. சார் மியூட்ல இருக்குங்க சார். சார் ஜெகன் சார் மியூட்ல இருக்குங்க சார்.
Okay.
Yes, sir.
Sorry, sir.
No problem, sir. It's okay, sir. Online classes, it's this type of problems.
It's very common, we can't.
Yes, sir.
Okay. So what I do is that I take my PowerPoint file and then I present here. So a few minutes. Yeah. Headset में जाते हैं.
Sir, unmute.
Yeah. Can I start now?
Yes, sir. Please, sir.
Yeah. So I am really sorry for the disturbance. So due to this network problem, I have to change the computer.
No problem, sir. No problem, sir. Please carry on, sir.
Okay. So now, lastly, I have discussed that how to activate by using ruthenium complex, how to activate CH bond of organic molecules. But basically, you can ask question. Both intermediate looks like same, but what kind of a variety of reactions we can do? But if you see very closely here, this reaction I have explained previously. If you take acetophenone and treats with olefin in the presence of ruthenium 0 catalyst, you can make ortho-alkylated compound. So this reaction goes via oxidative addition pathway, the above pathway. But if you see here, same reaction, if you do in deprotonation pathway, you can make ortho-olefininated derivative. Here double bond is there, no? In oxidative addition pathway, that double bond converts into single bond. Whereas in deprotonation pathway, this double bond stays as such. So that in this way, how same metal but different oxidation state does different type of reaction. If you see here, in oxidative addition pathway, this ruthenium hydrate undergoes insertion reaction with olefin. That's why we get ortho-alkylated compound. In deprotonation pathway, you don't have hydrate. So in this case, what happens? The carbon ruthenium inserts to the double bond, so that beta hydrate elimination takes place, and then you get like this kind of molecule. So this is one set of reaction. But even you can change the selectivity of product also. For example, if you take substituted aromatics and treat with the internal olefin, okay, and then if you do with the ruthenium 0 active catalyst, you have a molecule like this. Here, this aromatic moiety and phenyl, both are attached at same carbon. If you do same reaction in deprotonation pathway, the regioselectivity changes. You see, particularly concentrated here, the aromatic moiety and then this phenyl, both are trans to each other. So this is the beauty of the reaction. So, sir, can you hear me? So,
yes,
is it
sir.
clear, no? Yes.
Yes, sir. We have no problem.
So now, still, how many minutes that I have? I can go ahead.
Yours is the last one, sir. So no problem, sir. You please carry on, sir.
Yeah. So no problem, right?
Yes, sir.
Yes. Okay. So now, generally, if you see very carefully in this reaction, in ruthenium catalyzed reaction, so selection of chelating group is very, very important. We usually say directing group. So if you see here, the role of directing group, we know it very well. So, for example, you have plenty of functional group. Okay, so in the functional group, only heteroatom coordinates with metal and then do CH activation. So if coordinating atom is nitrogen, let us imagine. Those type of directing group is called strong directing group. And then if oxygen is coordinating atom, or pi system, even double bond or triple bond can be coordinating atom. So those type of reaction is called, those type of chelating group is called weak chelating group. So for this kind of reaction, ruthenium 2 is active catalyst. Generally, ruthenium diacetate complex, this complex is very, very good for nitrogen containing a chelating group. For example, if you have oxygen and or pi system, this catalyst is no longer very useful. So you have to look for other catalysts. The reason is that nitrogen is more electron rich in nature compared to oxygen. So oxygen is it's a electron negative, more electron negative compared to nitrogen. So that oxygen doesn't like to prefer with the metal. In those cases, you have to use cationic complex. So this cationic complex, if you see here, oxophilicity of this complex is very, very good. So that because basically this complex is there, this complex is more electron deficient in nature, although oxygen is more electron negative in nature. So that this cationic complex goes and bind with oxygen very nicely and then do CH activation very effectively. So what I want to conclude here is that by using neutral catalyst, you can activate CH bond by particularly nitrogen containing a chelating group. For oxygen or pi system, you need a strong you need cationic complex. This is the basic information I want to give here. And then now what we have done. So here, by using this catalyst, we have activated variety of CH bond of organic molecules, and then we have done variety of transformation. But I am going to talk about how to make olefin. Okay, so now let us take here Generally, if you want to make olefin derivative, what we do, we initial days we have done with the elimination reaction. So later on we have done with the Wittig reaction. Wittig is fantastic reaction. Only problem is side product. You get phosphine oxide. It is very, very unstable. You know, I mean, it is very stable. It is not easy to destroy phosphine oxide. So that in industry level, although you can make olefin derivative very easily, but you cannot destroy this phosphine oxide. That is the problem. So later development happens, and then what happened? You know, like egg reaction came into the picture. In egg reaction, if you take organic halide and treat with olefin, in the presence of metal gases, you get olefinated molecule. For example, instead of alkene, if you take alkyne, you get tri-substituted olefin. But you know, this is Nobel Prize winning reaction, fantastic reaction. But what is the problem in this reaction? If you see here, let us take here I have taken orthoiodoacetophenol. And then here what basically I have done is that this bond is cleaved. And then I have connected this carbon and this carbon. So you see here this molecule. But the molecular weight of this whole species is 245. And then molecular weight of styrene is 104. So if I mix together, I'm getting only 222. But I'm here wasting 127. Molecular weight. In atom economy point of view, this reaction is not that much good. Here, the waste product what we make, hydrogen iodide, the molecular weight is very, very high. Let us imagine same reaction. If I do with instead of carbon iodine bond, if I do with the CH bond, then what will be wasted? Here one hydrogen will be wasted and here one hydrogen. So molecular weight wastage is only 2. So in atom economy point of view, this type of reaction is very, very good. Apart from that, in order to make this molecule, here you want to have iodination, right? That itself takes more number of steps. So to overcome this problem, CH activation came into the picture. So this is our first report in 2011 we have reported. So by using ruthenium catalyst, you see here coordinating atom is oxygen, so that we take cationic complex. Here we take ruthenium chloride parathymine. This is our catalyst. Here AgSBF6 we have used. What is the role? You know it very well. Silver is very good halogen scavenger. If you here I have silver, this silver take it out chlorine, so that this SBF6 goes to ruthenium. I have a in this slide I have a clear explanation. So what happened? You get a cationic complex like this. Okay, so this is active catalyst. Here I take this catalyst, and then I said acetate base is very important to deprotonate this CH bond. If we want to deprotonate the CH bond, you need acetate base. So what we have done is that we have taken potassium acetate and treat over there. So here we have prepared this ruthenium diacetate complex, and then once you take a silver AgSBF6 antimonate over there, the silver take it out acetate, and then SBF goes to ruthenium, and then I have this kind of complex. This is active catalyst. So this catalyst, in this catalyst, this acetate group only deprotonate the CH bond, and then reaction happens, and then I make molecule like this. So via this way, we have activated CH bond of variety of organic molecules. You take here in this molecule, we have activated here, and then we have prepared olefin derivative. And then in this case, you see here there are 2 hydrogen for activation. One is here and another one is here. But here we have activated at this carbon. And then in this case, I have 2 functional group. One is a ketone and another one is ester. But ketone is very good directing group, so that here I have activated. And then here there are 2 hydrogen. One is here and another one is here. But here CH activation takes place very effectively. And then in this molecule, very interesting thing is that, so in this carbonyl group here I have, right? Here one CH bond is there, here one CH bond is there. But if you use palladium catalyst, you can do CH activation here. You can make this molecule. Whereas if you use ruthenium catalyst, you can activate CH bond here, and then you can prepare this kind of molecule. Okay, and then we have done this reaction with variety of olefins. In all cases, like a reaction worked very well, and then we have prepared a olefin derivative very effectively. Now we have extended this chemistry with benzaldehyde. Benzaldehyde, this formyl group is done. It's very, very sensitive group. Generally if you have air, this aldehyde easily oxidizes into acid. Okay, that is the problem. But here we have done this reaction very effectively, and then we have prepared plenty of olefin derivatives without having any trouble. In all cases we have prepared, but very interesting thing is that here this formyl group is not affected. So later on what we have done is that even you can do with the heteroaromatic system. Even in indole you can introduce olefin bond here. Even in thiophene, you can introduce olefin bond here. In all cases, you can make this molecule very effectively. Now, what application here we have done is that we have prepared this molecule, and then under photochemical condition, what we have done is that we have connected, we have cleaved the CH bond and connected here. So that here we have prepared 4-member carbonyl compound. When you change the substituent here, instead of methyl, if you have methoxy, you can make like this kind of tricyclic molecule having 1 6-member ring and 3-member ring. Like this kind of application we can do. And then next we have extended this reaction with the phenol substituted moiety. So in this case, in phenol directly, if I take phenol, reaction won't go. So here what I have done is that here we have introduced one carbonyl group, amide group. After that we have activated the CH bond, and then we have prepared plenty of olefinated compound. Okay, these all are applications. Okay, and then the reaction also worked very well with a variety of olefin derivatives. In all cases, we got corresponding compound in very good yield. Later on, we have cleaved this amide part is there. No, we have cleaved by using base. Now here we have taken benzone nitride. In benzone nitrile, if you take benzone nitrile and treat with methyl, 2 coordinations are possible. One is nitrogen coordination, and another one is this kind of pi coordination. But this pi coordination is very, very less likely. But in this reaction, very selectively, we have done pi coordination. After that, we have prepared, we have introduced double bond over there. And then later on, by using this molecule, again, we have introduced one phenyl group over there here very effectively. And then by using AD mix beta, we have prepared phthalate derivative, chiral molecule. This is nothing but a chiral reagent. By using this reagent, we have prepared this chiral molecule very effectively. And then the same reaction, in previous reaction, here we have used silver acetate. In the same reaction, if you use copper acetate, here reaction goes in different way. In copper acetate, what happens, this CH double bond N is there, no? That converts into amide. After that, we have activated CH bond, and then we have introduced double bond over there. And then we have done cyclization reaction, Michael type reaction, Michael type addition, and then we have prepared like this kind of heterocyclic molecule very effectively. But here, what important point is that the double bond here is that now this is Z geometry, Z geometry. It is very less likely, but this Z geometry is is stabilized by this hydrogen bonding. Here you have oxygen and hydrogen. So here, due to this hydrogen bonding, nicely you can stabilize Z geometry, and then you can prepare. So next, what we have done is that by using this methodology, we have prepared natural product. You see here this molecule. This is folk medicine in several Asian countries. This kind of molecule shows very interesting biological properties. So this is our retrosynthetic plan. So first we want to take benzoic acid and then treat with amine. We want to make amide. After that, we want to activate the CH bond and the NH bond, and then connect with this double bond, and then here we can make. And then later on, we want to do dihydrodeal reaction. In typical deal reaction, you need beta hydrate, butadiene. But in dihydrodeal reaction, in aromatic system, you have one double bond, and then here you have one double bond, and then benzene reacts over there, and then you get like this kind of molecule. Later on, you can cleave, and then you can make molecule like this. So for that, what we have done is that here we have taken benzamide and treat with olefin, and then we have prepared variety of isoindolone derivative. And then next, by using benzene, there are several ways to generate benzene, but this is one of the way. Here, if you take cesium fluoride, here F minus comes. This F minus cleaves this carbon silicon bond. Here you have carbon ion. This carbon ion cleaves this OTF. Eliminates this OTF, and then you get benzene. This benzene undergoes a dihydrodeal reaction with this double bond and this double bond, followed by elimination of the sulfonyl group, and then you can make like this kind of molecule. Now, by using this strategy, here we have prepared 6 different type of alkalides. Here, if you see, in all alkalides, I have N-methyl group. So we have taken N-methyl benzamide, and then here, by using ruthenium catalyst, we have prepared this isoindolone derivative, and later on we have done deal reaction with the benzene, and then we have prepared plenty of alkalides. And then here, in remaining 4 alkalides, we have NH bond. So here what we have done is that we have taken NPMP, so that this is easy to cleave, right? So here we have prepared this molecule, and then we have done dihydrodeal reaction. Later on we have cleaved this PMP moiety, and then we have prepared plenty of alkalides. And then now, previously, whatever I have discussed, I have used only activated olefin and styrene. But here, by using cobalt catalyst, we have done, we have done alkylation reaction with unactivated olefin. This type of olefins are less reactive in nature, but by using cobalt catalyst, we have activated the CH bond, and then we have done alkylation reaction. And then even by using allylic alcohol, we have done vinylation reaction. And then by using allylic acetate, we have done vinylation reaction. So like plenty of reaction we have done. And then even by using 2 equivalent amount of olefin, we have done olefination here as well as here. And then here, if you have already olefin derivative, here also you can introduce olefin derivative. And then like that, we have prepared plenty of molecules. And then this is the mechanism. Here, this cobalt activates the CH bond. After that, this olefin goes and inserts to this carbon cobalt bond. And then you have intermediate like this. After that, here you have beta hydrogen. So that beta, you see here this intermediate. Here, this is alpha position and this is beta position, and this is also beta position. But here you have 2 hydrogen, here you have 2 hydrogen. This hydrogen and cobalt both are not coplanar to each other. So here beta hydride elimination is not possible. So here this hydrogen is there, this is coplanar to each other. So after rotation, so here beta hydride elimination takes place, you get orthoallylated compound. Whereas in this case, what happened, like this base deprotonates this CH1, and then here reaction is happening. So next we have done what is that CH alkylation reaction at room temperature. But the very interesting thing here is that in this reaction we have done alkylation at room temperature along with the formation of hydrogen gas. So you see here benzamide reacted with olefin in the presence of cationic ruthenium complex to give olefin derivative. In the reaction, hydrogen was formed as a side product. And then how to prove hydrogen formed in my reaction? So generally for this kind of gas, you have to go for GCMS. And then in order to prove that, we have taken deuterated solvent. In this case, we should get HD, but HD cannot be identified by GCMS. You have to go for isotopic resonance mass spectroscopy. For example, if we want to know the stone of age, we know, right, this stone is 1,000 years old, this stone is 1,500 years old, we get this data, right? So for this kind of data, we have to go for IRMS instrument. So by using those instruments, we have figured it out HDS gas. And then, by using this strategy, we have prepared a variety of heterocyclic molecules. Here we have taken benzimidate, and then we have activated this CH bond and then this NH bond, and then connected to this carbon, and then we have prepared this molecule. This molecule is very, very sensitive in nature, but if you expose this molecule in air, you get this kind of unwanted products. So once you prepare this compound, immediately you have to store it in organic solvent. And then later on, by using this kind of molecule, you can do a lot of transformation. For example, by using simple acidic condition, you can convert it to amide. And then apart from amide formation, even you can introduce double bond over there. And then even by using base, you can rearrange this system. You see here, this 5-member can be rearranged in this way also. And then this is mechanism. Here, the CH activation takes place here. After that, olefination is happening. Beta hydride elimination is happening. It's all typical mechanism. Already I have discussed. And then this is quite recent result. Okay. So very interesting thing here is that in this reaction, we have used rhodium catalyst. Okay, so when we use rhodium catalyst and treat with alkene, in this case we got olefin product. You see here this double bond here stays as such. Okay, so in same react, even like you can use cyclic olefin also, like malamide, like this kind of malamide also you can use. In those cases also you can connect very nicely the CH1 to this double bond very nicely. This all reaction you need rhodium catalyst. Okay, the same reaction, if you do with the ruthenium catalyst, everything is similar, but catalyst is different. But in this case, you get only alkylated compound. You won't get double bond. You see here in previous case, you get double bond, right? When you do with the ruthenium catalyst, you get only single bond. That is the beauty of this method. Okay, and then this is the last part of my talk. Very recently, we have observed this reaction. So here we have taken benzoic acid. Okay, and then here we have activated this CH bond, and then we have connected with this olefin system. This is unactivated olefin. We have connected with this olefin system, and then we have done this reaction at room temperature only. Okay, so now this reaction worked with a plenty of olefins. In all cases, we got a really good yield. Even the system is working very nicely with the olefin also, like this kind of acrylic acid also. Here also you can activate CH bond, and then you can connect double bond over there. Okay, and then this is the mechanism. Okay, in this if you see, this is quite complicated mechanism. So this is called methyl-cycle intermediate. To prove this mechanism, we have prepared this methyl-cycle intermediate. How we have prepared is that we have taken benzoic acid and treated with the stoichiometric amount of rhodium catalyst, and then here we have prepared this methyl-cycle and then treated with olefin. Okay, so that we got a corresponding compound. This result clearly says that like this is key intermediate. in this reaction. So first, what is happening here? This oxygen coordinates with metal, and then this rhodium activates the CH bond, and then you have intermediate like that, and then this olefin inserts, to this carbon rhodium bond, followed by reductive elimination, you get this molecule. So like that reaction is happening. So I would like to stop here. What we have done here is that by using metal catalyst, we have activated CH bond very efficiently, and then we have prepared variety of olefin derivatives. Okay, if you need di-substituted olefin, you have to go for a double bond. If you need a tri-substituted olefin, you have to go for alkyne. Okay, only I have discussed this small part. So what is I want to conclude here? In almost 30 to 40 years before, if you want to prepare olefin derivatives, you have to go for elimination reaction. In elimination reaction, selectivity problems are there. Later on, Wittig reaction came into the picture. In Wittig reaction, what is the problem? You get side product triphenyl phosphine oxide. So to overcome that problem, Hake reaction came into the picture. Again, in Hake reaction, atom economy is not that much good. Okay, so now in this recent observation, what we have done is that we can also prepare this olefin derivative via CH activation. That is the recent advancement. So that down the line, if you want to prepare olefin derivative, maybe in another 10 years, people can use this method to prepare it. Okay, so here at this occasion, I would like to thank my student, my PhD students, for their hard work. So due to that hard work only, I could make it, this much a contribution in this area. Meanwhile, I would like to thank my present institute, IIT Madras, and then my former institute, ISAR Pune, and the funding agencies for financial support. And then, I would like to thank for your kind attention. Thank you very much.
Thank you, sir. Thank you, sir.
Thank you. Yes.
Very nice presentation, sir.
Yeah.
Sir,
it's a very hot topic. It would be really, new topic. Why I choose is that it would be really helpful for students. So what is happening in current scenario? So this MSc students can prefer, will know what type of active research is happening in international level. That's why I choose this topic.
Really wonderful, sir.
Yeah, thank you. Yes.
Can I, sir? Can I?
Yes, professor. Yes, professor.
Oh, that is.
Sir is from IICB Calcutta, sir. Dr. Parasuraman Jaishankar.
Oh, hello, sir. Thank you. Hello, sir.
Dr. Jagan Mohan, it's a fantastic work, really.
Thank you, sir.
I'm really mesmerized with your CH bond activation.
Thank you,
it's
sir.
a fantastic one.
Thank you.
As you rightly told, the importance of your CH bond activation reaction is that it's not activated one actually. Whereas you have, whereas the even Hake, Suzuki, and all they were using halides, boronic acid, and all those things are activated one actually.
Yes.
So
yeah.
you are using the intramolecular activation actually, in the sense that intramolecular neighboring group participation kind of activation. You are
Thank you,
using.
sir. Thank you.
So it's a really very excellent work, and I should congratulate you for the high class research you are carrying out.
Yes,
if you don't mind, I have a couple of questions with the
please,
permission
sir.
of the organizers. If they allow me, I can ask.
Please, sir. Please, sir. Please.
Okay. So in almost all of your reactions,
yes, sir.
say, so for example, benzene and styrene.
Yes, sir.
So you're always getting the terminal CH2, addition, you can say.
Yes, sir. Yes, sir.
Terminal olefin. Actually.
Yes, sir.
But that's quite obvious, actually.
Yes, sir. Yes, sir.
In the sense that.
Yes, sir.
But how to make it actually inside the CH bond, actually? Whether
So like a substituted olefin, you mean?
Exactly. Substituted
yes, sir. It's a very, because a lot of developments have to happen in this area, sir. So the major drawback I can say, what is that? Again, what you have pointed out is that, like alpha and beta, if you have substituents, sir, reaction goes, but yield is not that much great. So yield is very poor, 20%, 30% in this. So that the issue is there. And then, now we have reaction is going, but, yield is very poor. So particularly in those cases, I think we have to go with a new metal complex and then we should explore.
So I got your point actually.
Yes,
so still there is a scope.
Of course.
Still there is a scope for the research scholars to take up this issue.
Yes, sir. Yes,
because this is a really very challenging one.
Yes,
see, ultimately it leads to the chiral version. If you do it in the not the terminal one, inside one CH.
Yes, sir.
Actually.
Yes, sir. In
It
chiral
needs to, if
version,
you take
yes.
chiral version, actually.
You are
That is
true, sir.
really.
Yeah, you are
Exactly.
true, sir. You are true.
So it is, it's a challenging one.
Yes, sir.
And the next question is that actually you have used rhodium, if I remember correctly.
Yes, sir. Yes, sir.
Melimide.
Rhodium, ruthenium, all.
No, that's fine. Sir, for melimide, actually you have used melimide, you have substituted melimide, I suppose.
Yes, sir. Yes, sir. Yes.
With the rhodium.
Yes, sir.
Is it rhodium with the ruthenium? I just forgot actually.
Actually, sir, in particular case, it is a rhodium only.
Yeah,
but even ruthenium can be used.
I wanted to ask the same question actually.
Yes, sir. Yes, sir.
Whether the ruthenium is also giving rise to the same product or is it
yes, sir. Yes, sir. Yes, sir. So actually, the reason is that, sir, this is in this case, I conclude here, sir. Actually, rhodium is very, very reactive metal. But reason is, rhodium is very, very expensive compared to ruthenium. But if you see here, sir, here you get a kind of 1, 2, 3, 4, 5. 6-member kind of transition state.
Yes,
so ruthenium is not very effective, sir, for this kind of melamide reaction.
Okay.
So that's why we have used rhodium. But if you remove one carbon and then if you take directly amide, ruthenium can work.
Okay.
It's already known.
Okay. So thank you very much. And
thank you, sir. Thank you.
I wish you all the best.
Thank you very much, sir. Thank you.
Thank you.
Congratulations, Dr. Jagan, sir.
Thank you, sir.
I have one question, sir.
Please, sir.
You have prepared di-substituted alkene and tri-substituted alkene, am I right?
Yes, sir. Yes, sir. Yes, sir.
One paper you have cited in the Nature, the other another author.
Yes, sir. Yes, sir.
Your paper present in the organic letter, am I right?
Yes, sir. Yes, sir. Yes, sir.
In that paper, you have used the alkene and as well as alkyne.
Yeah.
Alkene, there is no change in the hybridization, whereas in the case of alkyne becomes alkene. How it is possible to convert? In the earlier stage, you have told that there is no change in the bond.
Yes, sir. So here, what is happening? Let us imagine you are having
exactly. PowerPoint is 20, I think. Slide number.
Yeah. Is there? Can you see, sir, this one? PowerPoint? Are you able to see?
Yeah.
Yes.
Yeah.
So in this case, what is happening? This triple bond is there, right? This triple bond goes and binds with the ruthenium. So in this case, ruthenium hydride inserts. After reductive elimination, you have double bond. But in deprotonation pathway, this carbon ruthenium, inserts to the triple bond. That is the reason. Remaining all are same.
Why specifically is ortho positions occupied? Because of a ring space, huh?
Why ortho position is, we have, that is true, yes. But if you increase this carbon length, let us imagine, here I have carbonyl, sir. If I increase little bit, I can activate meta also. There are examples. And then even if you increase this carbon length, it comes here and then even you can activate para also. These all are known.
You have told that it is a simple type of Friedel-Crafts alkylation reaction.
Yes.
Right. So arene is ready to accept electron deficient species.
Yes.
Okay. In your substrate, you have used some ketone.
Yes.
Amide.
Yeah.
These are all say electron withdrawing substituents are present. So under the circumstances, how it is possible in your ortho position?
Yes. So in those cases, what is happening here? You have an oxygen atom. So oxygen has a lone pair. So this, generally lone pair donation is quite strong compared to, like a pi coordination. Here in benzene system, if you have electron cloud, no doubt on it. But this electron cloud is above the benzene ring. So now there are two possibilities of coordination. One is like a pi coordination and another one is lone pair coordination. But metal prefer only lone pair coordination. That is quite strong. So that's why, what happened, this oxygen goes and bind with metal. So after that, if I go here, maybe here. So, yes. So after that, what is happening here? So now there is a possibility. So here pi coordination and then lone pair. So lone pair is dominates. After that only here deprotonation is happening. So no more Friedel-Crafts reaction.
Okay. Sir, you have used both carbonyl compound as well as phenolic compound, right?
Yes.
and under the circumstances, which one is undergoes alkenyl reaction is much faster?
Yes, sir. This is a really good one. I will go to that example. So now, if you want, here phenol you are having. So
Yeah.
now, if you want to do heat reaction, then palladium is very good catalyst. So what is beauty with palladium is that generally we tell no, so this is a chelation assisted CH activation, but palladium can undergo Fiddlecraft type reaction also. So when you take this molecule and treat with palladium, so palladium will see whether we can do chelation assisted CH activation or Fiddlecraft. But in this case, Fiddlecraft dominates and then you can do very nicely. But ruthenium metal prefer only chelation assisted. So ruthenium metal cannot do Fiddlecraft reaction. So that's why reaction is not going with the phenol. So even if ruthenium coordinates with this oxygen atom, you get only 4 members. So it is not very facile. That's why reaction doesn't happen. So that what we have done is that here we have introduced one more chelating group, like a carbon group. So that here metal goes and bind after the CH activation is happening.
Okay, great.
Yes.
Nice, sir. Nice presentation.
Yes.
Excellent work.
You.
Congratulations.
Thank you.
Okay.
Participants, do you have any questions? You can unmute yourself. You can ask the questions. Sir, a few questions are posted in the chat box, sir.
Okay.
Yes, sir.
Yes.
Why ruthenium catalyzed reaction in your case is different from palladium? Palladium catalyzed?
Yeah, so palladium is the 16 electron system. So palladium cannot go to 18 electron system. So that is, but ruthenium can go to 18 electrons. So that is the basic difference. So due to this electronic nature, reactivity changes. And that is first one. Second one is palladium is more, if you see here in the periodic table, it's more electropositive in nature compared to ruthenium. So that minute thing changes the reactivity.
Yes, sir. Another question posted is, why PT and PD are much more active than other metals for hydrogenation and dehydrogenation catalysis?
Yeah, same thing. The answer is same only because it's a more. If you go to periodic table, the second row, third row is more reactive due to this frequent, very easy oxidation state change and then several other reasons.
One of our student asked that one. PG
that's
student.
Good one. Yeah, that's good.
Yes, sir. He asked it, sir. Then our last question is, sir, in slide number 26.
Yeah, 26.
Yes, sir. Why you have used only 25 mole percentage of copper acetate?
Yeah, that's a really good one. I'm really happy. Student asked this question.
Pias Saha from Jammu and Kashmir.
Okay, sir. So that is a really very impressive question. Like if you see here, if you want to activate CH bond via deprotonation pathway, you need base. But in this case, you need stoichiometric amount of base. Okay, so let us imagine if I take 100 molecule, I need 100 molecule of copper acetate. But in this case, what is happening? We take only 30 mole percentage. So in this reaction, if you see very closely, cuprous, CuOAc2 is there. This cuprous copper acetate is there. No, this copper acetate give one acetate to ruthenium, and then come back cuprous acetate as a side product. This is side product. And then in the reaction, acetic acid is also formed as a side product. Okay. So, and then generally we do this reaction under air atmosphere. So during that time, Wacker type, Wacker oxidation reaction, Wacker type reaction, catalyst, copper chloride is regenerated. In similar way, cuprous acetate reacts with acetic acid under air to give copper acetate, so that we have regenerated. Here you need copper, stoichiometric amount of copper acetate only. But here multi-catalytic reaction is happening, so that we regenerate copper acetate in this way.
Yeah.
Fine, sir. Very
hello,
informative.
Sir.
Yes, sir. Yes, please ask.
Hello, sir.
Yes, please.
Yeah, actually, sir, I am P.S. Shah. Yeah, actually, I'm from Hyderabad Central University. Professor
nice.
Professor A.K. Shahu sir's lab.
I see.
Project yeah, sir. Yeah, so like you just now told, the question was 25. So like on what criteria means, like if the reaction is not under air means this case, or the side product acetic, then in that case stoichiometric amount is required, means little bit means I do not understand.
Yeah. Actually, now a lot of developments happen. This is 2011 we have done it. Now even oxygen is there. For example, if you take oxygen balloon, that oxygen balloon also can convert copper acetate. I mean, air generally, of course, oxygen only. But this all based on your reactivity only you have to study. For example, your reaction is very fast, then this kind of oxidation happens very nicely. For example, if your reaction is very slow, then you need stoichiometric moment. A lot of factors involved. But if you see here, since you have done project with the Sago, the recent development you can see here. Yeah, here. Yeah, so in this case, if you see here, even you don't need acetic, copper acetate. Even you can do reaction in acidic condition. No, generally, after beta hydrate elimination, you get ruthenium hydrate species like this. So if your reaction medium is basic, then reductive elimination is happening. For example, if your reaction medium, if you make it slightly acidic, then what happens? Right? This hydride, this is H minus. So this H minus gets a proton from acetic acid and then goes in form of H2, and then this acetate goes into the ruthenium. So in that way also you can avoid even copper acetate.
Okay,
so
thank you. This is nice, sir. Thank you, sir. Thank you. So just one last question, sir. You told just the catalyst developed by your groups. Like, can you little bit? I did not go that time. Like, what type of catalyst you are developing your group?
Initially, what happened? In 2011, there was no catalyst for activating CH, particularly in ruthenium. I'm talking about only ruthenium chemistry. In 2011, only this kind of neutral catalyst was used to activate CH bond. But this neutral catalyst was very, very good for nitrogen containing chelating group. Whereas if you go for oxygen containing chelating group, there was no catalyst during that time. So what we thought is that this oxygen is more electronegative in nature. So we thought due to more electronegative in nature, this coordination between oxygen and nitrogen is not happening. So we thought based on rhodium chemistry, we were very much impressed. In rhodium chemistry, they have done with the cationic complex and then they have activated oxygen containing diatom group. So what we thought in ruthenium case also it's possible. So we thought like if we prepare cationic complex, then this oxophilicity. If you see here, this ruthenium is there. This counterion takes more electron density from ruthenium, so that this species is more electron deficient in nature. So in that case, this species doesn't care whether oxygen or nitrogen. Wherever electron density is there, it goes on point. So in that way only, we have used this cationic complex. And then particularly here only one cation. In cationic complex, you have only one counterion. That we have studied here very elaborately here. So we have prepared a dicationic complex and then monocationic complex. And then even we have changed some other counterion like PF6, OTF, BF4. So among a variety of studies, we found that this is the best system.
Okay. Thank you very much, sir. Very nice work by your group, sir. Thank you.
Thank you.
Yes, sir. Jayan sir, fantastic presentation, sir. Excellent information you have given. Yes, sir. One more request from our side is our students are the students studying in our college, particularly in the chemistry department, are coming from poor backgrounds.
Yes.
So kindly give you a chance to do PhD in your prestigious institute.
No, yes, we are very much happy.
Yes,
See, particularly for students, I will communicate. Students are there.
Yes, sir. Our PG students are there. You
see,
please.
Now lot of possibilities are there. If you see here, there is an institute called ISAR. ISAR came up, IIT already are there. Now what happened? Now possibilities are really good to do PhD. So students have, have to clear either GATE or CSR. Okay, so that once they clear, they will get it wherever they want. So of course, in my group, I am very much happy to take, no doubt. Okay, so if any students come, I am very much happy to take. But I tell to our students that don't be in Chennai environment. Try to go to north.
Our Parsuramans are also there, sir. Sir is ready to take care. Frequently, sir is asking, and please send your students, like that.
Yes.
Even for Korea, also sir asked, sir.
Yes. So students should go out and then should learn new things.
Yes, sir. In fact, I also have the same
Yes, sir. One of our student called Farin Sultana. He is in second year MSc, sir. She wants to go to Korea, but only because of that attendance and other problems. Yes, sir. No, sir. The academic issue.
I think you need to solve this issue. You need to solve this issue because even Taiwan is also ready to take the second year MSc students, for giving exposure for a couple of 3 months, 4 months, 5 months. But I think this somehow you need to talk to your faculty and you need to talk to the higher authorities to make this kind of, because we need to allow them to go abroad now during their post-graduation study to encourage them to come to the research line. I think this is, I think need to take care of it, sir.
Yes, that's very good idea. Yes.
Sir, I have the same request now also. Next week, there is going to be a requirement for working in the COVID repurposing of the drug, which my lab is involved. I need a RA, but with MSc with the 2 years also will do.
Yes.
So thank you very much, sir. Thank you.
And then, sir, please communicate to students that clearing GATE or CSR is must, at least if you want to do PhD in our country.
Definitely, sir. Definitely,
that's must. And then easily, it's not big deal, sir. Actually, if the students read,
they can pass easily, yes, sir.
Yeah, they can. If they look CSR or GATE question paper for last 10 years, and then they will get the idea, and then easily they can clear.
Sir, in that line, sir, the chemistry syllabus for postgraduate degree, simply you adopt the syllabus of the NET syllabus, sir. See, this is what actually is being done by the Vidyasagar University in West Bengal.
Yes.
They teach 2 years only that one, sir. You will find 40 students. Earlier it used to be 100% students used to be qualified, used to get.
Actually, for them, Madras University only, sir, set syllabus. No, if I am true.
No, I think they have got autonomy.
Autonomous, sir. Ours is autonomous only.
Presidency is autonomous.
You can, as sir suggested, you can adopt actually, so that the students can clear very easily.
Yes, sir. Now, this academic year, we are trying to introduce the CSR syllabus, sir. But due to this pandemic situation, it's.
That's good. Okay, so there is a talk. That's great. That's a good thing. That there is initiation.
Yes, sir.
If you need anything, please, I'm
definitely,
happy to. Yes. So recently we have changed our structure at IIT Madras. We put lot of effort, and then we have now nice syllabus. So that you can also look on our syllabus and then slightly we can modify it, so that students will be benefited.
Sir, yes, sir. Every students of our college wants to meet IIT peoples, and they are seeing IIT peoples like what giant like, sir. But
no, we are here to help our students.
Yes, sir. That's why I'm asking, sir.
We are very much happy, sir. At any time they can approach us.
Yes,
so not only me, my colleagues are really happy to help our Chennai-based students. So we are very much happy to do that.
Yes, sir. Yes, sir. We will send our students to you, sir.
Surely, sir. Surely.
Yes, sir. Yes. Thank you, sir. Thank you, sir.
Yeah, thanks, sir.
Ma'am, Shanti, ma'am. Sir, your slides are sharing, sir.
Yeah.
Yes, sir.
Thank you, sir, for the wonderful presentation.
Thank you.
Really, you did a remarkable job. Your presentation is highly informative and updated the current research trends. Thank you so much.
So, due to lack of time, I have gone a little bit fast in, in research publications. Maybe, I'm here only. If everything COVID problem over, I can come directly and give, 2 to 3 lectures.
You're welcome, sir. You're welcome.
Yes.
Okay.
Yes, sir.
Yes.
Well, today the program went on well with the blessings of Almighty and support and cooperation of everyone. I'd like to thank Dr. R. Ravanan, Joint Director of Collegiate Education, Dr. O. R. Devanathan, Principal in Charge, and Dr. N. Indira Gandhi, Head Department of Chemistry, for the blessings and motivation. I also thank all the faculty members of Department of Chemistry, Presidency College, for the kind cooperation. I also thank today's speakers, Dr. A.K. Ghosh, Dr. Parasuraman Jaishankar, Dr. S. Prabhakar, and Dr. D.M. Jagmohan for sparing their valuable time and for their outstanding presentation. I also thank all the participants. We appreciate you being here. Once again, thank you so much for joining us today, and let's see tomorrow at 9:45 a.m. Thank you.
Thank you. Thank you.
Thank you. Bye bye. Thank you. See you
Thank you,
tomorrow.
sir. Thank you, sir.
See you, sir.
Thank you, sir. Thank you, sir. Thank you, sir. Thank you, madam. Thank you, sir. Sir, Vijay, sir. Thank you, sir. Sir, madam, actually, madam, thank you, ma'am. Sir, thank you.
Thank you, ma'am. Thank you very much.
Thank you. Thank you.
Sir, madam is there. HOD, madam. is
HOD,
there.
ma'am. Thank you very much. And Shanti, ma'am, thank you very much. Excellent, compilation and fantastic arrangement. Thank you.
Thank you. Thank you, sir.
Thank you. Bye.
Thank you, ma'am. Ma'am, shall I end the meeting now, ma'am?
Thank you.
Ma'am, HOD, ma'am, meeting unmute. Ma'am, mute lurking, ma'am. Mute.
What I'm not able to do. Oh,
Ma'am,
okay. Thank you so much, sir.
yes, ma'am. Shall I end the meeting now, ma'am? Meeting.